Hello, folks. Hi, Nihar. Can you hear me?
Yes, you're good to go.
Awesome. So we have 2 minutes. Okay. Let's get started. Good morning, everyone. Welcome to the workshop, Visual Perception and Learning in the Open World, VPLOW for short. My name is Shu. I'm the primary host of the workshop. Because of the complexity of the open world, I cannot attend the conference in person. So let me greet you remotely. In the open world, I hope everyone is safe and healthy. Today is Father's Day, so happy Father's Day. The goal of the workshop is to connect people and let people exchange ideas. I hope the workshop to be a venue where we can discuss new opportunities and challenges related to open world vision research. The workshop is a hybrid. That means we have both in-person and online speakers and audiences. And we will use Zoom to broadcast the talks. And that Zoom is for speakers only. And we will use YouTube to live stream the workshop. And for in-person audiences, please enjoy the workshop and ask questions. For those who are watching YouTube live, please leave comments and questions in the Zoom, in the YouTube chat. And we will deliver the questions to speakers, and we will encourage the speakers to answer them by typing. We have a great lineup of speakers and organizers. We have 3 wonderful student volunteers who can help out the on-site logistics. This year, we have a challenge organizers who will be leading 3 wonderful challenges during the workshop. I'm sure you will find them exciting and interesting. You can find the full schedule of the workshop from the workshop webpage. You can scan the QR code to get to the website. I want to acknowledge all the wonderful sponsors from different institutes. Okay, let me introduce the open world. Initially, the open world says a recognition system has to continuously update with additional object categories, be robust to unseen categories, and have minimum downtime. But nowadays, we use the phrase open world to mean many different things, such as in the wild, in the real world, robustness, continual learning, anomaly detection, adversarial attacks, domain adaptation, so on and so forth. So it's good to see that the people are addressing different challenges in the real open world. But what are the concrete challenges? To understand them, my strategy is to bump up 1 level and consider how we build open world visual perception systems. If we do so, I see a cycle from many applications, including autonomous driving, recommendation systems, and so on. Basically, we first start with the data collection. We annotate the data and train a model over the data, and we test the model before we deploy the model for the applications. But it's not done yet. We use the trainer model to snowball our data, to collect more and annotate more data. And we keep training and continuously updating the model for a better application. So this is a cycle. So why we do this in a cycle again and again? Because we see many challenges in the open world. But what are the other challenges? I summarize 4 aspects. First, the open world is vast. That's why we have unknown objects. We have never before seen situations. We have to address them in the vast open world. Second, the open world is imbalanced. There exists many rare or infrequent situations or classes, and we have to address the rare classes to build a fairer and better model. Third, the open world is unpredictable. We have limitations in the visual sensors. We have to address the limitations to address the unpredictability of the open world. Fourth, the open world is dynamic. That means we have a data distribution changing over time from place to place, and we have a semantic ontology or class labels evolving over time. So let me walk through the 4 aspects by presenting our recent work. First, in the vast open world, we have to detect the unknowns. Unknown recognition is an important problem to have and to address in the open world. Typically, when people study unknown recognition, people focus on enabling a closed road trained system, like a KV classification model, to recognize the unknown or open set input. But the closed road trained system is sort of flawed. If we want to address the open world, we have to train it in the open world. That said, we can use open world data or outlier data to better train a model for open set recognition. Actually, we can train a two-way classifier to classify the input data into known versus unknown. This idea is not new. Outlier exposure does this exactly. It trains a two-way classifier to do this. It is quite effective on many benchmarks, but it also fails catastrophically when the training outliers do not span the open world. So can we synthesize outliers to better span the open world? Of course we can, but synthetic data is very easy to recognize. That said, they are less useful to train the open set likelihood function or the open set classifier. So we are motivated to train a generator to generate hard and useful outlier data to better train the open set likelihood classifier. If we do so, we are training again, where we train the generator to synthesize hard examples. And we use the GAN discriminator at the open set likelihood function. So this idea is very neat, but it doesn't work in practice because of the unstable training of GANs. So our solution is simple. Let's combine outlier exposure and GAN and propose the Open GAN method. Open GAN method uses the real outlier data to stabilize the training of the GAN discriminator and the GAN generator. It uses the GAN discriminator at the open set likelihood function. And it learns to synthesize hard outlier data to better train the open set likelihood function. So this is the nice story, but this is not the end of the story. Remember that we care about the discriminative power of the GAN discriminator. That said, we don't really care about the quality of the synthetic images. So our final version is Open GAN in the feature space. We extract the features from the already trained KV classification model. The features are in low dimensional, and we find it more efficient to generate fake low dimensional features than high dimensional RGB pixels. In this sense, we enable closed world system to be readily modified for the open world. Without showing you any detailed results, let me jump to the salient conclusions. In a real open world, we should embrace open world data. We should synthesize outlier data to better span the open world. And we should use low-dimensional features rather than high-dimensional RGB pixels for the open world. All right, let me jump to the imbalanced open world. And one important problem is the long-tailed recognition. We want to train the KV classification on long-tailed class distributed training set. And we hope the model to perform well on all the imbalanced classes. Of course, a naively trained model on such a data set will perform well on common classes, but very poorly on the rare classes. So how to address this issue? Our observation is that this naively trained model has larger weights for common classes in the classifier than the rare classes. That motivates us to balance the weights during training. If we balance the weights, we can boost the performance from a 38% accuracy to 53% accuracy. And we explored 3 simple techniques to balance the weights: weight decay, max norm, and L2 normalization. Let me show you the results of a weight decay. In the literature of long-tailed recognition, embarrassingly, we didn't tune the weight decay, but weight decay encourages learning small and balanced weights. It penalizes the larger weights more heavily than the small weights because of the L2 penalty. So if we tune the hyperparameter for weight decay, we can improve the performance. If we increase the lambda, we get a better performance and much better than before until we get a very large lambda, which will dominate the loss. So we have a worse performance. That makes sense. But anyway, you can see the boost from here to here. That is amazing. Of course, we explored 2 more techniques for weight balancing: max norm and L2 normalization. Max norm encourages learning larger weights within a norm ball, and L2 normalization makes all the weights have an equal norm. It is the ideal case, but it lacks the flexibility of training a better model. That's why it performs worse than the other 2. Our model, our final model, combines weight decay and max norm. That outperforms the state-of-the-art methods significantly. The state-of-the-arts are more complicated than ours. So our salient conclusion is like this: we should balance the weights to improve the long-tailed accuracy. And we should regularize the network for a strong baseline for long-tailed recognition. And we have a paper on Wednesday to discuss more in depth. I'm happy to chat more later. Let me jump to the unpredictability of the open world. You know, the RGB camera has limitations. It cannot capture the human signature in the dark night, but a thermal camera can. That motivates us to combine multi-modal signals. And we focus on multi-modal fusion for object detection by fusing RGB images and thermal images. This is a well-studied area where many papers focus on fusing features to build a better detector. But our take is different. We ensemble detectors. We fuse detections. The benefits are, if we do this, we can fine-tune a pre-trained RGB detector on thermal. So we have a better single model detectors. And if we do so, our method will be more robust to modality or sensor failure. If one sensor fails, we can still rely on the other sensor. So the question is how to fuse multi-modal signals, how to fuse multi-modal, single model detections. Perhaps a naive method is to pull them without doing anything, but this will produce overlapping detections. So how to remove overlapping detections? We can use non-maximum suppression. You know, NMS can suppress the detections by keeping the higher scoring detection and remove the lower scoring detection. It is quite effective, and it is quite novel in the context of multi-modal fusion. But NMS with information, because it drops one modality completely. So how to leverage the two modalities? One method is to average their scores or average fusion. This is the popular practice, but this is not intuitive because it decreases the scores if we average them. It is not a probabilistic. If we want a probabilistic method, we should boost the score if two detections agree, right? Our model is called a probabilistic ensemble or PROBEN. It is a non-learned method that is derived from first principles. It can boost the score if two detections agree. Without showing you any detailed results, I want to present the salient conclusions. PROBEN performs the best in various setups. It improves off-the-shelf detectors, and in the real open world, we should use a PROBEN for fusion, not average. All right, I will not talk about the dynamic open world because we have speakers talk about it. Let me welcome our first speaker, Tini. Tini is a professor at KU Leuven. Her research interests include robust visual representation, multimodal analysis, continual learning, lifelong learning, novel object discovery. So all of these topics are open world. Okay, let's see what she's baking. So Tini, it's all yours.
Okay, thanks for the introduction. Can you confirm that you can hear me?
Yes.
Okay, then let me see if I can share my slides. Can you see my slides?
Yes.
Okay. Okay, so I'm sorry I cannot be there. It's one of the first times we can actually meet again and have a physical conference. I was looking forward to it a lot, but yeah, we have exams here in Leuven, and so I had to be here, and I couldn't come to CVPR. And so I appreciate that. Yeah, you make time for me, even though it's a virtual presentation. It's not ideal, but let's make the best of it. My title is rather vague. I just had a few ideas that I wanted to share on continual learning. And so indeed, I won't cover the entire breadth of open world problems and settings, but focus purely on the dynamical aspects, the continual learning. And so I don't think I really have to introduce this problem here anymore. So continual learning basically is learning from data that is non-IID. So we have changes in the data distribution, which means that we cannot just learn everything simultaneously. And so typically the way we tackle this or we look at this is that we solve different tasks one after the other. Critical aspect here is that we don't have access to the old data, because if we would have access to all the data all the time, we could just shuffle the data and the problem would be solved. We have, again, a standard IID task that doesn't change. But in practice, we do have those shifts. And then the question is, how do we learn new tasks without forgetting the old ones? How can we keep on learning and get better and better models? And so that's what I've been focusing on over the last few years. And several people in my team are working on that. And so I just want to point to a few things we have been working on recently and share them with you. And I'd like to start with a survey that one of my PhD students, Eli, did recently. And so he basically looked up all the papers on continual learning at ICCV, CVPR, and Europe's of last year, and basically categorized them based on the task they're solving. And so as you can see from this plot, the literature is dominated by classification tasks. To some sense, that's not surprising, that's logical, because classification is like the mother of all deep learning problems and architectures. And so if you want to have the most standard architectures, then you go to a classification task. Whereas if you go to other tasks, it might get more complex or more specific and so on. Still, I want to make a point that maybe we are looking too much at classification within our field. It's good that there's a lot of work on classification, but of course, computer vision is not just classification. There's a lot more than that. And if I talk to people who want to apply continual learning in the real world, then often their problem is not just classification. And so this is like, a call for looking wider, looking beyond classification, looking also at other problems and how we can actually build and incorporate these ideas of continual learning in a more broader setting. If you look at the other tasks that are actually tackled, I found it surprising to see that there's more work on semantic segmentation and even generative tasks than something standard like object detection. And I guess part of that is because object detection actually has more changes to the architectures than semantic segmentation. But also it seems that just doing knowledge distillation works reasonably well there. And so people might say, okay, there's not such a big issue with object detection than with classification. But I'll come back to that towards the end of my talk if I still have time, where I'll say a bit more about work we have been doing towards continual object detection. The others part here is basically, any task you can imagine, but then usually there's only one paper and they just say, okay, we try the standard stuff of continual learning in this context or in this context without really doing something really innovative there. Okay, and here's another plot that shows the current state of the art. This needs a bit more explanation, I guess. So based on the same pool of papers, we try to categorize them a bit along two axes. That is the input, and so vertically, and the output horizontally. And so I don't say anything new if I tell you that the most studied setting is the strict class incremental setting, where we have distinct distributions in our input as well as in our output. So task one just looks at a few categories, then you switch to task two that looks at a different set of categories, and so on. And so our output distributions are really disjoint, and also our input distributions consequently are disjoint. There's no overlap there. Now, if we look at the methods or the data sets that people tackle, we were happy to see that gradually people are moving to larger scale data sets. So it's not anymore just split MNIST, split Cypher 10, although they're still widely used. There's more and more trends towards like ImageNet or subsets of ImageNet, like tiny ImageNet or mini ImageNet. So to make it a bit more real world, more realistic. Still, this class incremental setting, I guess, can be criticized in many ways, and it's not what we have in the real world. And so instead of having these highly disjoint distributions, both in the input and in the output, actually we want to relax that to become more conform with what we see in the real world. And so that brings us, on the one hand, to the domain incremental setting. And again, that's reasonably well studied. So in that setting, basically all the classes are seen in all tasks, but we shift, for instance, from day to night. And there we see that although it's studied quite a bit, it's still studied often on these very small, very academic data sets, like permuted MNIST, rotated MNIST, or like sometimes a sequence of different tasks. So this is like the different data sets combined. It's not as real world or large scale yet as we would like to have it. And also the fact that here these distributions are so clearly disjoint is not what you have in practice. It's not that one moment it's clear and the next moment it's dark. You have a gradual transition from daylight to dusk. And so instead of having these disjoint distributions, actually what you have in practice is more like gradually changing distributions. And so you see that when you focus on these gradually changing distributions, there's far fewer works that tackle these. And again, I want to call on the community to maybe put more effort in these. And the good thing is that recently data sets have become available that tackle these. Well, Cohort 50 has been around for quite a long time already. But so recently there's also this clear challenge, and later in the workshops there will be a lot more about that. We have had on our side a challenge at last ICCV focusing on autonomous driving, where we had one challenge based on classification and one challenge based on detection. And there we focused not just on gradually changing input distributions, but also gradually changing output distributions, which really I think also is a key concept of like real world applications. When it rains, there's fewer pedestrians on the streets. And so you cannot assume that you have this nicely balanced setup. It was already mentioned in the intro, like imbalanced data is a key problem that is like not taken into account enough in the current literature on continual learning. And so I think we should really move more and put more effort on these real world settings. And so that means that instead of just trying to solve the catastrophic forgetting and get like a few percentages better there in this extreme case of disjoint distributions, maybe we should relax that and we can revisit some tasks and so on, but then focus on really, can we keep on improving? Can we have this positive transfer? Can we improve our methods over time in spite of data imbalances? And there I want to stress this can be both within and between classes. So you can have a class that's really underrepresented, that's rare and that doesn't occur often, but also within a class, you can have some like specific conditions that make it much harder or much infrequent, and therefore the prototypical cases for a given class will be easy to classify and remember, but then the corner cases are things that typically are missed, and so getting this or being able to cope with this is much harder because of course we don't have the labels, so we cannot easily identify them. We should focus more on scalability, and also I think domain shifts should be considered more. Like there are papers that also evaluate on domain incremental learning, but there's actually very few methods that come up with explicit methods for the domain incremental setting and really exploit this optimally. And so I think there's still a lot of improvement possible in that direction. So these are, I think, a couple of big open challenges where I think there's a lot of work to be done. And because there's a lot more data available, thanks to benchmarks these days, we are ready to actually start tackling them, and it would be interesting to see what that gives. Now, at the same time, and that's the second part of my talk, I think there's also still a lot of interesting stuff to be done on these very standard setups, like these academic setups, if you want. So if we just have like a split of a given data set, it's not the real world, and you can argue it's how relevant that is. But the good thing is that there at least we have control and we know exactly what's going on. And I feel like we are still lacking a lot of the basic intuition and insight in what's really going on when we learn tasks or keep on learning dynamically. It can be different tasks, or it can be from streaming data. And so if we don't really understand what's going on there, we also cannot really control and expect that we can cope with it properly. As a simple example, we had some discussions. We had some discussions in our group recently, like what would happen if you just take split MNIST and you can cycle over the different tasks multiple times. So you don't learn each task once and that's it, but after you've learned the 8s and the 9s, you go back to the 0 and the 1s, and so you can have multiple cycles like that. Would such a network ultimately be able to learn all the tasks, or would it keep forgetting and focusing on the last tasks? And we couldn't actually agree on it purely based on our understanding of the tasks, even though it's very simple, very clear. And so it turns out that actually it depends on how you set your parameters and so on. So we don't really have a full, we cannot predict whether it can learn or not, or what's going on, even in this very simple task. And I think that means that, we need to also look further into what's going on during the learning process and how things work there. Another question related to that is like, will a network overfit to the samples in the buffer or not when using replay? So replay nowadays is the most widely used method to tackle catastrophic forgetting, to a large extent because there's a lot of emphasis on this class incremental setting. And then if you have never seen like the old and the new classes together, it's very difficult to define the decision boundary between them. And if you look at the literature, there's a disagreement on whether you will overfit to the samples in the buffer or not. You have a small buffer, and so yes, there is this risk of overfitting, but will it happen or not? Some people say yes, some people say no. So what we did in a paper we presented at ICCV last year is trying to visualize what's going on if we learn 2 tasks with replay. And so we try to visualize this in parameter space. So what you have here on the left, W1, would be the optimum of after training your first task. So these are the parameters for which you reach a global minimum or a local minimum for task number 1. Then if from there you would learn a second task and you would just fine tune, you would end up in the point here on the right, W2 FT. If we learn the new task with replay, the idea is that we end up somewhere over here where we have a low loss for task 1 and a low loss for task 2. And that's what actually happens. So you can observe that the trajectory that you find in this parameter space will first start moving in the direction of this fine-tuned optimum, as long as the losses remain relatively low. So you are in a kind of flat valley here, but then at some point the losses start to increase, and then instead of moving like this, you start moving upward, where you try to stay within the low loss region of task 1. Yet there's a difference between the low loss region for task 1 when evaluated on the test data or when evaluated purely based on the data in the buffer. And so it turns out that you end up exactly in that region where there is a difference. So yes, there is some overfitting to the the data that you store in your buffer. If we take different samples in our buffer, we will end up in another point within that same region. And so you can see that if you evaluate along those lines, like if you would draw a line between your original point and where you end up after training the second task with replay, there's like low values for your loss over that entire path. So you stay within the same loss region. You don't really jump to somewhere completely differently, but you do overfit a bit. Now this is just a drawing, so you may not believe us, but we evaluated that further, like looking at the actual loss surfaces in this space. Now this is a huge dimensional space. You cannot visualize it directly, but what you can do is to take look at a certain hyperplane in that high dimensional feature space and look at the losses within that hyperplane. And so we took a hyperplane through these three optima, W1, W2, and W2 after fine-tuning. And so then you can see that the trajectory actually indeed behaves like we plotted in the previous slide. It starts moving towards this point, but then actually deviates to stay within the low loss region of the first task. But with the buffer, we have a somewhat different loss function than on the test set. And so it basically has lower loss here than here. And so there's some level of overfitting going on. Okay. And so here's for mini ImageNet, but basically it's the same thing. Another point, and I don't think I'll have time to discuss the object detection, but that's fine. Another point we recently observed is what we call the stability gap. Here we said, okay, if you want to do continual learning and you really want to do it not task by task, but like in a streaming fashion, then it only makes sense that you would also want to do your evaluation continually. At this moment, what people typically do is they only evaluate at the end of learning a task. And that would be indicated by these red diamonds in this figure. So we have the number of iterations on the horizontal axis, task 1 accuracy on the vertical axis. And so after 200 iterations, we switch to task number 2. After 400 iterations, we switch to task number 3, and so on. And so here you see the performance after you've trained your first task. It hasn't converged yet, but we train in a streaming fashion. So after one epoch, we switch to another task. And if you evaluate then after training the second task, you think that there's actually not that much forgetting. It goes from 62 to 57 something. So there's a bit of forgetting, but not really that dramatic. However, if we do this continual evaluation, we see that in between, there's a significant gap. There's a significant drop in the performance of task 1. And so later, the learning recovers from that. And again, well, doesn't get all the way back to where it was, but gets reasonable performance. But in between, there's a situation where the performance on task 1 is really abominable. And this holds when you do fine-tuning, but the same thing can be observed with whatever continual learning method you use, whether you use replay or knowledge distillation or parameter regularization. We always observe this kind of stability gap where the performance drops and then recovers. And this is important if, for instance, you have a self-driving car that's continuously learning and updating its models. If suddenly it would switch to a different situation, then you don't want this drop in the performance that you see here. You want to have a consistent performance throughout, or you want to have like at least a lower bound on the performance that you could get. Looking only at the red diamonds, you would think that you're always doing okay-ish, but that's not true. There's like moments in time when you do a lot worse than that. Now, looking at this plot, if you have been paying attention and combining it with some of these plots, you might say that there's an inconsistency here, because here we seem to learn and not go far beyond the original loss. We stay in the same low loss region, whereas here we say actually we do have a significant drop. This is something we are currently investigating further. Our current hypothesis is that that these plots are basically just showing what happens in this one hyperplane, but of course your trajectory is not within that hyperplane. Your trajectory lives in a much higher dimensional space, and so that means that you might actually get a wrong impression from this figure, and so probably this one is more correct. But that's things we are further looking into. I have the references at the bottom of my slides, so if you want, you can look into them. We also had some work on continual object detection, but I guess my time is up. So to stick to the schedule, I suggest we just switch to questions for now.
So in person, folks, do we have questions? I cannot see you.
Can you use the mic?
Can we go back to the stability gap slide?
Sorry, I could hear there was a question, but I couldn't hear the actual question.
Can you hear me? Can you hear me?
Yeah, but there's quite some echo.
Yeah, so you talk about the accuracy drop, right? The stability gap. Can you? Yeah, I wonder how you calculate the accuracy when, like, for the task 1 after you learn new tasks. Are you still only calculating the accuracies for the task 1, or they are calculated together with others? Because there is a huge drop at the beginning of learning. So I wonder, is it because, like my friend Alex said, is it a learning rate, so they totally like ruin all the weights learned before, or just because the new classes they adding, right, and then we cannot classify the new classes and then the accuracy drops. So,
Sorry, again, the question was not very clear. So you're referring to the figure with the stability gap. And so I guess you want to clarify what I'm actually plotting there.
why
so
accuracy drop so huge at the beginning of the learning? Yeah.
So one of the hypotheses is that when you start learning the new task, you have very small gradients for your old task because you're in that local minimum, and you have large. So even if you have a buffer or anything, your buffer will not like your replay will not really play a big role because they give you small gradients, but your new task will give you very large gradients, and so you will be pushed away, and especially the last layer probably very quickly puts a bias towards the new category labels, and therefore, it kind of forgets the old ones, and it's only after a few iterations that the gradients of the old task become big enough to kind of do the recovery from there.
So you like after using distillation and replace of the gradient of old data can play a larger role so that they can learn together and get better performance later. But at first, the cannot like declare a very small compared to the new data, so the drop so hugely, right?
Yeah, but we were also surprised that that the drop is so big. I guess that's so initially we just.
Sorry. I wonder how you calculate the accuracy. Are they calculated together with the new classes or only the old classes? The accuracy.
So what we plot is accuracy on the old task, and so we have. But yeah, I suggest you look at the paper, which is on archive. So we have plots for different settings. I just took like one, and it didn't have the time to explain everything in detail. So again, like if you have if you just do fine tuning, it drops. If you do replay, it also still drops, and so there's none of the methods, but it depending on how you do the settings, it recovers faster, or yeah, you can make it drop a bit slower, but there's no setting where really you don't have any drop at all.
Oh, okay. Yeah, I understand. So, okay.
Okay, thank you so much. I think there is one more question. If it's quick, you can come to the mic and speak.
Thank you so much. So my question is that, so just now you explained that, so there is a significant performance drop at the beginning of each new task. It is because like the gradient for the replay data is very small, and so but why with the number of iteration increases, the gradient for the replay data will increase?
Sorry, can you repeat the last part? Why?
Okay, sorry. So my question is that, so you explained that the reason why there is a performance drop is that the gradient is very small at the beginning of each phase. But why the gradient of the replay data increases? Why it becomes more significant when the iteration increases?
Again,
The question is, why does the gradient increase after some time?
Yeah, so I guess if you're in a local minimum, your gradients are by definition close to zero, right? And so, but as your performance degrades, your loss will become larger and your gradients will become larger. I guess that was our intuition for it, but yeah, this is all speculations and not something we tested explicitly.
Okay, thank you so much.
Okay, I think thank you so much, Tine. I think in the interest of time, we'll switch to the next presenter. So the next presenter is Carl Wondrich. Thank you. So Carl Wondrich is an assistant professor at Columbia University, and he did his PhD from MIT. And Carl has been doing really great work at the intersection of unsupervised learning and computer vision in domain of specific to future prediction. And let us see what he has to show today in his talk. Over to you, Carl.
Thanks so much. I can do this. Oh, that was fine actually, because I can just present off of this. And just close it. Okay, great. Okay, everyone. Hi, everyone. It's great to be in first person. I thought I'd talk about kind of an approach that we've been trying to develop over the last few years at Columbia. And we're not the only ones doing it. There's a lot of people doing this, but we got really interested in this. And I think it just has a lot of advantages. Okay, there you go. Maybe this sounds better. I think this has a lot of advantages for trying to how to handle a lot of different problems in computer vision. So the title of the talk is Inverting the Neural Net. Okay, so yeah, kind of what is a standard computer vision problem is given an image, you want to try to figure out what's there, right? What is actually going on in the scene? And we all look at this image and yeah, we can tell there's a chair here, right?
But if you look a little closely, you'll see there's actually something behind that chair, right? There's a little slit over here, right? You can see there's something behind that chair there. And what is there? What is actually there? What's actually behind it? It's really hard to tell, right? It's just like one pixel column revealing something there. But if you look really closely at this, right, you should know something about the shadows, right? There's actually two different shadows here. There's the shadow from the red chair in the front, and there's a shadow cast by the thing that's occluded behind, right? And so the problem we got interested in trying to solve is, can we do 3D reconstruction? Can we try to reconstruct what's going on in the scene, which is a very under-constrained problem, by leveraging these other clues like the shadow that's cast? And this is a really useful signal to use, because when there's an occlusion, right, the shadow is actually is going to bounce off the line of sight and tell you something about that object. So here's an example of what our system does just from the shadows, trying to reconstruct what actually is behind there. So this is a very hard problem. It's under constraint. There's many different solutions here, right? But this is something we want to try to solve, right? I think we do this all the time, right? If we see someone walking down a hallway and we don't see them, we see the shadow, we can infer that they're there. And shadows are all over the place. Not all images have shadows, but most of them do. And this is a really interesting clue in the real world, right? That we can try to use to solve different computer vision problems. Okay, so the task here. Okay, essentially the task that we want to try to solve is, given an observation of the shadow, what are the 3D objects that could have cast the shadow? What are all the set of possible objects that could have created this shadow? And the standard way that a lot of other people solve this in computer vision today, right? The most common approach is basically to cast this as a regression problem. We can collect some training set of input output pairs and train this regressor, try to map from what we observe as the shadow to regress some representation of the 3D object. But this approach actually has a lot of different problems, and this is where I think it comes into this workshop about how do we do kind of this robustness to the open world. If we just train this type of regression here, you get three main problems, right? One is this is going to overfit, right? This will overfit to the training data that you have. It's going to be specific just for that task and not have this flexibility, which you're going to need in order to adapt to any open world setting. You also just get one prediction, right? All these systems that do this regression, you get a point estimate. And this isn't going to work for a problem like this, right? I mean, most problems in computer vision are trying to solve an inverse problem. Shadows are just an extreme case of that. And you should be getting more than one solution if there's some uncertainty. And finally, any type of this kind of feed forward approach, it is very hard to incorporate constraints, right? You have the constraints you have about the world, very difficult to integrate into them. So we've been coming up with this kind of different approach to try to solve these problems. Rather than doing this feed forward inference, we're going to try to solve this by inverting a neural network rather than just running it forward. So the way this works is to figure out, we want to try to explain what's going on in that observed shadow there. And the way we're going to solve this is by taking a generative model of 3D objects and searching through it. What are the possible kind of scenes here that could have been generated by this generative model? They're going to best explain what we observe in this shadow, right? There's a lot of different generative models for different computer vision tasks. There's one for images, one for 3D. You can use GAN, you can use a VAE, right? You can take any generative model you have. Right? We want to try to search through it. When we try to search through, we want to invert this generative model to figure out what are the scenes that could have created this observation that we have. So, just one generative model by itself is not enough to solve all of this problem. The shadows depend on a lot of different things. It depends on on both the pose of the object, right? You can always rotate the camera, right? Change the pose, as well as the location of the light source, right? These are all going to change whether the shadow that you observe. And so we can actually integrate all this into a generative model. If we can use kind of advances in differential rendering to combine this with a generative model. And what this does is it writes down a forward model, which says, given where the light is, given some latent code that represents what the object is, and given the pose, it's going to render what is the shadow that you have observed. Now, that's what's written up at this top equation in the top right. This S hat is basically our estimate of what the shadow is, given the light, the latent vector, and the pose. And so then our problem in inference becomes, all we have to basically to explain the shadow, to produce a prediction, we just have to invert this process, right? We wrote down the forward process, and the way we're going to do perception now is invert it. We're going to try to go backwards. And so this is actually really easy, just to write it down as a kind of an optimization problem. We can write down a loss function between what our predicted shadow is and what the observed shadow is. And because this is all differentiable, right? Every step here can be made differentiable. We can just solve this with gradient descent, right? We're just going to do gradient descent in order to figure out what are the light sources, the location vector, and the pose that would have created this shadow that we've observed. Okay, so here's I wish I get rid of the bottom bar, but here's a video basically this optimization process in action. So what's cut off on the zoom here is on the bottom left is the input shadow. That's what the shadow is the input. And the middle column at the bottom is the current hypothesis, basically, when it tries to render the object forward. The top left is the original object. That's never seen. That's just shown through your visualization. And so what you can see going on here is basically what gradient descent is doing is it's searching over what are all the objects and what are all the poses and what are all the light sources that would have created this shadow, and you can eventually find, right, what is the object that creates evidence for the shadow. And the bottom right is showing basically this loss curve. It's a really hard problem to solve, right? This is not a convex loss surface, so this makes it quite challenging. But I think what's really cool about this is it's basically able to find, right, given just this very limited observation you have about the scene, just the shadow, it's able to actually define kind of what are possible shapes that could explain this. Okay, and so this can be used in lots of different scenarios. And this is what it kind of, when we started experimenting with this, we basically found it started working in all these scenarios where we were surprised, we were kind of somewhat surprised in some of the cases that it worked, because it really generalized outside the training set. I mean, it really was doing tasks that we didn't design it for. That's why I kind of thought this was so cool. So here's an example where it's trying to basically reconstruct the object when there's an occlusion, right? It wasn't designed for occlusions, it was designed just to invert shadows, given the full shadow. But even if there's just a partial shadow, it still can work, right? It's still, you know, even there's no training set of different occlusions, even though just a subset of the visible shadow is available, it still can find an object that matches it. So here we put two different toy cars behind this chair that are occluded, right? And it reconstructs, right, based off of the evidence, right, of the shadow. What are the possible shapes of that car? And it really, you know, I don't know, it really does work in some ways, because, you know, if you look at the shadows for the truck versus the sports car, right, it actually is figuring out some of the small details there to figure out what is the right shape that should go there. Here's another example for airplanes, right? Just based off of the shadow and some of the wing that's visible, right, it actually can reconstruct that object. We did, you know, we started all this in Blender, and, you know, what the reviewers were saying was, what about the real world, right? Does this actually work in the real world? And we're thinking, you know, does this really work? Well, at least let's try, right? And it does. This is what was so cool to me. Was it's never seen these real world images. It's trained just in this simulation environment, and out of the box, right? it instantly generalizes to these examples, even when the shadow is automatically extracted. So here's just some examples. We have many more where it's trying to reconstruct what is the object just based off the shadow. And it works, in different scenarios, even when the ground isn't completely flat, right? The sandbank is not, it's almost flat, but it's not completely flat, right? And it still is able to find some of the objects. And so I think this is something that, when you do this with just a feed-forward model, or you train this model for regression, it doesn't work because it overfits to the little details, right? It tries, the experimental models find any little pattern they can in order to exploit to solve all the tasks. Well, these generative models instead are actually really good for generalization, because they try to model what the data generating process is. And that gives you this flexibility basically to adapt to new tasks. This is a severely under-constrained problem, of course. So another advantage of this over just these feed-forward models is you actually get diversity in the reconstructions. It can generate multiple possible objects that are all consistent just with that shadow. So here's a few examples, both for a car and for a sofa. If you look at the bottom row, for example, that same shadow can be cast by a kind of a rectangular sofa as well as an L-shaped sofa. And the system actually can figure out kind of what's the full space of different ones. And it just comes out for free from this model, because you basically repeat the optimization process over and over again. You start with a different random seed and run this over again, and you get a different solution. So finally, one thing that's really nice about this is you get these faithful reconstructions. It incorporates constraints. Constraints are not actually incorporated here. So with a feed-forward model, you don't get any guarantee that the object you generate is going to be consistent with the shadow that you observe. But because you're solving this optimization problem and doing this inversion, trying to invert the neural net, these constraints are basically guaranteed you to hold. So I think this was a cool result, where if you actually start modifying the shadow, you perturb the shadow, we take a paintbrush and we start painting. We go from the top row to the bottom row, we add a little arm coming out. It actually changes the reconstruction and adds an arm to this chair, right? It figures it out, right? It actually is going to respect the evidence that you see. So we got pretty excited about this. I thought this was a pretty interesting result. We started thinking, like, what else can we invert? Or can we solve more problems to do this? Are there other types of problems being solved in computer vision just by trying to invert these models rather than just going feed forward? We started experimenting with some tasks in robotics, where we wrote down a forward model, basically that takes in the configuration of the robots, is like the joints of the angle, the arm angles, and tries to estimate a full 3D body of what your robot's own body looks like. So we call it a self model. It's a modeling of the robot's self. We're trying to model how the own robot's going to look, given its joint angles here. And so this is just a feed-forward model, right? This is a regression, essentially, right? Given what your angles are, try to produce what the body is going to look like. So what's cool about this is by inverting this model, you can use this for planning, and you can plan for a lot of different tasks, even for ones that you haven't really incorporated into your training set. So here's an example video of this, where the robot has to move its arm in order to touch a sphere while avoiding an obstacle, right? It has to avoid that red box. We've never shown it in an obstacle at training time. It's never seen an obstacle. We've never even told this model what the task is, right? The task itself was just to try to model itself, right? Given its own joint angles, what is it going to look like? And just by searching, I guess, no problem. Okay, and so just by searching through the basically the input space here, to arrive at the basically what we want the body to look like. We can say we want the body to be touching the sphere. We can just invert that model to figure out what is the joint angle that would be touching the sphere all while avoiding the obstacle. Okay. We've also been experimenting with this in other cases. We've been using this for just general robustness. In particular, everyone probably knows about adversarial examples, right? You have small noise to an image and it disrupts the classifier. And I think this is really a big crack in the current paradigm that we have for a lot of computer vision tasks. So what we found out actually with these adversarial examples, this is some work published at CCV last year, was that when you perform these attacks, it also disrupts the any self-supervised structure that there is. So there's all these different tasks for self-supervised learning, jigsaw puzzles, or contrastive, or mass auto-encoding, and so on. When you do an adversarial attack, it basically disrupts all right? It breaks it. It won't solve all the jigsaw puzzle correctly. So, you know, this is actually a clue you can use to improve the worst case, right? When there's an attack, when there is an adversarial attack, you can use the fact that the self-supervised structure should not be broken. That's always going to be available at testing time. You can use that in order to establish robustness. But to do that, you basically have to invert a neural net. So instead of doing this feed-forward inference where you get your estimate, right, y hat is just going to run the neural network forward based off the image, you can perform inference by basically inverting that neural net to ensure that your self-supervised structure is going to be respected. So the way this is written down is just y hat is going to be your adversarial attack, right? The image you get xa plus some perturbation vector r that you're going to find such that r is going to restore what the self-supervised structure is. You're going to solve this in optimization problem to find r, right? That's going to make the self-supervised structure restored. And this you have to do by inverting the neural net. You got to figure out, well, how do I modify r? What r do I find, right? That's going to cause a self-supervised task to be solved. And what's cool about this is it basically has this constraint, this guarantee that all this self-supervised structure inside G must be intact when you perform inference. So, you know, we experimentally showed this works quite well. You know, at the time, I think it got state of the art, kind of in the worst stage performance. But what's interesting is analytically, this also is a win-win for us or a lose-lose for any adversary. And the arguments, I think, is actually quite neat. The argument here as to why this is kind of analytically is strictly just a good idea is because if you want to try to if you have an attacker that wants to basically attack this model, they now have a harder problem to solve fundamentally. They have to solve a multi-objective problem, right? They got to both attack a specification objective as well as this self-supervised objective that we're going to use for our defense. And so this creates a Pareto frontier. Essentially, there's a trade-off between these two objectives. So no matter what, it comes out to be a win for us. If they completely ignore our defense, we're going to improve the accuracy. If they try to address the defense, they actually end up harming their attack because they shift some of their budget that they've used from the classification to the self-supervised one. So to me, these results I think are really exciting because it just shows analytically that, you know, doing this inversion actually has some intrinsic advantages for the robustness. Okay, the last thing in the last few minutes here is, you know, there's a trade-off with this approach, right? This feed-forward inference is really fast, right? GPUs are really well optimized to perform this very fast now. That's, you know, basically operating at real time. So the limitation for all of this is basically the speed, right? Because now you're performing inference. It's not just one step forward. You actually have to solve an optimization problem at inference, right? You got to do multiple forwards and backward steps. And what's worse is you're traversing this landscape that is not ideal, right? This landscape that you're traversing is not designed to do an optimization, to do an inversion. Right? This is highly non-convex, there's bumps, there's every worst case you can imagine in terms of this last landscape is going into being there, which makes this quite slow. So this actually can be addressed. This is some work that we're going to be putting on our archive next I guess on Tuesday, where we can actually speed all of these up. We can make them very, very fast, where we basically learn a new landscape where gradient descent is going to be efficient. Rather than searching through X space, which is what you typically do in inverting a neural net, we're going to learn a new space Z, which is what we're going to do our optimization in. And we're going to train this so that basically Z has nice properties for gradient descent. So gradient descent is going to converge quickly. And the way we map between these two spaces is just with the neural net data. And you can learn this neural net data to do this mapping so that you're going to converge quickly. And inversion can be quite fast. Yeah, so instead of basically your inversion is really fast, and rather than searching through X space, you search through this Z space, which is going to map through theta into X. And you can get to the solution very fast. Here's some examples of this. Hopefully this plays over Zoom. So this is going to be a video. It's operating in real time. So the frame rate is set to basically how long it's going to take the optimization to take. And it's trying to reconstruct these images here. On the left is going to be the baseline. When I play the movie, the left will be the baseline, which is gradient descent. The middle column is going to be our approach, and the right column is going to be the target. This is what it's trying to reconstruct. And what you're going to see as I play this, it happens a little fast, is that the middle column is going to converge much faster. The left column eventually is going to get there. It's just going to take a long time. So let's play this. Yeah, so kind of within a second, right? It's able to reconstruct the target very fast. The baseline is still going, right? Even after 100 iterations, it's still trying to converge. So we actually found that with this approach, we can speed this all up by order of magnitude and get much faster at trying to invert these neural nets. Okay, so I think I'm running out of time, so I want to wrap up. So yeah, I think it's a pretty interesting this approach. Basically using generative models that we can write down a generative model of what's happening in the visual world, and then we invert it in order to explain it. And I think we can solve a lot of different computer vision problems in that. We're not the only ones doing this. There's a lot of other people are actually working on this approach, but I think it's kind of been a silent, majority somehow. It's been exploring this. And I think there's just intrinsic advantages for any open world, and it solves a lot of problems that we see in this computer vision paradigm right now, right? I mean, it has these advantages for robustness and generalization about going beyond the training set. It fixes things like adversarial examples. Well, maybe fix too strong a word, but it makes serious progress on that. You get multiple solutions, right? You're not committed just to one point estimate now. For free, you get multiple solutions, and let's face it, in vision, everything's an inverse problem. There's always going to be multiple solutions. And you can put constraints in, right? This is really easy to put constraints. If there's some domain knowledge you have about the world, it's very easy to put constraints in, and it will respect those. So this was all done, all this work was only possible by the great PhD students in my group. I put their photos at the bottom here. We've been exploring this through a series of different papers. The first two papers we're putting up on archive. We've submitted archiving, so we'll go online kind of on the next time that archive updates. And the last two are already available. So I don't know. I think it's really exciting. I think it's a really interesting approach. I think it has serious advantages for generalizing to an open world. It's still a lot of progress to be made, right? It's still a lot of steps here, but this is very well on the top. Thanks so much, everyone. Happy to take any questions. Yeah.
Would you please help me understand a bit more about this shadow problem? Is my naive understanding correct that you are basically a line function and that a lot of records object towards
Yeah, I had a hard time hearing the question, but I think I understood. Okay. Yeah, so essentially what's happening here is we're writing down a forward model for how an image is rendered. And we're not actually rendering the full image. We just want to render the shadow. And basically, this is going to be a function of three things. It's a function of where the light is, what the object is, or if we call it a z vector, and the pose of the camera, right? So we can basically build this forward model. It actually is pretty straightforward to build this forward model. We have a generative model for the objects. This is like a GAN trained on ShapeNet, for example. And then rotation is really easy to do for the camera pose. And then you have to have some module that can do rendering of the shadow. And so you have to render shadows in a differentiable way. So there's been a lot of advances in differential neural rendering. We actually couldn't find a way to do differential neural rendering of shadows, so we had to create one. It actually was really easy. It just was max pooling basically along rays. So you can write down this forward model essentially of how a shadow is produced, and then you try to explain a shadow you see in the scene by inverting that. And this is how you explain it. Does that answer the question?
Yeah. So I guess I would ask two questions. First, is it even practical in real life to actually know where the locomotion has in most cases? Why is the consideration not to look at the shadows in the same scene and then reconstruct the object out of the shadow? The second question is, I think there are a lot of lighting conditions and poses that would cause the same kind of shadow or differential objects. So how do you actually resolve that? I think that would be able to extend to a broader question, like what if the mechanism is not actually one-to-one, but
Right.
multiple-to-one? How do you address this?
Yeah, those are great questions. So we actually can search for the light location. We don't have to know the light source location. We assume there's only one light source location, but I think it's going to be generalized to the arbitrary number of light sources. Yeah, and so this is also operating in kind of a prototype in some ways, minimal example of can we get this to work in a simple scene. As generative models improve, I think it will be possible to make this work in more and more complex scenes. This is basically our hypothesis: is advances in generative modeling is going to enable big advances in kind of analysis tasks in computer vision, because we can just invert it. So it's not out there yet. We basically there's generative models for 3D objects now. There's starting to be generative models of 3D scenes, right? But as these improve, we think we can just invert those to solve all different analysis tasks. So this will be a debate to see if this comes true. But I mean, I think that's what we're seeing basically with all this kind of generative models are making huge advances each day, right? I mean, it's just incredible what they can generate now. I mean, DALL-E is a great kind of well-known example of that. But yeah, I guess the jury's out as to how this approach will work. But this is what we think. We think there are just intrinsic advantages to the approach. And so in some ways, this is, I mean, one takeaway from this talk could be a call for everyone to improve on generative models, right? Can we improve them? Because if we can, I think it solves a lot of issues that we see in computer vision.
So one question I have also about the shadow work is one of the striking examples you had is a single shadow can generate objects in category. One thing that was interesting is even though the shape is all different, all of them the same pose. I was wondering if you could speak a little bit to why it is, like where is it, what is the signal in the shadow that gives you pose? And if it's the case that you get consistently good pose, then can we do pose estimation simply from the shadow itself?
Yeah, that's a fantastic question. I believe in this experiment, we assume we know the pose. So I should have said that. If you actually free the pose and search for that as well, it will find different objects of different poses too.
Yeah, that would be cool to see, but yeah, it's nice to see the lots of variations.
Yeah.
So you showed a real-world example for shadow construction. So I'm wondering how you get primary maps for the shadow
That's, yeah. Right, that's another question. So these are automatically, so the middle column is showing automatically estimated shadows. There's been some, this is actually, there's been a few works in computer vision at trying to estimate, to kind of do segmentation of objects and segmentation of their shadows, and it's built off of mask RCNN. So we use a pre-trained detector off the shelf for that. So.
Yeah, so can it work also if the shadows are more blurry or very sharp?
Yeah, we haven't experimented with that yet. I think that'd be an interesting next step. Just increasing the kind of the complexity of the type of situations we need to consider. Okay, thank you.
Thank you so much, Carl. Let's give a round of applause for the speaker. Okay. Nihal, mute your. You have to mute this. Okay. So our next speaker is Judy Hoffman. Judy is assistant professor at Georgia Tech. Before she did her PhD from UC Berkeley, Judy has done extensive work in domain adaptation, transfer learning, and more recently in fairness. And let us see what Judy has for us to say. Okay, over to you, Judy.
Great, thank you. Hi, everyone. It's a great pleasure to be here today, especially in person. I guess we were all reminded of one of the joys of in-person conferences with the registration line, but I'm glad to see you're all here. So this talk is going to be about bias in vision systems, and we're going to be thinking a bit about all the complexity along and the bias that's implied as a result of those. So as Deepak mentioned, my lab works in a bunch of different areas. This talk is going to be mostly on this focus of bias. So this workshop is on open world recognition. And so I want us to all think about the world more broadly, all the different people, all the different places that exist in this world that we would like our vision systems to work in. So to do that, let's get started by thinking about all of the different data sets that our vision systems rely on. So of course, if we have tasks like classification, there's the famous data sets of ImageNet and Places. As you move on to detection and segmentation, the list expands. We have COCO, cityscapes. These are modeling different challenges that we expect in the world. So we have something like COCO that's trying to emulate a broad detection task. We have cityscapes that's trying to emulate a self-driving task. But one of the challenges here is that a lot of which we train and evaluate these models is by separating this data into multiple and evaluating on a held out piece. The assumption there is that that held out piece is emblematic, is representative of all the situations that you would like to deploy the system that matches the task that's being emulated in these data sets. And we know that this isn't a great representation. The previous talk was talking about adversarial attacks. We also have just general corruptions that could occur in our data. And as you perturb the data set, as you make changes, so this is one example from 2019, where they showed that small corruptions to images could result in a large performance drop on standard data sets. We also just have the fact that our world is highly variable. So we think about that task of semantic segmentation driving scenes that we have in cityscapes. First off, we want to be able to train models with supervision. We need to collect expensive annotations. And so naturally, we're going to be limited in how many annotations we can collect because, this data set or this type of data, this task is very challenging. It's very variable. We need to consider all kinds of different weather patterns, different cities to drive in, different car sensors. The list goes on and on. So it's clearly not feasible to actually collect all of that data to train on before you're going to deploy a system. And this is a real challenge. If we look at a model that was trained on just a subset of this variability, maybe it was trained on a sunny set of data, and then we want to ask how well it performs when there's snow on the ground. Well, this model fails miserably, especially in the regions that are covered in snow. So in this case, it's confusing the road and the sidewalk, which are kind of areas that were usually on the easier side to recognize, but here it's confusing them with things like building, because it hasn't necessarily seen that type of appearance of a. So in general, the things that can cause performance degradation is quite vast. A lot of it has to do with the way that we have captured and curated our data sets. So as soon as the assumptions change about how we have curated them and the type of data that we see at test time, the model is going to degrade. And I showed you an example that arises because of weather or because of, we can think of it as sort of sensor variations. In today's talk, I'm going to focus a lot on the ways in which our data sets can be biased against different demographic groups. And this really just means that the system can underperform for certain subpopulations, and it's often caused by underrepresentation in the data set, but it doesn't have to be. This problem was really propelled or kind of into the community's attention with some of the egregious failures that were publicly available on existing systems. Here's one example all the way back from 2015, where an open system made an egregious error on darker skinned individuals. And this led to some seminal work on studying how our systems might vary across people from different demographic groups. This work was called Gender Shades. And what they did was they first off collected a data set to even be able to measure this problem. So one of the challenges when you're trying to understand how well a system performs on underrepresented groups is that, well, they're underrepresented. So that means that it's inherently difficult to measure the performance because you don't necessarily have the data. So they collected this data set to fix that problem. They controlled for lots of different factors by having headshots of people. So that means that it was just close-ups of people's faces. And they wanted to have representation across different skin types. They used the Patrick skin type scale, grouped together types 1 to 3 and 4 to 6, and called them lighter scales. And then made sure that their data set was much more balanced across both skin type as well as gender. So now they were ready to be able to perform an evaluation and to really measure the inequity of existing systems. So here were their results. And perhaps for any of you who have been following the literature, it was unsurprising at this point, which is that the system performed very, very well on lighter skinned males and had substantially higher error rates on darker skinned females. So going from near perfect performance on lighter skinned males up to 20 to 30% error on darker skinned females. You could ask whether a problem is pervasive across different conditions or different tasks. It doesn't need face recognition or gender recognition. So to answer that, we looked at one of the off-the-shelf self-driving data sets. This is the BDD data set. It has a fair amount of variability. It's unfortunately only across 2 different cities, which is pretty common for a lot of the driving data sets to be heavily focused in just a few geographic regions. But it has different times of day, it has different weather patterns. So it's like clear that people are trying to make an attempt to have the type of variation that I was talking about before that you need to be robust against. The difficulty though, is that there's substantial underrepresentation when it comes to these skin types that I'm talking about. And so we used the same convention as the Gender Shades work, the same Fitzpatrick skin type scale. And we wanted to see whether or not we could measure how many skin types were, or what the distribution of skin types was in this data set for pedestrians. Now, admittedly, a lot of pedestrians are small or turn their back to the camera or things like that. So for those, we throw them out. We ask annotators whether or not they can even make a reasonable judgment about the different skin type. And we accumulate over a number of different annotators to make sure that it was a consistent annotation. And then as a result, we're able to get annotations for basically just close-up pedestrians. So these should be the easier pedestrians. Usually in object detection, the closer the objects are, the bigger the objects are, the easier they are. So this is a relatively smaller subset of the data, but it's the ones that we can make a characterization about the skin type. And what we found was that this data set had dramatic underrepresentation of darker skinned individuals. So in the training data set, you had 2,700 examples of lighter skinned and only 387 of darker. Now you can measure performance on these data sets across lighter skin and darker skin, but it's hard to make any statistical claims here because you only have hundreds of the darker skin. So this really just highlights, even though maybe we can say, oh, we found a small performance drop here, it really highlights a fundamental problem, which is that if we want to be able to address bias, we first off have to be able to measure it. And the protocol that I just outlined, this annotation or new data collection, is extremely time-consuming and costly. You have to predefine the access of fairness or the access of underrepresentation that you would like to measure. You then have to annotate it. You have to be very careful in that annotation process. And then you might end up in the situation we were in, which is after you've annotated it, you just don't have enough data. So once you have measured it, it's then really hard to make a judgment about what is the true cause of any inequity in a system. Is it because of the data set itself? In the case of dramatic underrepresentation, it seems like a fair assumption. But it could be something inherent to the model or the sensor or any other part of the capture process. If we don't have the data to be able to measure these things, then we can't even begin to make any claims for how to mitigate. If we don't have the data to measure, then we also don't necessarily have the data to train a new model to help improve this situation. So this makes it fundamentally different than the domain adaptation scenario, which is some techniques that I'll talk about a bit later for mitigation efforts. But the fundamental domain adaptation scenario kind of assumes that you have lots and lots of data in a target domain. It's just unlabeled. And so you can use excess of data to compute statistics and do alignment techniques to help mitigate any bias in an initial system. But again, if we don't have the data, we can't use those types of techniques. So first off, I want to talk about this problem of even just measuring the bias or defining the bias in a system. And there's been a lot of studies recently that have showed that manual annotations, in addition to being time-consuming and costly, are also just fraught with errors. It is particularly difficult to annotate these types of tasks. And so there's a lot of inconsistency among annotators. So let's focus on two different goals here. We want to be able to detect bias, ideally in a way that's not overly costly, so that it has a greater chance of adoption. And then we'd like to be able to mitigate any bias that we find. So for detecting bias, I'm going to highlight this one work called UDIS, which is an unsupervised discovery of bias system. And as a reminder, the challenges that we're trying to address is that existing solutions to measuring bias take a manual approach, manually defining the axes on which you would like to measure bias and manually defining or labeling rather all of these different attributes. The problem with that is that it can be difficult to pre-enumerate all of the conditions that you would like to measure against. And of course, it's very expensive to get these annotations. So with that in mind, we had a goal of trying to do this in an unsupervised way. We'd like to be able to propose a set of biases to an annotator or to a developer or researcher who can then analyze them in a more cost-effective way and decide what to do. So for this, we use an agglomerative clustering approach. And we took a model that had been trained with some task. So this is the assumption that you have a model and you would like to be able to understand the bias in a fully trained model. So on a test set, we can cluster in the learned feature space these images. And what we're going to do is we're going to essentially define underperformance as a form of bias. So we would like to find parts of the data that are cohesive and that are dramatically underperforming compared to the average of a system. So for example, if this system was getting 92% accuracy overall, and you find a cluster that's visually cohesive in the learned feature space, but has performance of 60%, this is something interesting to explore. It's a failure mode of the system. Whether or not it corresponds to a cultural form of bias, we don't know yet. But it's something that's underperforming, and so it's worthy of study. So we have some ways of measuring whether or not a cluster is distinctive, and we can use accuracy on this validation set to understand how well it performs. For this, we're going to use the Celeb 8 data set and the task of predicting whether or not a person is smiling. So this data set actually has annotations, but we don't use them in our unsupervised discovery approach. And we can find clusters that underperform that look like this. And to try to aid in our understanding of these clusters, understanding of why they might be underperforming at predicting smiling or not smiling, what we can do is we can use a visualization tool like GradCam, which is what's shown in the bottom row. And this tool tells us which region of the image the model is looking at to decide what to do in its prediction. So we know that to predict whether or not a person is smiling or not smiling, the model should most likely be looking at the mouth. And in cluster 1 on the left, what we see is that the model is paying attention to kind of a vertical artifacting. Now, obviously, this is not in itself a form of bias that I was talking about before, but it is a failure mode of the system that you can discover. And then the cluster, it's focusing a lot on bangs. You can use the same tool to look at more complex data sets like the COCO data set and find interesting co-occurrence artifacts. So things like the fact that you would mislabel a teddy bear as a bed because they were frequently on the bed. So this is a more general purpose tool because it's unsupervised to be able to discover modes of failure in the model. The ongoing challenge is that because it is unsupervised, it's hard to interpret clusters by themselves. So we've designed extra systems to be able to use any additional annotations to compare a well-performing cluster to an underperforming cluster. For example, we have this cluster here that's underperforming, and it looks like the model is paying attention to hats. So you might be tempted to say that it's hats that are causing this underperformance. But we can find what is the nearest cluster where the model is performing well, and you can see this one. It's not the hats alone, it's something more deep than that. This is ongoing work, and we actually have a demo at this conference that shows a way that has a visualization tool to be able to investigate all of these different clusters and to do comparisons between strongly performing and underperforming clusters. So this is an open, challenging problem. The right solution, it has to be a combination of techniques together with sparse annotations to help with analysis. I don't think that a fully manual approach is going to be sufficient. I think it's too expensive to be able to compute all of those annotations, to label them all, and to predefine everything. So once you have some sort of bias, whether it's manually defined or discovered, we'd like to be able to mitigate it. We'd like to be able to improve on this situation. We found that there's predictive inequity. We found that there's underperformance of the system against some modes of failure. What can we do about it? For this, we're going to use some techniques from domain adaptation. In domain adaptation, what you have access to is a large labeled source data set. This could be a manual data set like ImageNet. It could be warehouse. It could be simulated images. It's going to be somewhere where you have access to lots and lots of labels. The problem is that this data is not perfectly representative of the data that you're going to see at test time. Again, this could be because of curation bias. Maybe you had still images and you'd like to use them on frames in a video. Or maybe you'd like to train on images from your product warehouse and then recognize those products as they appear out in the world. Or you'd like to be able to use your model trained in simulation on real-world images. The hallmark of these types of techniques is that you have lots of labels in the source domain, and you have very few or even no labels in the target domain. There's visual appearance shift between the two, and we'd like to be able to, good, all right. And we'd like to be able to adapt our model for use in one scenario, for use in the target scenario. So one of the techniques that is very popular in this line of work is called domain adversarial adaptation. I'm just going to very, very briefly mention it. The joys of having lots of things open at the same time. All right, so the first thing that you do here is you train a classifier to be able to distinguish between features from the source and target data set. Intuition is that if you can distinguish them, they're far apart. And we would like them to be as aligned as possible because we're going to be training a classifier on this feature space using only source labels. So the adversarial part comes in because you'd like to be able to update the underlying representation so as to align the two distributions or make it hard to classify them. So this is a very, very popular type of approach in the domain adaptation world. The difficulty when you're using it for something like the fairness or predictive inequity across subpopulations is that it operates from a space of full invariance. You're just taking the full feature space and you want to make sure that it's invariant or renders the two domains indistinguishable. And that could be overly restrictive when you're talking about different populations rather than something like a resolution shift. And so what people saw when they use these types of techniques is that they did increase fairness, they did reduce the predictive inequity, but they did so at a cost of accuracy. So they kind of lost some distinctiveness of the feature spaces that was actually necessary for the predictive task. So our goal in this work, mitigating bias with visual transformers, was to use a targeted alignment technique that allowed you to reduce the bias in the system while also maintaining accuracy. For those that aren't familiar, the visual transformers are going to be built on top of these attention heads. And the important part here is that attention heads have these three matrices, K, Q, and V, query, key, and value. And we're going to be leveraging those in our alignment technique. The visual transformer overall is going to be taking patches of the model and then passing it through these attention heads. Once you vectorize the representation of these patches, we're going to be passing it through these attention heads that have, again, those query, key, and values. And what we found was, if you measured the average query or key the attribute that we were looking at was whether or not the person had high cheekbones. And this was the task of predicting smiling or not smiling again. What we found was that there was substantially more variation in the query than in the key or also the value, which is not being shown here. So what that means is there was this one piece of the model, this query matrix, that is asking for slightly different information across these different groups. This is a relatively small amount of the parameter space of the overall model, but we wondered, what if we just focused our alignment on just making sure that you were querying the same information from the two groups when making this task of smiling, not smiling. And so for that, we use these adversarial alignment techniques as well as an MMD alignment technique on top of the query matrices as well as the class token. and found that just by aligning those small pieces, you're able to reduce the bias in the system substantially while making modifications to a small part of the feature space so that you can retain the accuracy. So in this experiment, we again were using the celeb A data set and the task of predicting whether or not a person was smiling. After we use our debiasing technique, we can investigate and make sure that the query matrices are now aligned, as well as the keys. And what we find is that the model, though it has a very high difference in balanced accuracy, the original model had a 9-point difference between people with high and low cheekbones at predicting smiling or not smiling. After you did this type of alignment, you're able to dramatically reduce the performance difference down to 2.4, while at the same time retaining all of the standard metrics on the aggregation of the data set, so both balanced accuracy and accuracy overall. So this is a direction of study that says we'd like to be able to pool some of our techniques from other sources, but we need to be able to understand the differences in this setting. So there's some key differences when you're studying demographic bias as opposed to sensor bias or weather bias. One other really fundamental example from demographic bias is that of geographic bias. So it doesn't have to be on an individual level. It doesn't have to be a single person has some attribute. It could be on a larger scale. There were some studies in 2019 that looked at the distribution of images across the world. The top two rows, ImageNet Coco and then Open Images, show that most of the images in our data sets are coming from North America and Western Europe, whereas the world population is, of course, more distributed. And this has ramifications when you're talking about what an object is, what it looks like, what it means. Here's two examples of soap. So frequently in North America and Western Europe, a lot of the images of soap are going to be these bottles of kind of liquid soap, whereas they might look more like bar soaps or scrubs in other parts of the world. And so that can become difficult because the off-the-shelf systems are now starting to label soap here as food. We need to be able to have images that kind of represent what these concepts mean in different regions. And of course, that same study, not surprisingly, showed that the models underperformed in the regions that were underrepresented, performed best in North America and Western Europe. So we wanted to understand whether or not we could do the same thing. We could leverage some techniques from domain adaptation to help with this geographic bias. And so what we did was we used a data set that had access to different parts of the world. And we imagined training on North America and then trying to adapt our model to other regions like Asia or Africa. To do this, we had to very substantially filter or clean the Dollar Street DA and GOYFCC data set. But once we did that, we had access to data from different parts of the world. And this is actually what I'm talking about right now is going to be presented at a workshop tomorrow. So long story short, what we found is that the off-the-shelf systems, all the different methods that we tried, didn't work at this task. So you can say, hey, you have the North America data, you have the data from Asia. Should we be able to use these off-the-shelf techniques to reduce the bias, to use adaptation? But it doesn't necessarily work exactly like that. And part of the reasons why involved a lot of investigation. And really, it boiled down to two key challenges in this geographic bias or geographic domain adaptation setting that don't always exist in some of the canonical adaptation settings. So one of them is that of subpopulation shift. So if we think back to that soap example, there are actually images of bars of soap in North America. They just don't dominate. And so the problem is that if you just train a model across the subpopulation distribution that exists in one continent, it doesn't necessarily generalize the other. And if you use marginal statistical alignment techniques across these two different distributions that have different subpopulations, it's not going to work out of the box. So you might need to have techniques that look for similar images across different regions, look for bars of soap as they exist in the different regions, and can help to use that to perform alignment. And the other one is context shift. So here's an example. Toothbrushes are frequently shown in bathroom settings in North America, whereas in other parts of the world, in some parts of Africa, they store toothbrushes in the ceiling. So as long as you are leveraging a lot of the context to make your decisions, which we know to be the case, you're going to suffer in these circumstances. And it's going to be really challenging to be able to do an unsupervised alignment technique here. So overall, these challenges that I just articulated, they exist in the object recognition world, but they also exist and probably are exacerbated in other tasks like detection and segmentation. In object recognition, you have appearance, context, representation or underrepresentation as issues. Extra factors in detection and segmentation are things like having co-occurrence with other objects. The size of the objects may differ. The time of day, I don't have time to go into this particular example right now, but we've found that there's actually a lot of bias in terms of the time of day that different geographic regions are captured in, and so on. So overall, today I've talked about lots and lots of different ways in which our data sets can influence the models and the performance of the models that we train. Geographic bias is a wide open area of study that comes with all kinds of complex, challenging tasks. Demographic bias is one that now has a rich history, but is still really needs a lot more work to be able to solve. But bias can exist in many other different ways that we haven't fully even explored yet. So of course, we've looked at things like things like having different sensors or different weather patterns. But there's all types of curation bias in the data sets that we collect, where we collect them, that informs things like context, that informs things like co-occurrence. And all of these subtle details are being learned by the models. So if we would like to be able to solve this problem long-term, I would advocate for having more systems that can automatically, in the loop, be able to identify, discover forms of bias, forms of model failures, going beyond aggregate measures of performance of a system, and being able to more accurately tell people what are ways in which a system will fail. So with that, I'd want to thank my lab members who have done all this work. There are all kinds of citations in the slides that point to their names. Hopefully some of them are here and we'll get a chance to talk about some of this work later in the conference. And I'll take any questions if there are any.
Thanks so much for the great talk. I found the idea of using the collaborative clustering to find the fully conforming clusters really interesting. But it seems to me that, from what I understood, you need some level of manual inspection of the grad time maps to see like if they're performing fully. Have you thought about any ways that that stage of the pipeline could also be automated, or free automation in that stage?
Yeah, so I didn't have time to go into all the details, but there is an automated part. So there are thousands of clusters. There's an automated part to be able to rank and sort them and present just a small subset to people. The problem is that at least at this point, we only have manual inspection or some of those visualization tools to help with the manual inspection to be able to understand and make a decision about those top clusters, whether or not you would like to do something about them, basically.
Okay, thank you.
Hi, thanks for the great talk. Also related to the clustering. So I didn't get the details of that part. So what representation do you do with the clustering? Is there like an implicit assumption that the representation needs to cover the bias that you actually have?
Yeah, so In that work, we were investigating bias in a model that was already trained. So we're using the feature space of the model itself. We tried using like off-the-shelf features from ImageNet or other different places as well to help us to explain the bias that was discovered, but it was important to us to use the model that was trained itself because we were using the accuracy of the model on those clusters as a measure of the model's failure or underperformance.
So that means that if the model doesn't present a certain feature at all, you wouldn't be able to find it in a way that that feature is actually underlying bias.
So if the model, the assumption is that you're using this model for your predictive tasks. So if the model doesn't have a feature, but it still gets 100%, that should be fine. The assumption that I think is what you're getting at is that we assume you have a test set of images. And if the test set doesn't have representation over all factors that you would like to be able to measure, then you're kind of out of luck.
Thank you.
Yeah.
Thank you for the great talk. Actually, we explored space classes for just 2 years, and we have noticed bias for the feature space explained here, but also help us see some related errors. And what I was wondering about is, do you have visualization tools somewhere to have like the data of the source of the data? Because what we saw sometimes the related bias comes from tuning indicators. For example, if you only have one part of the wall, it will definitely tend to misclassify specific.
Yeah, absolutely. You can integrate, if you have access to labels, you can integrate them. We have an example of that in the VizCut tool. For the celeb A dataset, there are annotations available for some attributes. And so you can use those to help you to perform, to have like an auxiliary metadata feature space that you can use to look at most similar clusters in an attribute space. And that can be really helpful. Again, it's limited because you have to have those annotations, but if you have them, might as well use them. All right, coffee break. Is it a coffee? 5 minutes? All right, it sounds like we'll be back in 5 minutes. Thanks, everyone.
So there's a coffee break. Oh, sorry. There's a coffee break, and we'll start in five minutes.
Hi, Tommaso. Can you share your screen and just so we can check that?
Can you hear me?
Yes, we do. We'll get
Okay.
started.
Can I start sharing screen or should I wait?
Yes, please. Please share your screen.
Sorry?
Please do share your screen. Yes.
Thank you. Okay, does it work?
Yeah, we see your slides.
Okay.
So everyone, let's get started again. So it's my great pleasure to introduce Tommaso Poggio, who will give the next talk. Tommaso, he's a real polymath and has worked in many different fields. He's made big contributions to neuroscience, to machine learning, to computer vision, understanding human vision, understanding fly vision. I mean, it's just incredible all the things that he has done. Sorry, I guess can you hear me now?
Well, thank you.
Okay, well, I think let me before you can hear, let's welcome Tommaso. Thanks so much, everyone, for coming.
Thank you. Should I start?
Yeah.
Thank you. Okay, so this would be a bit different as a talk, but I think that's a background also for a symposium like the one of today. These are some thoughts on machine learning, especially theory, why it works, and let me move on. Let me see if I can get this going on the next slide, showing that there are a number of very good network architecture, especially in the last 3 or 4 years with the advent of transformers, in addition, of course, to the existing CNN, convolutional networks, and other architectures like perceivers and MLP mixers and so on. And so a question is really why do all this architecture works? And let us not forget that an architecture that we also to understand eventually is the brain, the human brain. And so why do all this architecture work as well as they do? And the equivalent way to ask this question is whether there are common principles among these different architectures. And so I'll try to answer this question, and I'll try to answer by looking at 3 different ways, in 3 different ways to machine learning, especially deep learning, and one is approximation theory, another one is machine learning, generalization, and the third is optimization. But so let me give you first some background, probably unnecessary, but will be very quick. I'm mostly going to speak about supervised learning, multi-layer networks, in which you have an input, you have an output, and a basic operation that is repeated across units in the same layer, and then across layers is each unit is receiving a weighted sum of inputs and performs a very simple operation, the RLU operation, this max between 0 and the input, and then that's the activation of the unit that is passed on to other units. And the way you find the weights is by gradient descent techniques, in which you minimize a cost functional. So how much is the discrepancy between the prediction of the network and the true output given, because you have a set of input-output pairs, xi, yi, that I called zi. And so I'm trying to find weights that minimize this loss over the whole set of capital N examples. And one way to do this is to look, to do gradient descent on the loss function, the sum over I of the losses for each of the training examples. And one version of it is stochastic gradient descent, in which instead of using the whole training set for each iteration, I'm using a randomly chosen mini batch from the training set. Okay, now there are a few things that are known in the meantime about the loss landscape. If you take the loss function to be the square, so the square loss, then we know that for over-parameterized networks in which you have a number of parameters, W, which is much larger than the number of training example N, this loss function has degenerate minima, so many minima with zero loss, and this is they are degenerate in the sense that they have a dimensionality which is W minus N, and furthermore, under some additional assumptions, this minima can be thought as being connected in a large zero loss valley. Okay, that's the first thing. To give you an intuition what this means, here is a simple experiment that you have done years ago, in which we took a deep network used to for classification in CIFAR, and we replaced every RLU unit in the network with a univariate polynomial approximation of the RLU function. In the figure on the left, it's, I think, a polynomial of degree 8. You see some oscillations there, pretty close to the RLU. And when we trained and tested the network, we found results that were very similar, indistinguishable from the case with RLU. So seems an approximation works well. And what that tells us is this intuition that leads to using standard tools in algebraic geometry, because if you replace the RLU with a univariate polynomial, if you think about what the network now is, it's now computing a high degree polynomial in many input variables and in the weights, and finding zero loss minima means finding zero of the polynomial, which is f of xi minus yi for each I, for all I. And so you have n equations in W unknowns with W much larger than n for a high degree polynomial. And now you can use Bézout theorem there, which is an extension of the basic theorem of linear algebra, which tells you that like in the case for linear equations, in this case, you have many solutions and they are degenerate. And they are typically degenerate with degeneracy, which is W minus N. Now, that's the first important point. That's true. The second one is just a comment, is that if you look for the zero of the gradients, which of course include the minimizer of the loss, but it's more than that. In this case, you're writing this equation in the gradient, zero of the gradients, the second line in the slide. And in this case, you have W unknowns as before, the weights, but you have W equations, as many as the W. And so typically you expect the zeros of the gradient, which are many more than the zero of the loss, to be less degenerate. This is just a qualitative statement, does not say much. This would require...
Excuse me, Tommaso, we didn't see your slides moving. We still see your second page.
Let's see, do you see a different slide?
No.
Oh, what's going on? Do you see my screen?
Yes.
Okay, let me try again. First slide.
Right.
This is second slide.
No, it didn't go through.
No.
Maybe you can use this format.
What can I, let me see. Let me see, just 1 second. I think, I don't know why, but let me try to get out, stop sharing. Let me try again. Can you see this one changing?
Yes.
And can you see this changing?
No.
Okay. Don't know what's going on, but let me use this one.
Sure, thanks.
Okay, so I started with this. I mentioned that I want to look at common principles. I went through what we are doing and this basic topological results on the generate global minima for over-parameterized RLU networks by Yaim Cooper. The fact that we can replace each RLU by a univariate polynomial approximation, then the deep networks is a polynomial of very high degree, many variables. We can use Bézout theorem that says that the zero of the loss are degenerate because we have an equation in W unknowns. And then there is this comment, just an intuition, that if we are looking for zero of the gradients, which are more than the absolute minima, the zero loss minimizer, because it includes saddle point and local minima, I would expect these zeros to be less degenerate than the other ones, because in this case, we have many more equations in the same number of unknowns. Okay. Furthermore, there is this fact, again, that if I consider stochastic gradient descent, and suppose I add a derivative of Brownian motion, then then what I have is a so-called Langevin equation, a stochastic differential equation, and the solution, the probability which solves this asymptotically for time going to infinity, is a probability distribution that is the Boltzmann distribution, is e to the minus the loss divided by a parameter t, which is the power in the white noise. And what does that mean? That means that if I look at what happens for such a stochastic differential equation, I can see that when I have, say 2 dimensions for the parameters, then if I have a loss profile, which is like here under potential function, which I say 2 minima equal depth, equally deep, but one is degenerate and the other one is not, then this Boltzmann distribution will see much more probability to ending up in this diffusion process in the degenerate minimum. It has a much larger basin of attraction. The interesting point is that there is a kind of concentration of probability, because by increasing the dimensionality of the parameter space, so increasing the relative degeneracy of one minimum relative to the other, I have a situation in which basically I never end up in the non-degenerate minimum and always end up in the highly degenerate minimum. And this becomes even more so with high dimensionality. And let's remind you that the dimensionality of the number of parameters with respect to and the number of training data is usually quite large. So this degeneracy is quite large, and that means that with high probability stochastic gradient descent will end up on the degenerate minima, which happen to be the zero minimizer, according to the argument before. So just to give you an idea of the optimization part and the landscape and some general properties. So now let me go to what I wanted to tell you about common principle about this different learning architecture. And let me start with approximation theory, which is usually not considered very much, but I think it gives you the key insight here. And here, I remind you there are shallow networks like kernel machines, which has only one layer of trainable weights, the C here. And then there are architecture like convolutional networks that here I represent in a very simplified, cartoonish picture, like essentially binary tree, a network with this structure of a binary tree, and the red dots here will be neurons, that each one of which gets, in this example, 2 inputs. This 2 is the equivalent of a kernel in CNNs. Okay, so now we know, and this is known since the 80s, is part of the reason why until 10 or 15 years ago, people focused on one-layer networks. This theorem says that from the point of view of representing, approximating continuous function on a compact domain, both shallow, say 2 hidden layers of weights, and deep networks with many more layers are equivalent, and they are universal approximators. They can approximate a continuous function, arbitrary one. So there is no difference between shallow and deep network from this point of view. However, in both cases, we have to deal with a real problem, which is that both shallow and deep networks can work well, but they have this curse of dimensionality. The number of parameters, it's an upper bound, but they may require, for an approximation within an error epsilon, depends on the dimensionality of the function d, in this case 8, exponentially. So for instance, epsilon is 10%, d is 10, I have 10 to the 10 parameters, which is not a small number. And if d instead of 10 is say 1,000, like the pixels in the image of CIFAR, then I have 10 to the 1,000, which is a real big number. So the curse of dimensionality is a real problem. And you can think of it because in the way that the function of 10 variables corresponds, if you want to represent it in, say, computer, represent equivalent to the 10-dimensional table. And if I have, I don't know, 10 partitions per dimension, then again, I have 10 to the 10. Okay, so there are a couple of ways to avoid this curse or to reduce this curse of dimensionality. One of them is smoothness, is the classical one, assuming that your target function, nothing about the networks, but the target function, that the function you're going to learn, representing the task you want to learn, this function is very smooth. But another way, it's something we came up a few years ago with Hrusikesh Maskar and a few others, is that the function is compositional. In other words, it's the function of functions. And each of these constituent functions has a low dimensionality. In this example, 2, for instance, think of an underlying function you want to learn. That's not a network again, it's just the underlying function. And this is a function graph. And you assume this function graph to be a binary tree. So each node here is a constituent function, a G, and it's a function of 2 variables. Now, by making this binary T as deep as I want, I can have overall function being as high dimensional as I want. So the dimensional function can be as large as I want, but the dimensionality of the constituent function is always 2. And now larger than 2. And in this case, we can prove that if you approximate such a function with a deep networks, then the number of parameters you need does not depend exponentially in the dimension, like in the generic function case, but it's actually linear in the dimensionality. And as a small note, but interesting note, convolutional network are a special case of the network you'd like to use to approximate this kind of compositional functions. And the key property of this convolution of this underlying function that makes them avoid the curse of dimensionality during approximation is not weight sharing, although this helps, but is the fact that the constituent function have low dimensionality. Okay, so now this can be extended to arbitrary graphs, directed acyclic graphs. So the key part for an underlying function, a task you want to learn to be approximated by a deep network without curse of dimensionality, is that the constituent function of the underlying function have an upper bound on their dimensionality. And that's the key part. And so this repeated says, so you're assuming a sparse composition of the target function. This is an assumption about the world. It's not about the networks. It's about really the task I want to learn. And there are some general arguments that have been developed with Seth Lloyd that essentially say that functions that are efficiently computable by a Turing machine have to be compositional. That's a separate one. I will not speak about it here. Just remember that a lot of systems that we are dealing with in real life are compositional, recurrent system, differential equations, and so on. Let me say simply that when the target function is sparse, is compositional, then you can avoid the curse of dimensionality. And it turns out that this is good for approximation theory, but this looks to be also the answer for generalization. There is a recent paper, a set of papers actually by different German statisticians in the Annals of Statistics, showing that you can approximate and generalize, assuming that the underlying function is the underlying function you want to learn is compositionally sparse, and so that's very good. These papers assume underparameterization in order to use VC bounds, but I think you can get around it. This is a conjecture, and so to justify this conjecture, I can show you that if you take a deep network, you assume binary classification, normalization of the weight, over parameterization, you end up with a set of equations, and you can consider here the function represented by the network as a function f of x, which is the function given to you by a network with normalized weight matrices, which is the weight matrices Frobenius norm 1, time rho, which is the product of the Frobenius norm of the different weight matrices. This is because of the homogeneity property of the RLE. And so using this, we can use very simple generalization bounds that essentially say that when you are over parameterized and therefore interpolate, and therefore your empirical error is 0, your expected error is bounded by rho divided by the square root of n, where n is the training example, and rho is the product of Frobenius norm of the various layers. And it turns out that although this bound is still loose, as you can see in the middle, you see the test error for different training sets in CIFAR, binary classification, and on the right you see that the bound, this is still loose, this bound is vacuous, but is now within reach of being a reasonable bound. And like all other bounds, for its a VC dimension bound, several millions, 10 to the 8 or so terms, so very, very vacuous bound. So there is a real hope that bounds based not on the number of parameters like the VC bounds, but on the norm of the weight matrices can be used in the approach of that we've seen of Sophie Langer and Schmidt-Heber and so on. And those, together with their result, provide both approximation and generalization guarantees. Now, I see that I'm almost over with time. I'm just mentioning that the real question that remains is about optimization. All these papers assume that empirical risk minimization works, can find optimum or minimizer that are close to it. Empirically, this seems true for, at least for convolutional networks, because you typically find 0 minimizer. But this requires still work, especially because what I said about the norm, I'm assuming regularization terms like a weight decay, and one needs to show that you can optimize and under which condition, not only the empirical risk, but also finding the minimum of the norm. Let me skip this, but this essentially assumes that possibly for convolutional network, but possibly not for dense networks, stochastic gradient descent will find both the minimum of the loss and the minimum with minimum norm. This is similar to the linear case in which we know that gradient descent and stochastic gradient descent find in the over-parameterized linear case, find the minimum norm solution, essentially the pseudo-inverse. So not only the one of the inverses, but the one with minimum norm. So let me finish by this. This is what I just said about the linear case. In the RLU case, multi-layer, we have similar results in some unpublished work. There is convergence to solution to the minimum row, although with a regularizer. And so, in my view, this would be a potential explanation for why deep networks, including transformer, I did not have time to explain this, but including transformers, why they work is because the underlying function that they try to approximate as is compositional and has relatively low dimensionality of the constituent function. I can explain more if there is time in the question, but in the meantime, thank you.
Any questions in the audience, in-person audience? So Carl, Mihar.
Sorry.
Composition of functions in optimal manner to apply this in practice.
Sorry, could you repeat we were on mute. So,
so the hierarchy of structure is clearly important for generalization, as indicated by it. But I'm curious on your thoughts for how we define this hierarchy or this composition of functions in an optimal manner. Where do we apply this in practice? So are there any rules of thumb for applying this to more general problems, especially
Sure. Do you mind repeating the question? The connection was very bad.
You want to ask the question here? You're able to hear me, right?
Okay. Now, yes.
Yes, got it. So my question is about how we apply this in practice. If we want to train a model to use this hierarchical structure, how do we define this hierarchy, and how do we actually train this on a generalized problem?
Yes. So in the case of convolutional networks, you're basically assuming a graph of the unknown function by having a convolutional architecture matched to it. You know, people essentially historically just tried until something worked. That worked. It makes sense for images and text to have this, you know, a kind of compositionality property of the network. And anyway, I'm basically assuming this, that the function graph represented in architecture is also the function graph of the underlying function. Now, for transformer, the story is a bit different, and I did not have time to explain, but the idea is that for certain compositional functions, you can find the variables that are important for all constituent functions by considering just the linear terms of the function. This assumes some specific structure in the function. It's very similar to what Guy Breisler and co-worker in a paper a year ago called staircase functions, in the case of Boolean functions. And in that case, they can prove that the optimization problem is easy, even if you don't know the underlying graph structure. So you can find it during optimization. But as I said, this assumes, again, a specific compositional structure of the underlying function. So that is a conjecture that this is what is going on with transformers. And I may be wrong, but if the function has a specific compositional structure, so it's more than what I said before, is that the linear variables appears in all higher order terms, but the linear variables are a small subset of all the variables. In that case, optimization become easier. You can basically find the graph of the function even if you don't know it.
Great, thanks so much. I think we have to move on to the next section. Let's give Pastor one more round of applause.
Thank you.
Okay, set up. Yes. And then and you can share desktop too.
Yeah, this one.
There you go.
All right, is it working? Okay, cool.
Okay, so please welcome ZQ Lin, PhD student at CMU. He is the lead author of the CLEAR benchmark.
Yes.
And he's going to basically host the challenge and present some kind of overview of everything.
Thanks, Carl, for the introduction. And hi, everyone. This is Zhiqiu from CMU Argo AI Center. In this talk, we'll present our recent work, the CLEAR benchmark for continual learning with real-world imagery, as well as the first competition event based on this novel benchmark. So let's first start with the motivation. Visual perception systems in open worlds needs to cope with constantly changing environments, where the data comes in dynamic streaming fashions. For example, self-driving cars must be able to perform visual recognitions and their distribution shifts over time, such as when they're deploying at different cities or when they are seeing brand new car models. However, most of the successes in computer vision in the last 10 years were achieved on static benchmarks, such as ImageNet for visual recognition and MS-COCO for object detection. These datasets did not change ever since they're released. Therefore, a lot of the research efforts have been devoted to the field of continual or lifelong learning, and researchers propose various benchmarks simulating a stream of data from the changing distributions. The classical continual or lifelong learning benchmarks usually consist of a non-ID data stream split into multiple buckets. Each bucket of data forms a new learning task that is different from the previous ones. A continual or lifelong learning algorithm is expected to learn with the streaming data and perform well on the already seen tasks and generalize the future unseen ones. However, classical continual vision benchmarks usually create such an artificial non-ID data stream out of a static benchmark. For example, split CFAR breaks the CFAR dataset down to disjoint sets of labels, and permuted MNIST randomly shuffles the pixels to come up with novel tasks. These benchmarks are curated in order to highlight the phenomenon of catastrophic forgetting, that is, when the neural network forgets about the previous task after learning on the new ones. Therefore, we can see the distribution shifts of all those dynamic synthetic continual benchmarks are somehow too extreme, which do not generalize to practical applications in real world. In reality, things change smoothly, such as novel computer models with fancier look and more fashionable closes and backs. This motivates us to propose CLEAR, a continual benchmark with natural distribution shifts, collected from internet imagery spanning a real-world decade. And now I will hand over to Siqi to introduce this novel benchmark.
Can you hear me now?
Yes.
Sorry, give me 1 minute. Could you talk, Siqi?
Yeah. Okay, I will start now. So yeah, thanks, Zhiqiu. Yeah, hi, I'm Siqi. I will describe how we design and collect CLEAR. Yeah, the first continual learning benchmark for open world vision. So CVPR 10 and CVPR 100 are well-known image classification datasets, originally released in 2009, and they motivated a lot of progresses in vision and learning community. So why don't we create a benchmark at a similar scale, but closer to the real-world streaming setting for the continual learning community? To fill in this gap, we started to collect CLEAR 10 and CLEAR 100, each with 10 and 100 classes over a decade. So in the next few slides, I will show first how we designed CLEAR to capture a natural distribution shift of internet images over a decade. And second, how we efficiently and faithfully perform annotation with million-scale image collections. And finally, what are some valuable assets that comes with CLEAR for future continual research, such as unlabeled data, metadata, and instruction sets? To capture a long-ranged natural distribution shift, we start from the public Flickr YFCC 100M dataset with internet imagery spanning over a decade from 2004 to 2014. We use image timestamps to recreate a temporal stream of images. Then we split the image stream into 11 equal-sized buckets, each spanning about a year. The zeros bucket is reserved for unsupervised pre-training, and we will annotate a high-quality label subset for each of the next 10 buckets. To create a visual recognition dataset, we select some dynamic visual concepts that might experience distribution shifts over time as class labels. Besides, we have a diverse set of visual concepts such as vehicles, accessories, places, artworks, and so on. And after selecting the classes, the next challenge is how to actually annotate the images. Since YFCC is a million-scale dataset, it would be very expensive to go through all the images. Instead, we propose a semi-automated dataset curation approach based on the popular visual linguistic model CLIP in order to retrieve images from relevant classes using carefully engineered textual prompts. With CLIP, we efficiently retrieve the top 1% of the images containing the visual concept of interest, saving a lot of efforts to manually label the millions of Flickr images. So next, for you to get a better sense of how CLEAR looks like, I'm going to show you some examples. Computers at the first row evolves from classic ThinkPads and bulky desktops to detachable Microsoft Surface and recent MacBook models. Watches develops from old school analog watches to digital and smart watches. In 2004, the popular video games are in 2D with pixel art style, and owing to the advancement in computer graphics technology, we start to have video games with fancier 3D effects. In short, in CLEAR, we observe natural temporal evolution in those selected visual concepts. And finally, we perform dedicated manual verification of the CLIP-generated labels with both crowdsourced and professional labeling service to make sure a high annotation accuracy. So here is the statistics of CLEAR. We released to the public 10 buckets of labeled training set and test sets. And besides labeled data, each bucket also comes with 3.6 million unlabeled images from YFCC temporal stream. At last, I want to mention that CLEAR also comes with valuable assets that previous benchmarks did not have. These assets could be helpful for future research on continual learning. First, CLEAR comes with abundant labeled images with timestamp that can be helpful for continual unsupervised learning, which is a relatively underexplored area of research. And secondly, the images in CLEAR also comes with metadata such as time, location, social media hashtag, and text description that can be helpful for multimodal learning. And finally, to improve the data transparency, we are planning to publish our dataset curation procedure with around 200 pages of instruction set and corner cases. And now I will hand over to Zhiqiu to talk about some baseline experiments on CLEAR.
Okay, thanks, Siqi. So as we can see, the CLEAR benchmark simulates a typical real-world continual learning scenario. And to see why this is a big deal, let's first look at some baseline results training a state-of-the-art RASNet model on CLEAR 100. So when the first bucket of data comes, as shown at the top left corner, training a RASNet does achieve reasonable performance of 42% when evaluating on the corresponding task set. However, as time progresses, new buckets of data arrive, and we need to evaluate our model on the more recent task sets and their distribution shifts. So suppose we don't do continual learning, and we just keep deploying the same model to avoid the cost of retraining. then we could see that the model performance unfortunately gradually decreases over time. As shown in the first row of the matrix, the performance drops by more than 5% from the first to the last 10th bucket due to the natural distribution shifts that happen over the past decade. To improve the performance, we could adapt a smarter continual learning strategy, which is to accumulate the data and fine-tune the model every time a new bucket of data come in. So this continual fine-tuning strategy boosts the average scores on the task sets by around 20%. And this is also obvious from the diagonal entries whose scores are much better than the first row, where we only train the model for once without continual fine-tuning. And in addition, if you look at this complete accuracy matrix, where each row from top to bottom represents a new incoming bucket of data, and each column from left to right represents the index of the text bucket, it is obvious that continual learning not only helps with the current incoming buckets, but also uniformly improves performances on both the previously seen and future unseen bucket. So in order to quantify this improvement, we propose several metrics to summarize this huge 10 by 10 matrix. The first metric, in-domain accuracy, is the average scores of the diagonal entries in red, and it measures performance on the current incoming buckets while assuming the training and past distributions are locally the same. So this simple metric is in fact a popular one being used in prior continual learning literature. However, we suspect that in real world, we always evaluate a model we train today at some points in near future, because data annotation, model training, and model deployment could all take considerable amount of time in practice. Therefore, to simulate this time delay between data arrival and model deployment, we propose a second metric, next domain accuracy, to evaluate this model performance on the immediate future bucket, which can be represented by the superdiagonal entries as shown in green. We can see that the next domain accuracy is on average 3% lower than the in-domain accuracy on clear 100. This experiment suggests that this one of the most popular metric being used in prior continual learning research might artificially inflate the real-world performance of an actual continual learning system. And finally, we also adopt two other popular metrics from prior literature. So backward transfer is the average of lower triangular part of the matrix in yellow, and it represents the performance on the buckets the model has already seen. It is also the main focus of all the previous continual learning research because it measures the network's ability to avoid forgetting on previous tasks. However, we observed that in clear benchmark, it is a much more challenging and perhaps more interesting task to improve the forward transfer, or the upper triangular part of the matrix in blue, because they have much lower scores in comparison. But this requires the model to learn with limited historical data and be robust against future distribution shifts, which could be hard to predict. In fact, in this year's competition, we already have teams that utilize domain generalization and meta-learning techniques trying to improve this generalization performance. And for Clear 10, the lessons we learned are the same, even though all the scores are on average 15% higher, because Clear 10 is perhaps obviously an easier task. And besides a naive fine-tuning strategy, we also want to see whether the progresses people achieved within the past decades of research in continual learning can be translated to Clear. And for this purpose, we integrated Clear benchmark into one of the most popular continual learning library, Avalanche, and we used their open source implementation of classical algorithms, such as AGEN, learning without forgetting, synaptic intelligence, and so on to test on Clear. And while these algorithms are nearly saturated on prior benchmarks, focusing on forgetting issues, we can see that from this table, their performance on Clear are only slightly better or about the same as our naive fine-tuning strategies, as shown in the top row. Also, their generalization performance, as represented by next domain accuracy and forward transfer, are still inferior, suggesting there could be a lot of room for improvement. And similar trends holds for Clear 10 as well. And finally, I also want to advertise for the Avalanche library, as Clear is now officially part of their API. So if you're interested in Clear after this workshop, you can actually download it on Avalanche with one line of code and start playing around. And I will hand over to Shihao now to introduce the first Clear workshop challenge.
Can you hear me?
Yes, yes.
Okay. Yeah, so now we can you go to the next slide? Hi, ZQ. Can you go to the next slide?
This one or the previous?
Oh, the previous, sorry. I was looking at the YouTube video. I didn't update. Anyway, all right. Yeah. Now we'd love to introduce our challenge. The challenge features the two datasets we have introduced above, Clear 10 and Clear 100. The challenge is an opportunity for researchers and machine learning folks to experiment and explore continual learning strategies on this novel benchmark. Through the challenge, we also hope more people can come up with more innovative ideas and new directions in continual learning by completing on this dataset directly. A brief overview of our challenge. It contains two subtasks, Clear 10 and Clear 100. The final score of each team is based on a weighted average of each score they obtain in Clear 10 and Clear 100. Participants have to train their models from scratch, which means they're not allowed to use any pre-trained models on their datasets, and their training time is strictly controlled under limited compute resources, which is 12 hours per time bucket. Their submissions are evaluated against an holdout test set on our server, which will be released after the workshop ends. In all, the challenge was very successful. It has lasted 39 days, and we are surprised to have as many as 79 participants and 15 teams to sign up in such a short amount of time. And most importantly, there are more than 500 submissions to the challenge during this period. In addition, our participants are coming from more than 17 organizations and universities, as well as 21 different countries and regions. Here's the breakdown. We have people from universities like Tsinghua, Carnegie Mellon, also National Institute of Science and Technology, IIT, and so on. We also have people from companies such as Tencent, YouTube Lab, AI Prime, BOE, and so on. In terms of countries and regions, about 70% of participants are from China, India, the United States, Hong Kong, Japan, and Korea. We are very glad to have such a diverse composition of participation in our challenge. And indeed, the way that we interacted with people from different backgrounds, different experience, has been reshaping our vision of the Clear benchmark. Now comes to the leaderboard of Clear 10 first. The screenshot shows the top entries on the actual leaderboard. We can see the top 4 teams have achieved a huge jump of more than 20% in accuracy compared to our baseline. And even more exciting, when it comes to Clear 100, teams have almost double the accuracy. All of the top 4 teams will share how they achieved such good results in a minute. However, you might notice that there is still a gap between the backward transfer and the forward transfer for each team, which is a strong signal that generalization into the future is still an unsolved problem compared to forgetting. This matches the experience we have went over in previous slides. Overall, we have seen a lot of smart strategies used by participants throughout the challenge. We have summarized a portion of them that seems promising and is definitely interesting for more investigation in the future. You will hear from them sharing these strategies in more details in a minute. For example, teams that use state-of-the-art model backbones like ResNet 15D or ECA ResNet 50D tend to increase overall accuracy. Some teams also use smarter sampling strategy that is able to generalize better to the future buckets. Also, teams that use better augmentation such as auto-aug and cut mix have significantly increased their scores. A couple of them also experiment innovative training laws such as adaptive sharpness aware minimization in order to deal with the domain transfer problem, which makes their models better generalized to the future and gives higher forward transfer accuracy. Now we'll announce the winners of the challenges. The first place goes to the team from Tencent YouTube Lab. The team members are Xinkai Guo, Bo Ke, Su Nanhe, and Rui Zhiqiao. They achieved a very impressive weighted score above 90% with their bucket-aware sampling strategy. The second place goes to the team from a startup based in Shanghai, AI Prime. The team members are Jia Wei Dong, Meng Wen Du, and Shuo Wang. They have achieved almost the same performance as the first place. They did a comprehensive study on sampling, state-of-the-art model architecture, and data augmentation strategies. The third place goes to Xiao Juntang, Pan Zhong, Ting Ting Wang, and Yu Zhou Pen from BOE Technology Group. They used adaptive laws for better generalization. The fourth place goes to Ge Liu, a graduate student from Shanghai Jiaotong University. His supervised contrastive feature representation has made his model stand out and achieve a very high weighted score of 86% compared to the rest. Finally, we'd love to award the Innovation Prize to the team from Austin National Institute of Science and Technology. They are So-Long Kim, Jin Yuk Lim, and Song Wan Yong. We admire their innovative exploration in domain generalization and meta-learning on the CLEAR benchmark. Now let's start with the fourth place. Unfortunately, Ge Liu is in China right now, so he has recorded a video for us, while the second and third place will give a live talk right after this. Let's now hear about Ge Liu's novel continued learning solution based on supervised contrastive learning.
Let's begin to introduce my solution. This challenge follows the cumulative learning setting. It allows reusing the previous training data. However, it still limits the training cost. So I adopt a balanced sampling strategy, particularly in each training iteration. The equal bench size data are sampled from the previous and the current data loaders. Second, I would like to introduce the model structure. As it is a classification task, the conventional approach is training a deep CNN model by the cross-entropy loss. Here, I consider two modifications. First, to improve the feature representation, I include a bilinear pooling layer at the end of the general use CNN backbone. As we can see from the detailed structure of the bilinear pooling layer, it mainly includes two parallel convolutional layers and followed by product and global average pooling operations. Particularly, the bilinear pooling was widely used in the background classification task because it can capture more local features that may be useful for the recognition problem. And the second modification is replacing the original linear classification layer with a cosine classifier. To be specific, the H-weight vector in the cosine classifier can be regarded as a class prototypes, and the logits was the prediction or calculated by the cosine similarity. Further, I would like to introduce the loss function to train the classification model. My motivation is that imposing model consistency towards input variation can benefit the model generalization. To achieve the objective, I use the three loss components combined with the classification loss. They are self-contrastive loss, cross-contrastive loss, and the prediction consistency loss. And the two contrastive loss are inspired and modified from supervised contrastive learning. And concretely, the self-contrastive loss aims to optimize the instance invariance from the two augmented views. And the cross-contrastive loss aims at imposing class invariance at the feature level. Finally, the prediction consistency loss also aims to impose instance invariance, but at the logit level. This loss is also a cross-entropy loss between the two predictions of the augmented pairs. To validate the effect of each component in the solution, I conducted a detailed ablation study. I first validated the improved classification model. As we can see from the table, only using the cosine classifier can lead to about 2 points performance gain. Further directly ending the bilinear pooling results in slightly performance degradation. However, when combining strong data augmentation that is used in the contrastive learning, the bilinear pooling can improve the accuracy by 1 point. I further validate the effectiveness of the trailing loss. First, when only ending one of the three proposed consistency loss, the result can be improved by about 2 points compared to the baseline. Combining all loss components can achieve the best average accuracy. We can also observe that combining two contrastive loss achieves the better results in next domain accuracy and the forward transfer. It indicates that the contrastive loss is helpful to improve the model generalization. Finally, I report the results on the online data in the challenge. I also use the deep ResNet as a backbone. For example, on the clear 10 dataset, results on the ResNet 13.4 is better than ResNet 18. In summary, the proposed method can improve continuous learning on clear benchmark. I also consider that improving model generalization towards unseen domains is very important for continuous learning. And the sampling strategy matters, especially when computational cost is limited. Besides, conventional image classification tricks, including data augmentation and deep models, may be also helpful to improve the continuous learning. Thanks for your watching.
Okay. So, hello. My name is Jashi. I'm currently a master's student for Carnegie Mellon University Robotics Institute, and I'll continue the presentation. So now let's welcome the third place from the BOE technology group to share their solution. They have used adaptive loss for better generalization. Welcome.
Hi, can you see my screen? Can you hear my voice?
We can hear you. Cannot see the screen.
We should stop sharing.
Yeah,
I'm gonna share my screen here. I guess now you can see it, right?
Give me one second.
Yes, I can see your screen. At least on Zoom.
Yes, on Zoom.
Okay, so let's. Is it good now?
Yeah.
All right, cool. Hi everyone. I'm sorry.
Sorry.
Give us 1 second.
Oh, okay.
I think you're ready to go.
Okay, cool. Hi everyone. This is BOE AI team from China, and nice to meet you. So for this challenging task, we started from the data preparation. To deal with the catastrophic forgetting, it's necessary to properly utilize the old knowledge for each task. That is, for the task 0, we train our model based on the 2004 data sets with randomly initialized weights. For the later tasks, let's say task T, we use the weights of the previous task T-1 as the pre-trained model. Here, the training data set is composed of two parts. The first part is the new knowledge in current year, and the others are the old knowledges in previous year data set, half by half. And that's how we get our training data set in each task. And then we implemented the data augmentation to prevent the overfitting. Besides the commonly used methods such as random resize corp, flip, and color jitter, we apply both the interclass and interclass cut mix to make the data more complicated. As for the model architecture, we select the rank expansion network as our backbone that can eliminate the representational bottleneck. It is maintained that the feature embedding of a convolutional layer can sufficiently represent the categorical information only if the input of this layer has bigger dimension compared to its output, which is so-called representational bottleneck. RexNet can efficiently solve this problem. As for the learning rate scheduler, for the first several tasks, we use the cosine annealing learning rate to help faster reach the global optima. And then when the model has the ability to do good feature embedding, we switch the learning rate to step learning rate to expect faster convergence. And here comes the most important part. So to improve the model generalization, the model generalization of the model, we implemented the adaptive sharpness aware minimization to simultaneously minimizing the loss value and the loss sharpness. So it's functioned by seeking parameters that lie in neighborhoods having uniformly low loss value rather than the parameters that only themselves have low loss value. So as shown in this figure, can you see my cursor? Yeah, so as shown in this figure, the sharpened parameters, you can also call them noises. We start from it and search the maximum loss around it in a specific range and make it the new loss at this point. So visually, the sharpened parameters have been greatly softened by this method. To this end, when we go through the neighborhood parameters with fixed steps, this process might be not very efficient. Therefore, the adaptive sharpness aware minimization, as known as ASAM, proposed to make the step adaptive. That is, if a parameter has larger gradient, then we give it a larger step to do the sharpness aware minimization. So finally, the hyperparameters we used and the hardware we depend are listed at the upper tables, and our experiments results are as shown in the bottom tables. As you can see, each module we added can cumulatively improve our score a little bit, and the adaptive sharpness aware minimization, the ASAM, as mentioned last page, serves highest improvement of 0.04. This one on the accuracy matrix. And that's all. Thank you.
We just need to switch back to the test.
Shall I keep sharing or?
Yeah. Okay.
Okay, can you see my screen?
Yeah.
Okay, let's get it started. Hi everyone, I'm Jiawei Dong from Shanghai AI Prime, and I'm going to present our second place solution of Clear Challenge.
Our title is Comprehensive Studies on Sampling, Architecture, and Augmentation Strategies. According to the statistics of the dataset, the average size of the picture is close to imaginary dataset. The size of picture in the clear 100 dataset varies greatly, but 99% of pictures has a width and height larger than 250, and most of the picture have one side length to be 500. As shown in the table, the distribution of each timestamp and each category is basically the same. We selected some samples from the dataset. Comparing to normal label, it's difficult to classify some picture into correct category. So it can be considered that there are some noise and hard labels in the dataset, and smooth labels will be used in the training. This is the evaluation metric of clear. Let's skip this part. Here is our model selection. Due to the limitation of training time, we need to choose lightweight models with strong generalization ability. Our baseline model moves from ResNet 18 to ResNet 15D and ECA ResNet 15T. As shown in the table, that under the same hyperparameter settings, the evaluation accuracy of ECA ResNet 15T in the trail 0 of clear 100 is about 14% higher than that of ResNet 18, without adding much computational cost. From ResNet 18 to ResNet 50D with deeper network, we changed the downsampling block of ResNet 50. Works well in practice and impacts the computational cost a little. From ResNet 50D to ECA ResNet 50, we add efficient channel attention module to improve the performance of our model in an extremely lightweight way. On the sampling strategy, the strategy we have tested are the following. First is naive strategy. Second is replaying a previous time step. That means training the dataset with the current time step and the previous n time steps, similar to a sliding window. Third is replaying n time step according to evaluation loss of time step. That means training the dataset with the current time step and the previous n time steps according to top n evaluation loss of time steps. The fourth is replaying n samples according to learning loss. That means training the dataset with the current time step and n samples from previous time step according to top n learning loss of samples. And the last is cumulative dataset. That means training the dataset with all previous time steps. As shown in the table, compared with other strategies, the cumulative sampling strategy can maximize the performance and alleviate the catastrophic forgetting in training. So at last, we use cumulative dataset as our sampling strategy. There are three checkpoint saving strategies we have tested in CLEAR challenge. First is the strategy A, which is based on optimizing next domain accuracy. For each trail, the evaluation dataset is the next time step. For the last trail, the evaluation dataset is the first time step. Here is our checkpoint saving strategy B, which is based on optimizing forward transfer accuracy. For each trail, the evaluation dataset is all subsequent time steps. This is the most time-consuming strategy. Here is our checkpoint saving strategy C, which is based on optimizing in-domain accuracy. For each trail, the training dataset includes the previous time steps and 80% of current time step. And the evaluation dataset is 20% of current time step. This is the most time-saving strategy. Finally, we choose the strategy based on optimizing next domain. There are several reasons. First, the strategy based on optimizing in-domain will theoretically reduce performance due to less training images, and also performance reduction is observed in our experiment. Second, as shown in the table, the performance of optimizing next domain and the forward transfer is almost the same, but the training time of later strategy is much longer. Since each accuracy has the same weight, both of these two have the same optimization efficiency. So at last, we choose the checkpoint saving strategy based on optimizing next domain. There is also a detail about why for the last trail, we use first time step for evaluation. For the catastrophic forgetting that exists in continual learning, choosing the time steps with the largest domain difference from the current time step is an ideal strategy, which is to choose the first time step. To avoid timeout, we use a regressive number of epochs. The estimated training time for a single GPU for every trail will be under 10 hours, and the GPU memory we use is all under 10 GB. Here is our training loss and accuracy on Clear 100. Due to heavy data augmentation, the training loss is much higher than the testing loss. In addition to the last time step, the evaluation accuracy can reach up to 92%, which is very close to our submitted score. Here is our simple ablation study. On data augmentation, heavy augmentation with random, color jitter, random erase, mix up, and cut mix can improve our score by 6%, which may due to the small number of training images. On testing strategy, we test the images with various scales, and we found that the testing image size bigger than training image size, which can improve the score slightly, but there is an upper limit on size of 320. We also test many other networks. Transformer-based network mainly include swing, VIT, VPLOW, DATE, convit. Convolutional network mainly include convnex, TRSnet, NFnet, RecNet, EfficientNet. As shown in the table is the evaluation accuracy of various networks in Trail 0. Most networks are not used due to slow coverage speed or bad performance. And the last is our conclusion. First, cumulative sampling strategy can significantly reduce the catastrophic forgetting during continual learning. Second, checkpoint saving strategy based on optimizing next domain accuracy can be a trade-off between performance and time cost. The third is model with deep and attention architecture is proved to be effective in training and testing. But in small data set, transformer-based model is difficult to achieve same performance as convolutional network. And the last is heavy data augmentation like cut mix and mix up with moderate parameters can greatly improve the generalization ability of the model on small data set. Okay, thank you for your listening.
We need to share your screen. I think the slide should be this. So finally, let's work on first place of the peer competition. Teams from Tencent U2 AI Lab to share the solution. Due to time zone issue, they have recorded video for us to share the solution. They have achieved a backward transfer accuracy of 93% and a forward transfer accuracy of 89%, which is really impressive. They have investigated several bucket-aware sampling strategy, which works on efficient replay when replanning their cumulative method from previous bucket. So I'll save it to the next for the video. So let me just continue my presentation. Yeah. Yeah. Right. So to conclude our presentation, we'll summarize the lesson we learned in this workshop as well as some promising future direction. First of all, from the top 10, we can see that for continuous learning under computational constraint, it is important to adopt smart sampling strategy for training and validation.
Secondly, we can see that the state-of-the-art augmentation techniques, such as the comics, really boost the generalization performance on clear, presumably because augmentation helps the learned representation to be more robust to future distribution shift. However, augmentation is not enough. We still observe from the current result that the generalization performance, such as the next domain accuracy and forward transfer, is still the real-world bottleneck for continual learning. There is still a gap between the backward transfer and the forward transfer accuracy for existing solution. But in this competition, we also see several promising generalization strategies based on adaptive laws, domain generalization, and meta-learning. We hope that the community will come with more innovative solutions to solve those generalization bottlenecks. Finally, that's an important take-home message. As mentioned earlier, CLEAR also comes with abundant unlabeled data per bucket. So I want to show some promising results we have obtained with self-supervised learning. As a preliminary experiment, we used the zero bucket of the CLEAR dataset with millions of unlabeled images to pre-train a state-of-the-art MoCo encoder in self-supervised fashion. And then we follow a standard linear classification protocol for all future bucket. From this plot, you can see that the MoCo pre-train feature significantly improves the performance of all baseline algorithms by average of 15% without any painful hyperparameter tuning. This suggests that it would even be more promising to explore the unlabeled data in future buckets for continuous self-supervised learning or continuous semi-supervised learning. We also like to share that we are currently in the process of expanding CLEAR to an ImageNet scale benchmark, which around 1,000 classes. Please stay tuned for that. Finally, big thank you to our sponsor and friend list here to make this competition possible. We also like to thank everybody for their time here to listen to our presentation. We will stay on the stage for any question. Please come back after lunch at 1:15. Thank you so much. In case anybody interested, I'm gonna skip back for the first play presentation.
Hello, everyone. We are Team Chanel 3 from Tencent Utilab. We are glad to share our solution on CLEAR Challenge. Sorry we couldn't be on site, so we introduce our work in a video. The theme of our presentation is bucket-aware sampling strategy for efficient replay. The presentation includes the following 3 aspects. The CLEAR is the first continual learning benchmark with a natural temporal evolution of visual concepts. And it has a novel stream protocol and evaluation metrics, which allows us to repurpose today's test set as tomorrow's train set. It is meaningful to deal with the increasing number of new coming web images in the streaming way. However, there are some challenges in this setting. First, the visual concepts are always evolving in the real world. Second, due to stream protocol, the train from scratched model should be robust against yesterday and today data and generalize well for tomorrow data. Third, we can only train the models within the specified time limit. In our solution, we first construct a strong baseline. Note that we only use the competition dataset and train model from scratch without pre-training. Training time is limited to 12 hours on a single 1080t for each timestamp. To speed up the experiment, we use V100 GPUs with each timestamp limit of 6 hours. Due to the runtime constraints, the convolution networks are more effective than the recently popular vision transformers. In our experiments, we mainly consider ResNet and its variants. We adopt the following optimization strategies, including cosine learning rate, color jittering, and auto-augment. Cumulative training is also used in our strong baseline. In cumulative setting, we buffer all images prior to the current timestamp for training. It can be seen from the experiments that both optimization and cumulative methods can effectively improve the performance of model. For the ResNet 18 baseline and Clear 10 dataset, the optimization strategies deliver more than 5 points of improvement in performance. Although the in-domain accuracy has decreased, the accuracy on next domain, backward and forward transfer have significantly improved. It illustrates that our optimization can greatly reduce the risk of overfitting. We therefore use the same optimizations on the Clear 100 dataset. The cumulative training boosts the performance by 6 points, even with above optimization for Clear 10 dataset. The unlimited replay of past data avoids catastrophic forgetting, and the diversity of data enhances the generalizability of the model to future data. But at the meantime, it brings a large computational burden. Taking the last timestamp as an example, more than 6 times the training time is required for Clear 10 and 8 times for Clear 100. However, if we want to increase model capacity, like ResNet 50, to enhance the generalization of the performance, the cumulative method cannot be effectively trained in a limited time. It becomes important to efficiently repeat past data without downweighting the new coming data. To make cumulative training more efficient, we propose several bucket-aware sampling strategies. The cumulative method loads all the data from the previous timestamps, which model has seen continuously during training. In early timestamp, the method only loads current data and cannot efficiently train from scratch. Therefore, we can uniformly sample data with a K bucket size so that model can continue to learn some repeated knowledge during the training process without causing forgetting. The model also loads the data with the current timestamp to better learn new knowledge. The above approach is named uniform sampling. Similarly, in early timestamps, if the bucket length is less than buffer size K, we can repeat sampling until meeting the buffer size K to make model better trained from scratch. By setting an appropriate value of K, the uniform sampling method can reduce the training time of the cumulative method, and the repeated sampling can improve the performance models in early timestamp. With these techniques, we can use larger backbone and more iterations to improve the generalization of the model within a limited time. In the experiment of larger backbone, we find that the vanilla ResNet have limited gains even when repeated sampling is used. It seems that the backbone easily suffers from the catastrophic forgetting and continuous learning. From the vanilla ResNet shown in Figure 1, the kernel size of convolution is 1 with a stride of 2. It ignores 3/4 of the input feature map. To enhance the model's ability to capture details, we change the downsampling method of the model. Following the great practices in ResNet D, we avoid downsampling with a convolution whose kernel size is equal to 1. Instead, downsampling convolution with kernel size of 3 and average pooling is used. These techniques can effectively reduce the catastrophic forgetting. With the use of bucket-aware sampling, the training is faster, but with a higher risk of overfitting. So, we use label smoothing to prevent overfitting on training data. Label smoothing regularizes the classifier layer by estimating the marginalized effect of label dropout during training and makes it more adaptable for future. In the experimental result, we focus on the comparison of different backbones and methods on validation set. First, we noticed that uniform sampling can effectively reduce the model training time and only need 1/3 of the original time to achieve the same performance. It indicates that full replay on past data is not required for continual learning. Since the model is already fully trained using past data, we only need to sample a subset of past data to maintain model performance. The same phenomenon is also observed in the larger dataset Clear 100. We use the uniform sampling method to train ResNet 50 model from scratch in less time, and even gain 2 points in overall score. Second, using repeat sampling can improve the nearly 1 point in Clear 10. The improvement is also apparent in the Clear 100 task with ResNet 50D. Although repeat sampling operates at the early timestamp, It can help to the generalization ability of the model through sufficient training of past data. Third, label smoothing is an effective tool to avoid overfitting. In CLEAR 10, the performance gains 0.2 point with label smoothing. We have been utilizing this technique in other experiments. Fourth, ResNet-D is superior to the ResNet. For ResNet 50, adding the repeat sampling method does not improve the model performance. In the ResNet 50D model, repeat sampling can effectively increase the next domain accuracy and backward transfer, while the network training time is only increased by 20 minutes. The above experiments were performed on V100. To ensure that the above method meets the competition regulations, we perform a reproducible experiment on a single 1080T. The experiment shows that our solution requires maximum training time of 7 hours 20 minutes for each timestamp model on a single 1080T, which is much lower than the time limit required by the organizer. In the accuracy matrix of ResNet 50, we can find that repeat sampling improves the performance of early timestamp models, but from the final score, forgetting occurs during continuous learning. In ResNet 50D, the model achieves better performance for both early and late timestamps. This showed that the ResNet 50D model has better robustness against past data and better generalization to future data. In test set, we use some commonly available post-processing methods, such as 5-crop and resizing the image size to 240 or 256. Experiments show that 5-crop improves the performance to about 1 point. And larger image size boosts more significantly on the CLEAR 100 dataset. In conclusion, all these approaches can effectively increase the performance without any additional training overload. With the methods above, we achieve first place on both CLEAR 10 and CLEAR 100 tasks on the leaderboards. Thank you all for listening.
Okay, thank you so much for the presentation. We'd like to thank everybody here in person and in Zoom to stay until the very end. Now I need to hand back to Kongshu.
I think we can.
Hey, Tom. How are you?
Fine. Shall I share my slides here?
Yeah, please try. And then we still have 3 minutes to start.
Sure. Does it look good?
Yes.
I don't know why I'm getting this. Please move this window away from the shared application. Do you see that?
Yes, I see. I guess you have another window overlapping your current slides.
Well, let's stop sharing. I don't actually, but maybe if I just go to full share screen, it's better. Then it doesn't do that.
Looks good.
Okay. Well, so far this has been a great workshop.
Yeah.
Really enjoying it.
Thanks. It's good to have you throughout the workshop.
Well, yeah, I mean, I like to, if I say I'm going to be at a workshop, I want to be there all day. Plus, there's just so much for me to learn. You know, being a computer vision, I'm not a computer vision person, I think, in terms of my training. So my knowledge is shallow. And so it's great to hear from these talks where people go into a lot more depth on what they're doing.
Okay, let me introduce you, although we have 30 seconds. So everyone, we're gonna have Tom present his work. So some recent work on anomaly detection. And Tom is an emeritus professor at the Oregon State University. He's one of the pioneers in the field of machine learning. He also works on computer vision. And his broad research interests covers learning the open world, including anomaly detection, open category, supervised learning, robust AI, so on and so forth. So Tom, it's all yours.
Well, thank you. And as I was saying, I'm really enjoying the workshop today and learning so much. This work is joint work with my now former student, Alex Geyer, and is part of a large team effort here at Oregon State. And we got advice from Fuxin Li, Stefan Li, and Alan Fern in doing this work. So as we were just talking, I'm interested in the problem of open set detection, or generally out of distribution detection, when I have a classifier. Obviously, this problem arises in any application of classification in an open world, whether it's novel obstacles, novel diseases, novel products in online marketplaces, novel cyber attacks, and so on. And one of my goals is that every deployed machine learning classifier should include a competence model that can detect when new queries are far from the training data. And the model, therefore, the classifier should not be trusted. Right. So the picture where I usually draw is this one, where we have our training examples and we train two separate things, a classifier and a competence model. And then given a query, we evaluate the competence model first. And if the model, if it says, yes, I'm competent, then we go ahead and use the classifier. But as I'll discuss today, it seems that in many cases, we can just get our competence score directly out of the classifier itself. And that was the finding of this very nice paper that I like by Vase, Hahn, Vidaldi, and Zisserman that was posted on arXiv last November. Open set recognition, a good classifier is all you need. And what they argued was that a lot of the work showing poor performance of simple methods from trained networks really reflected that we've learned a lot now about how to train, say, ResNets, or in their case, VGG type networks. And so they did this comparison study where they said, well, let's use all of the sort of current bag of tricks, cosine learning rate schedules with learning rate warmup, RAND augment, and label smoothing. And we'll use as the anomaly score just the maximum of the logit scores, right? So I'm going to refer to the penultimate layer or the embedding layer as Z, and from there then we calculate the logits, right? Are just the linear weights that go into the softmax calculation to get the class probabilities. So instead of using the maximum of the softmax scores, we're going to use the maximum of the logit scores. We'll negate it so that whenever it's larger, that means it's more anomalous, more likely to be out of distribution query. So they follow the protocol that one of our students, Lawrence Neal, developed for out of distribution detection and open set detection on a whole collection of benchmarks. And if you use just vanilla cross entropy training, you get quite poor performance compared to the state of the art. And they compared against open hybrid, right, which combines a standard supervised encoder with a flow-based density model that's learned on top of the Z representation. With this adversarial reciprocal points method, ARPL, and the plus CS part here indicates that they're using a generative model as well to generate pseudo novelties. And then what they're calling cross entropy plus, which is training supervised learning, but with these improvements. Okay, so it's telling me now participants can see my screen. Couldn't they not see it before? This gives me a chance to say, well, let me give my. Okay, so so we can see that just using this cross entropy plus with the max logit as the score is reasonably competitive with some very strong methods. And they went on and tested it on some of the larger data sets. So they looked at the birds, they looked at the fine-grained visual classification aircraft data set, and at ImageNet. And across all of these, they were finding that the softmax in many cases is better than this adversarial reciprocal points thing, although this was without the generation of pseudo novelties, except on ImageNet where ARPL plus is doing well. So the question that Alex and I, we had also discovered this phenomenon, but we had not done nearly the detail of experiments that Vase et al. Had done. But we were wondering, why is it? Why is that the max logit working so well? And so we did some additional experiments here. Alex trained a DenseNet that has a 384-dimensional latent space on a split of CFAR10 into 6 known classes and 4 novel classes. And we captured the embedding vectors after every epoch of training, and then threw them all into a UMAP visualization so that we could see how training evolved. And we compare. You'll see these dots. They're light green dots. Those are data points from the novel classes, which are not being used in training. And the darker greens are 6 classes that are known. And so what we see as training proceeds is that it basically pulls the data points that belong to the known categories out away from the center of the representational space, and then they eventually sort of collapse into fairly tight clusters, and we end up with 6 known classes, all in pretty reasonable clusters. I mean, there's some stray points, and that the representation of the novel classes is still much closer to the center of the space. So because my interpretation would be that because the novel classes are not there during the training process, the network hasn't learned to learn distinctive representations for them and separate them away from the center of the space. And we're not the only ones to observe this, right? If you look at the CSI paper by Tack et al., where they were training with sort of SimClear style training and looking at out of distribution detection, they also found that these red points are the out of distribution points, the blue points are the in distribution, and the out of distribution points under this TSNE visualization are closer to the center. Vase et al. Trained a version of their network that had only 2 features in the final layer, again for a CFAR 6-4 split, and we can see that the 6 known classes
are, nicely pulled away from the center of the space, and all of the unknown or novel classes are here in the center. So this led us to what we call the familiarity hypothesis. Our hypothesis is that these networks are not actually detecting novelty in the sense of detecting things that they've never seen before. Instead, they're measuring the absence of familiarity. So in particular, suppose we had never seen an elephant before. Under this familiarity hypothesis, we would say, well, I don't recognize the trunk or the tusks because I don't have visual features learned for that. But maybe I only recognize the feet, the legs, maybe the eyes, not those weird ears. And so the idea is that, the CNN has learned features that detect image patches or patterns that are relevant in some way to the classification task that we've set it. The logit layers then assign weights to those features, and novel classes are just going to activate fewer of those features. So their activation vectors will be smaller in magnitude. And so I think the hypothesis then is that we're not really measuring the novel parts of the image. We're just seeing that there's not much that we do recognize that is familiar. So some initial evidence for this comes from Vase et al. Right? They compared the max logit to the softmax and to just the norm of the latent layer as a function of the number of epochs of training here. And the vertical axis is the open set AUROC. And you can see that the max logit is doing better than the max softmax probability and better than the feature norms. So it's not just that the activation vectors have smaller norm, there must be something else happening with the logits. And that something else must not be happening with the max softmax. Another piece of evidence, we looked at just counting the number of features that have an activation above some threshold. So in this plot here, we are varying the activation threshold, and the vertical axis is the number of activations exceeding that threshold. And again, this is for a CFAR 6-4 split with a dense net. And so we can see that, for instance, if we set the activation threshold at 1, the known classes turn on about 10 features to have an activation of bigger than 1, whereas the novel class images only turn on about 6. And if we set the threshold at 2, then the known classes are turning on about 4 features. The novel ones may be 1 or 2 features. So that's just sort of simple counting. But can we get a sense of, well, what aspects of what features, what aspects of the image are really accounting for this? And so we decided to try to determine whether the features that are making distance are ones that are actually on the object of interest, or are they something on the background? And so our strategy was to blur the object and then see how the feature activations change. So we started with Pascal VOC segmented images because we have segmentation masks for them. And then we'd apply a blur with a 31 by 31 kernel and a standard deviation of 31 to the whole image. And then we would use the segmentation mask to composite just the object, the blurred object, into the background. And so this is a little hand-drawn thing, but here are some actual images to show you what happens. So we can see that the airplane is pretty well blurred. The dogs are pretty well blurred. Here's another airplane. And I'm not sure what category this is. It's some sort of a box, planter box here. But I mean, the rationale is, right, that if the activation of a feature changes when we blur the object, then it must be measuring something about the object. But the converse is not true. Features whose activation don't change might still be measuring something about the shape of the object, because obviously the shape is still really well preserved in these blurred images. So we don't detect all features that might be on object, but every feature that we do detect definitely is measuring something about the object. So we define the blurring effect for feature J in image I as the difference between the activation of that feature in the unblurred image and its activation in the blurred image. And then we are going to divide the features into features that are presence features, that is where the blurring is greater than 0. So the blurring, when we blur it, it decreases the activation of that feature. And we should always remember that a feature in the penultimate layer of a neural network could be actually some complex function of a bunch of different, let's call them primitive patterns in the image, right? When we see some of the work on explanation, for instance, IGOS++, which Fuxin Li has developed, and where they learn sort of and/or trees to explain that a feature is computing some kind of Boolean combination of simple patterns. But we'll say that the net effect of this feature for this image is that its activation decreases when we blur the object. And we call it a presence feature because its activity is high when those patterns are present that it's looking for. Conversely, if the blurring effect is negative, that is, we blur the object and the activation of a feature actually increases, we call this an absence feature because its activity is high when the primitive patterns that are being measured are actually absent. It's presumably subtracting them from some high bias somewhere in the network to get that effect. Okay, so those are or sometimes people call these positive and negative features, but we didn't want to do that because we want to also bring in the weight that is assigned. But in any case, let's now average this over all of the features that belong to class K. So let's look at all of the images whose class label is K. We'll add up this how much the blurring decreases the activity and average that. And we'll say that a feature is a net presence feature for the entire class K if its on-object score is bigger than 0.02, and it's a net absence feature if its on-object score is less than -0.02, and otherwise we'll call it a net neutral feature, and we'll basically ignore those. So then we can also look at the weight that is assigned to that feature, right? The logit score, after all, is just the sum of the weights times the activations plus a bias term, which I forgot here, a weight assigned to each feature for class K. And so we'll call this the contribution. This is a term I think coined by Sun and Lee in a paper they have on arXiv here. And again, we'll use tilde to indicate the contribution when the image is blurred and C to indicate the contribution when it's not blurred. And so we'll calculate the mean contribution as C bar. That'll be the average contribution averaged over all the images in class K. And C tilde bar will be the blurred version of that. So then we can come up with a 2x2 feature taxonomy that says if we have a presence feature, it might be assigned a positive weight or a negative weight by a particular class. And we can have absence features that assign positive weights or negative weights by that class, by the classifier for that class. All right, and so then we can produce these things that we call Sun-Lee diagrams because this is what Sun and Lee had in their paper. You take all of the features and you sort them by their average contribution to a given class. In this case, I'm taking in-domain class 3. And there's a blue solid line here that you can't really see very well, but that is the mean contribution. So there are a few features that are making very big positive contributions to this class, and there are some features that are making big negative contributions to the class. And then the color coding here codes whether it is a presence feature or an absence feature. So these have positive weight over here, negative weight over here, and then there are a lot of these red dots. The dots are for the blurred version, the average contribution when it's blurred. Well, this is hard to read, so we're going to zoom in on the left and right edges of it. And so here's a zoom in on class 3. And what we see is that the blue line here, right, is the mean unblurred contribution, and the red dots are the mean blurred contribution. And the darkness of the degree of saturation of the red dots indicates the strength of the blurring effect, right? And so we can see that when we blur the image, mostly what we're doing is knocking down the weights of positive presence features, and also knocking down the activations, not the weights. We're knocking down the activations of positive presence features and knocking down the weights of negative absence features. And both of those are decreasing the logit score. So when we blur the image, we're decreasing the logit score. Now, this isn't always true. There are a few features that are positive absence features. We blur the image and their activity actually increases. So there are a few that are not helping us, I guess, in novelty detection. So just graphically, I'm going to revisit these 4 categories of features. So positive presence features will always look like this. They will be red dots and with positive weight. And these are negative presence features over here. So this is one where it's a presence feature, so it's a red dot. And because it's negatively weighted, its activation actually, it's in absolute value, decreases when we blur, but that has the result of making its contribution go up. And then we have positive absence features and negative absence features. So now let's look at individual images and see what happens. So we can look at an individual image. This was the one that got the highest novelty score. And we can see that there's a huge effect due to the positive presence features. Although in this particular image, some features that on average are positive presence features are actually behaving like absence features. So, and we have a lot of features that have very low weight and just aren't doing anything. And then we have some of these that are negative absence features that are also acting to reduce the logit score. And we can look at some other instances. They look quite similar. Here's another one. Again, looks quite similar. And so what we can do with one of these is we can add up the effect of all of the positive presence features. That is that were on average were presence features. So all the red dots that have a positive weight, all the red dots that have a negative weight, all the blue dots that have a positive weight, all the blue dots that have a negative weight, and we can plot them like this. So what I've done here is sort all of the novel images that belong to novel categories by their max logit score. So these are the ones with the highest max logit score. That is, they're the ones that are most anomalous. And for each image, there are actually 4 dots or 4 little circles plotted here of these 4 colors. And then I fit a low S curve, which kind of tries to fit the mean vertically. And what we can see is that this is the curve of the positive presence feature. When we add up all the positive presence features in an image, it's almost entirely accounting for the change in the logit score. There's a small contribution from the negative absence features and basically nothing from the positive absence and negative presence features. We can also ask about how this relates to the novelty detection accuracy. So now on this black line here is a low S estimate of our smooth accuracy of the known versus novel images, right? Because in our test data, we have a mix of known category objects and novel category objects. And we can see, again, we're sorting by the logit score, that in this red curve now doesn't have quite the same shape, but because now we have all the images in here, novel and non-novel. But we can see that, again, this is really accounting for our novelty detection accuracy. Okay, well, what are the implications of this? I mean, basically, we view this as strong confirmation of the familiarity hypothesis, because the positive presence features are things that the logits are, or the trained logits are expecting to be present in images that belong to that class. And when the images are absent, or in our case, or have been blurred, then the activation drops, and that's what the logit score is measuring. Okay, well, what are some of the implications? Well, first of all, we would predict that the max logit method is going to work better than something like the Mahalanobis method. Right, the Mahalanobis method basically fits a multivariate Gaussian to the activation vectors for each class separately, but with a shared covariance matrix. And it's an example of fitting some kind of a density model to the latent activations. And the issue here, I think, is any metric that treats all features as equally important is going to perform worse than the max logits. Because one of the beautiful things about the logits is that each class has learned to pay attention to some of the features, but not by no means all of them. And so it's a class-specific detector for change of activation. And so each class is weighting the features very differently. We predict that training on additional known classes will improve novelty detection, because we think it provides a larger vocabulary of more narrowly focused features. And so these will be less likely to be activated by novel objects. Another possibility that we predict is that occluded views will tend to give false novelty detection. Because after all, if I can just hide some of the salient aspects of an object, then fewer features will be turned on, and it will reduce the logit score, and we will, using max logit as our novelty score, we will have a false detection. We also predict that adversarial attacks will easily defeat this. Presumably, it would be relatively easy to introduce some changes in the image that would still activate enough of the logits to cause a novel object to not be detected. Or even imagine just an image that contains two objects, one of which is novel and one of which is known, that known object is going to activate enough things that we will not see the novel object. And finally, we hypothesize that objects that are novel combinations of known features could still be detected as novel. So if we had a centaur and the system had never seen it, but it had seen men and it had seen horses, we think it would still detect it as novel because it wouldn't turn on all the features of horses or all the features of man. And so the max logit score would be less. So we were able to test some of these. So we compared max logit here with Mahalanobis, and we found that, that the Mahalanobis method was consistently worse on all of these data sets. And the max softmax is also slightly worse than, well, actually sometimes more significantly worse on some of these bigger data sets. We did an experiment training on auxiliary classes. So we took the CFAR 100 data set and we divided it into 10 known classes, 10 novel classes, and then 80 auxiliary classes. And we compared what we call the normal configuration here, where we just train on the 10 known classes, and then our test set is a mix of known and novel, and we get an AUROC of 0.757. But in the auxiliary thing, we train on the 10 known classes plus the 80 auxiliary classes, and then test just on how well we can separate the 10 knowns from the 10 novels. And we can see that our AUROC improves dramatically. And so I think it's an interesting question. This is an alternative to pre-training, right? Instead of pre-training on those 80 auxiliary classes and then fine-tuning on the knowns, we just train on the 90 classes that we have available. So we'll see, we need to extend that further, obviously. Occlusion, what can cause false alarms? I'm running out of time, so this is a fairly obvious statement. We did some experiments just recently with two other architectures. So we tried using the instance contrastive training from the Winkins et al. Paper that came out of Google and Google Brain and Google DeepMind. And so this is a sort of SimClear style mechanism. And we see that still the positive presence features are the dominant ones, but surprisingly, there are a lot of negative presence features, a huge number of them. And our guess is that, self-supervised training is learning a whole bunch of features that are actually not particularly useful for the task. And so they're assigned negative weights by the classifiers. We also tried the VIT vision transformer. It behaves a lot more like the ResNets that we've been training. And just to zoom in a little bit on this instance contrasted, here's what the Sun-Lee diagram looks like for them. You can see that just about every feature gets a non-zero weight attached to it. And we have a huge number of positive presence features and negative presence features. So when we blur an image, while the activation drops for all these, and so the logit score drops, the activation drops or heads towards 0 for all these, which actually increase the logit score. So there's a kind of battle between these two. And we can sort of roughly see that the red points outweigh the black points. The black points being these guys over here. But it's just a radically different representation when you do the self-supervised learning. Okay, well, I think it's interesting to ask, can we really expect computer visions to perceive things they've not been trained on? And I think many of you may remember this famous or even notorious experiment by Blake, Moore, and Cooper, where they raised kittens in a restricted environment where they're basically kept in the dark, except for, I don't know, I can't remember, 4 hours each day or something, where they were placed in this visual environment where there were either only vertical stripes or horizontal stripes in their visual field during the period when they're learning to see, basically. And then they found that kittens that were raised in an environment like a vertical environment were basically blind to horizontal contours. In particular, they said if they take a vertical kitten and a horizontal kitten and put them together, and then take a black bar and hold it vertically and wiggle it, only the kitten raised in the vertical environment sees the bar and plays with it. Whereas if they then turn the bar and hold it horizontally, only the horizontal kitten sees the bar and plays with it. And I think our deep networks are very much like these kittens. If there's a direction of variability or object components that were not present in the training set, the network is basically blind to them. And so it can't see the novelty there. Well, what are the possible paths forward? Obviously, one thing is to train on as many object categories as possible. You know, maybe if we had trained on snakes, then we would have been able to detect the trunks of the elephants. So if we have a big enough visual vocabulary, presumably we will detect novel things as novel combinations of known stuff. Or maybe we could systematically synthesize natural parts, whatever that means. You know, I'm reminded of the early days of computer vision when we like to use constructive solid geometry to represent shapes. Could we build, you know, some crazy menagerie of random CSG shapes and train on those and develop feature detectors from them? And with that, I'll just summarize. We are arguing that the max logit score is detecting the absence of familiar patterns rather than the presence of novel patterns in images. We hypothesize that this probably applies to all other deep novelty detection methods, although it's not that remains to be shown. And we would also argue that building better models on top of familiarity-based features is not going to solve the problem. That we need to really find some way of being able to detect novel stuff in images that was not there in our training data. All right, so I will stop there and answer questions.
Any questions?
Yes.
From the audience?
So I have two questions here. So first, it's really interesting that you apply blurring effects here. So I'm wondering why the objects themselves weren't completely cropped out of the image using the same segmentation mask. Is there some motivation for why blurring has the effect that you've shown?
No, that's a fair question. I'm not sure why we made that choice. I guess we were worried that might change the image statistics so much, you know, that it would be a very easy novelty detection task. But we weren't, yeah. But that would certainly be a worthwhile experiment to do.
Got it. And another question I have is there a principled approach for selecting known and unknown classes, or in distribution and out of distribution classes? Because I could imagine if you have, for example, the number 0 in your in distribution class and the number 8 in your out of distribution class, that may have some, I guess, effect.
You should have a lot of the vocabulary you need. Yeah, well, so in the Vase et al. Paper, they selected classes, for instance, in the bird data cub and in ImageNet, right? Their in distribution was ImageNet 1K, and then they used basically distance in the WordNet ontology to decide on what categories were close or far away, right? And the same in cub, they were able to use the whatever it is, 200 and something attributes in the cub data set to define near and far OOD data. That's with cub, it's definitely related to appearance, right? Because most of the attributes are appearance attributes. With ImageNet, probably not so much appearance related.
Got it. Thank you very much. Are there any other questions from the audience here?
Okay, well, thank you for your attention, and I'll be around the rest of the day, so you can shoot me questions in the chat or by email or whatever.
I'll ask a question. So with your familiarity hypothesis, it would be interesting. I know you did some blurring stuff. Have you considered doing more like a jigsaw solution, right? Where you have all the features, they're just not in the right places, right? And yet we know that breaks lots of our systems, but none of the features are necessarily novel. Does it make sense?
Right. So it would be you're saying right, which features are destroyed by the puzzle kind of augmentation?
Right.
Yeah. And I don't know. That's a great question too. Right. And we're also thinking that suppose we didn't have the segmentation maps, maybe it would still be worthwhile to apply some maybe light blur to the entire image, and maybe we could detect from that just which features are presence versus absence features, and maybe we could use that information.
Thanks. Nice work.
Well, yeah, I should thank the anonymous reviewers who told us to think about the negative weighted things, the absence features, because that was a great suggestion.
Great. Thank you very much. So next, I'm pleased to introduce Kristen Grauman, who's a professor of computer science at UT Austin. Her primary interests are video, multimodal perception, embodied AI, vision for robotics perception for action, and visual recognition. She will also be talking about from naming to using agents in the open world.
Sharing on Zoom as well.
Oh, I think Shu may have sent you an email.
Okay. I think it's good. Yeah. Sorry for the delay, everyone. And thanks to organizers for having me here. I think we're all now connected in all the right ways. So this talk is about moving from naming to using. So we'll see how this means something in the open world in terms of agents who need to do things in the world. And in particular, we're motivated by problems where, in the future, more and more, we'd like to have robotic agents that operate in human spaces. And that means they should be able to manipulate human-centric objects and navigate around human-centric spaces. Now, you'll note, of course, in the context of this workshop, that means grappling with the long tail of objects that exist in the world, grappling with things that haven't been taught very explicitly, and understanding whether they're familiar or not, and being able to generalize to, as you'll see today, to tasks that may not have been explicitly experienced before or in a very supervised way. Okay.
Could you hit and then when you share,
screen
I guess,
sharing.
yeah, so you'd have to share from beginning here from this screen.
Okay, let's try it.
Share.
Okay, there was a mismatch with Zoom, I think. Let's see if it's fixed now. Is it good?
No, it's showing your presenter view.
On Zoom, okay.
Yes. So I think you have to tell it which screen to share on Zoom.
Okay.
So share.
Should I stop that one?
Yes. Share. And then I think you have to tell it specifically. So it could be useful to just share without going into presenter. That might be this. I don't know.
Okay.
We're still seeing this.
Okay. Do we have another solution, or
could you just
sorry, could you say it again? Okay. So we okay.
You have two screens, make sure you share screen two.
That's right.
Okay. All right. Okay. Okay, I'm not sure what else to try, sorry. Okay, so again, thanks for your patience. Motivation, agents, and environments, it's gonna be an open world. And when we think about the problems that we want to solve there, it'll include things like specifying a task, say, you know, can you go heat a cup of tea and bring it to me? And that'll require an agent to learn how to uncover, you know, what are the objects that are relevant for this task? Where are they? How do I go move to them? What do I do with them once I find them? And so there's going to be definitely, you know, we have recognition problems, navigation problems that need to be tackled. But on top of that, there's the things that need to be solved, like, is this a cup I could put in the microwave? Where do I go to do something, to make something heated? Or how do I grasp a cup? All these things come together, and you'll notice that that second set of questions really pushes us more towards open world style problems, because we need to know how things work and how to interact with them. And so this is not so much, or it's not enough anyway, to be able to name all the things we see and recognize them again. We'd have to be able to encounter new things, know how to use them, and know where to be in a space to do so. So if you were to train an agent today, there's a lot of interesting work looking at how to build policies for agents that can do various tasks from a bottom-up manner, like taking reinforcement learning and saying, okay, agent, take all your experience, get rewards for when you're doing things right, and eventually you'll stumble upon or build up the behaviors that allow you to accomplish your goals. And while this work is important and leading to really exciting new discoveries, at the same time, it's kind of famously sample inefficient. You got to do a whole lot of exploring and trying things to get a good policy. So this has led people to also explore imitation learning, where rather than just say, hey, try things and you'll get reward when things go well, you can show what it looks like when things go well. So you can think of this as the supervised form of saying, you know, whether manipulating a robot arm like this person is doing, or providing some mocap examples of you doing a task, you could start to teach the agent. This will cut down that sample inefficiency, but there's this need for kind of indirection between how you're showing the robot how to do it, as well as usually a need for some special hardware to accomplish that demonstration. So we come to the main idea for my talk, which is, what could we learn from watching people, and specifically watching them, like watching them in video? Here's an ecocentric video, a first-person video, camera on someone's head, and you can see how rich it is with revealing things we do, like how do we move in a space? How do we direct our attention over time? How do we interact with other people? And how do we interact with objects? Meaning, how do we use them, touch them, when are they relevant? So this is a lot of things that we care to do to bestow to the kind of agents I just described. And so we're looking at ways in which we can teach embodied agents, and my results today, these will be simulated virtual robots to learn their task faster by watching how people do. And I'll touch on the results exactly where the open world bits come in. First, I'm going to look at affordances on objects, and then we'll bring that into a dexterous robot hand that can grasp new objects faster. And then we'll look at how watching people interact with multiple objects and different activities can build up a task agnostic behavior for an agent, so it's ready to solve tasks that otherwise would have very sparse rewards and would be sample inefficient to address. So let's start with the first one in affordances. And this is where the title of the talk kind of comes from naming objects to using them. So in a closed world, we're very happy about naming, we see a lamp and we can detect it. More in the open world, I think you find a place for affordance-based reasoning where it would require looking at an object and sure, it's a lamp, but what would I do with it? Or even if I don't know what to call it, what would I do with it? Where would I grasp it, lift it, turn it, toggle it? And this is the notion of affordances or the potential for action. So current methods have looked at predicting affordances from imagery. And this is can be handled by taking a supervised approach. You say, let's teach the system where it looks like you could hold a book, for example, or any other action on any other object. And this is one approach to treat it really as a recognition task. However, it has the limitation of expense, sure, but also the limitation of saying, we're asking annotators to say where they think they do things, like hold a book, as opposed to actually the rich way they might really do it. And so we'd like to remove that indirection. So we've been exploring how you could take video and start to learn how people do actions with objects, and specifically how to learn where the regions are on objects that a different action is afforded. Okay, and these videos suggest like how complex and multimodal the distribution of places you could use a book, hold a book might be. So let me say a couple slides about the method we first developed here. It's a video-based method. You start with training video that does have labels for actions. We call this weekly label because there's no labels about where you touch the objects. So if you learn a classifier for those actions, all you've done there so far is action recognition. But what we'll add to that is a module that's going to look at an inactive object, an object at rest, and be able to predict what the state would be like for an action recognition system looking at that frame. So in other words, during training, if we know what sequences of frames and the aggregate history of those frames would trigger the recognition of the action, let's train a module that knows how to map from the object at rest, meaning you're not doing anything to it, and to predict what that state would be like. And this is in the feature space. So having done that, and then also kind of back projecting from the with class activation mapping to see which regions in an object at rest are most responsible for triggering that potential action. Now we can come out with what we call hotspot maps, or these heat maps showing where the interactions are possible. And we can do that one interaction at a time. So we say, hey, here's an object, this image of the object at rest. Where are the places where it's pressable, or where are the places where it looks pullable? And you'll get a different heat map for each of those. Okay, so we call these interaction hotspots, and the main idea here was to move away from heavy supervision, saying this is where you hold a microwave or a refrigerator, to instead discovering it from the video as people use things directly. Now we've tested this on data sets like Oprah. This is a Stanford collected data set from YouTube product demonstrations, and Epic Kitchens, which is an egocentric video data set of people using objects in the kitchen. And the key thing we had to test here is, can we predict these heat maps or hotspots on not just new instances, but even new categories of things? So you can imagine training these with a certain bucket of objects, and then encountering, say, a new kind of coffee maker, or a blender, which you've never seen before, or an appliance that you just haven't seen before. So in these new categories, which you can see as a step into this open world, you still want to be able to predict these heat maps. And so that's exactly what we evaluate, is how good can you do in generalization across categories. And these are some videos to show you what hotspots look like. The colors are coded for different afforded actions. So like green is mixable. And you'll notice in that sample, the stuff in the pot looked mixable before someone mixed it. And there's an array of other common verbs among the some dozens of verbs that are learned for this data set, Epic. Here's another one where pink says something that looks washable. And notice the knife is washable. Indeed, it's being washed, but so is the the knife to the left of the sink has that potential for action. And here, these jars to the right in cyan, they looked openable. This door looks openable as well before the interaction begins. So this is a model then that's going to be able to look at the world through the lens of not just what I should call everything, but how can I use it, or where would I interact with it? And we evaluated hotspots, quantitatively in terms of how good are those maps compared to the ground truth maps, even though we haven't trained with any such maps. And the results are encouraging, competing well, even with the heavy supervised models, but also quite a bit better than the existing weakly supervised. Now, perhaps the most important result with interaction hotspots that, as far as this workshop goes, is to look at what they can do for our object recognition, and specifically for few shot settings. So here what we did is to realize, that certain instances of objects are more recognizable than others. We know that. So if you take off an off-the-shelf detector and try to recognize these refrigerators, some of them are well found, like the ones on the left that are kind of canonical, and the ones on the right, however, they're misrecognized. And it has to do with the fact, I think, they're atypical context, unusual viewpoints. But here is what we wanted to know. If we understood these objects, not just exactly for how they look, but also for how they seem to be used, meaning in terms of these hotspots, could we improve our recognition? Because we know that for humans, it is true that before I can name something, my ability to understand how it works would allow me to understand what it is and what it's for. And so what we did is provide not just the visual features that were trained for the task, but also the feature encodings through the hotspots I just described. And in doing that, when we turn to the low shot setting, very low, if you just had 5 samples labeled per class, this is where we see an edge. So if you didn't do that, you're a couple points less on this preliminary experience, a couple points less on the accuracy for the recognition. And it's encouraging result to say that if you anticipate an object's function, you may have more grounds for recognizing it, particularly when you have very few labeled samples, this low shot scenario. So this is an initial result. I think there's a lot more we could try to dig around in here, but somewhere that I hope that this can go next. Okay, so I've talked about hotspots and affordance regions. Now let's take a step from what we're anticipating about objects and how they're used to actually benefit the kind of agents I described in the beginning. So an agent that needs to work in a human space. And we're going to first consider the model of a dexterous hand robot. So this is a multi-fingered hand. Its embodiment is close to human-like, which makes it a great candidate to see if it can look at objects in our world and anticipate how to use them. Now, if you work with an agent like this, a big problem is it's highly complex action space, right? 24 degrees of freedom. You need to control all of them and learn up these sequential behaviors like picking things up or using them to do a task. So extremely expensive sounding kind of learning environment. So the idea we had was to bring in affordances from the visual side, visually detected affordances, and bring in a prior about human hands that we could capture from video in order to accelerate and improve the learning process for this dexterous hand robot. And as I mentioned, we're doing this so far fully in simulation. So what our goal is to be able to take video, like in the wild YouTube video even, and discover how people are holding their hands in order to use different objects, as well as bring in those visual-based affordance regions to know where they tend to use the objects. So we've taken in the wild YouTube videos from the How to 100 Million data set, and we've extracted hand poses like you see here, and then we're gonna ask that this agent that is gonna be trained with reinforcement learning prefer to use human-like postures with its hand to do grasping, and prefer to do it where the affordance regions are. And if we do it well, then you could accelerate the learning, get a better grasping policy, and generalize to new objects. Again, that need is there. It's not that we should have to train a policy to pick up mugs and then a policy to pick up vacuums and one for knives. But once we have an array of objects, what we expect is to be able to generalize that picking up behavior or that usage behavior to know how to do something intelligent, even with an object we haven't seen before. Okay, so that prior coming from video, I mentioned how to 100 million is the source. Here are some frames in which we extracted 3D hand poses using an existing model called Frank mocap, which we chose for its speed and accuracy. You can see some of the hands that are detected, and the way that people are grasping has some, one or more modes of how it's done for the object cup, or here's another set for the object hammer. And so we're learning from these videos how people interact with these objects. And now the way we'll push that into the preference I mentioned for the agent is shown here. We call this model DEX VIP. So dexterous video informed prior is the source of that name. And what you're looking at here is a reinforcement learning loop, where on the left-hand side in green, you have your inputs. It's going to include the RGB, the depth, the affordance map, like the one I showed you with interaction hotspots, saying where the object's likely to be grasped in this case. Proprioception, knowledge of where the joints are, and the object, measurement of the object hand distance. So those are the inputs. And then what your job is as an agent is to keep continually at every time step choosing an action such that the world changes around you and the environment updates what you get as input, and you'll be rewarded with respect to how good your actions are as far as leading to the desired behavior, which is here to get the things off the table. Now, the key new thing in this whole pipeline is the red part. And this is where we're coming in saying we prefer human poses, so we'll reward more when you start using them, even if you haven't successfully gotten the thing off the table. And we prefer those interaction hotspots. Okay, so we augment the reward according to those things. So let me show you what it looks like over time as this agent is training. So it's looking at 6 different objects here, starting to bumble around and through experience realize good and bad ways to approach them. But as we'll see in a moment, getting to a good kind of policy faster because it has this human-based prior. Okay, so remember, this is an agent who's encountering things on the fly and just determining, well, how is it I'm going to start to pick them up in a human-like way? And this is how well it went, and comparatively. So what we're looking at is in curves that say how successful is this grasping versus how long it takes to train that behavior. So you'd like a curve that goes up fast on the left-hand side. The blue curve is the model I just described. The cyan is a ablation of it, where we take out that pose learned from video. And then the other 3 baselines, well, the one in yellow is a more traditional and state-of-the-art model that blends reinforcement learning with imitation. So it actually has seen mocap, motion glove-like examples of how people would do these grasping tasks, and it tries to imitate them to speed up the learning. And then you have more simple, naive priors, like just try to touch the object a lot, that's in green, or try to get it near the center of the mass in red. You can see that this DEX VIP model is accelerating the training, plus it's leading us to a more successful policy overall. Okay, so that's the value of watching people do things as a way to vicariously augment you, the agent's own physical experience. And there's a lot of savings of energy, power, time, once you can do that from the video. I'll show you a couple samples, behavior, from that final policy. The naive baseline I mentioned is on the left, the imitation learning one is in the middle, and ours is on the right. And you can see the blue hand posture, the one we're trying to achieve down there on the bottom. Okay. So starting to get more human-like interaction. Okay. So in the last part, I want to talk about tasks that will be like zoom out a level. So grasping and this dexterous hand is very low level in the sense we have to control all these fingers and then do some fine-grained manipulation. Now we'll look at tasks that are abstracting away those kind of details of the motion, but care about now how to move in the space and how to use and choose objects in the space to achieve a certain goal. So back to like my opening example was something like go make me a cup of tea. Another one would be, wash the dishes. This is something that requires sequential behavior in the space. Now, learning this, I already alluded to how sparse rewards, like the fact that if you just send an agent into a home and tell it, figure out how to wash the dishes, there's going to be lots and lots of trials of things that don't work and don't lead to clean dishes. And we know this because there's so many preconditions, so many things that have to come together just right to get to that high level behavior. So for example, you got to be at the sink. The agent needs to be holding a sponge. There needs to be a dirty dish in the sink. The faucet needs to be on. The soap needs to be nearby, and so on. So getting the intersection of all those things is going to be a lucky event. So I think our goal then is to make it less about the stumbling upon or luck, but to use human behavior as observed through video to zoom in on these likely preconditions. Okay. So again, let's see if we can get this kind of insight from video. And we're looking at specifically egocentric video here, which is wonderful for having this kind of up close view of objects that a person uses. So sure enough, if we saw and understood video like this, we might start to build up models of the kinds of things that need to come together for an event like washing to happen. That's our intuition. That's what we'd like to attempt. So here's how we've actually approached it. We take in the wild video, epic kitchen video, in fact, like the one I just showed you, to discover what objects together are compatible for enabling action. So not just what objects tend to come together in our field of view, but which are the ones that people bring together and enable some activity. We can discover this from unlabeled video, and then we want to leverage those findings to accelerate, improve the policy learning for building up these behaviors like wash the dishes. Okay. So we'll be taking an approach related to what I just showed you, in that we'll try to say, let's learn what are these common interactions that happen between objects, and then we'll use it to kind of augment the rewards for an agent trying to attempt them in this simulated world. So it's valuable to interact with some objects only when other relevant objects are nearby. So for example, if the agent's holding a pan, stuff can start to happen if he brings it to the stove or maybe the faucet, but not so much happens when you bring it next to a book or a bottle. That's the intuition. And so if we capture those kind of mutual compatibilities, then we'll be steering an agent in the open world, without knowing what its task is yet, to favor those kind of compatible interactions, to make them happen so that more preconditions for any task might be met and things could start changing in the environment. Okay. So we did this by looking at the Epic Kitchen's egocentric video I mentioned, and what those red and blue boxes are objects that were found and then found to be part of a hand-object interaction by the person. So they're active right then. And then we build up what we call the activity context for every object. So a pan, in my example from before, remember, would have a high affinity for being by a sink or a stove, maybe a fridge, but not so much with a book or bottle. And now when running this agent and having it learn and explore in the world, it'll just be drawn to explore those more. Okay, so rather than equal opportunity to every object, trying every which way, it's going to favor those first. And that's where, from human experience, things start to happen. And again, I should stress, in the context of this workshop, that means in a task agnostic manner, right? So we're not saying here, watch a person wash dishes, now you wash dishes. This is perfectly valid, but that's more, a traditional kind of imitation that will require like one-by-one enumeration of the tasks. This is a task agnostic preference that says, when you see objects like this, get engaged with other objects like that. I also want to emphasize that these priors that we're going to discover from the ego video are distinct from other kind of useful priors that people have explored. And that is, as shown here, things like object co-occurrence or even semantic relatedness of objects. So it's true that certain objects tend to appear next to one another or next to each other in the room, but this is different than being relevant to human use of the objects. So we take the activity context that we discover from the ego video, we write them all down as scores between any pair of objects. And now when we encounter an egocentric view for our agents here in the AI2 Thor environment, you're going to see that as it's picking up an object like a mug, here it's picked up a mug, then we're just color coding according to rewards that our activity context would issue, saying, hey, approaching the sink is starting to look promising. Here, picking up a pot, things look promising by the sink when you passed. Also the stove over there. Picking up a knife, getting it in the garbage can is not rewarded so much because not much activity tends to happen for people in video when that would happen. So you're getting these augmented rewards, and then finally we put it into an agent that is trying to solve visual semantic planning tasks, like the ones you see here, like cool something, store something in a drawer, heat something up, etc. And we add this task agnostic reward to improve our ability to solve these tasks. Okay. And indeed, the curves kind of similar as the ones I showed you before. High and steep is good. We're accelerating the learning and getting better policies as a result. So the final slide here, one way in which we can look for greater structure and finding about human-object interaction is indeed egocentric video. And there's a paper from a large team of us appearing Friday at the main conference about Ego 4D. And this is a massive new data set of ego video captured all around the world from 9 different countries, 74 different cities, more than 900 people wearing these cameras, such that we now have a volume of 3,600 some hours of content that you can license and use freely for research. And it's multimodal with the video, but also audio, 3D scans, IMU, stereo, multi-camera capture. So if you're interested in the video itself, you can check out this work as well. All right, so I'll stop here. Thanks so much for your attention. Highlighting the first authors on the work I highlighted today, Tushar and Priyanka. I'm glad to have questions or comments.
I'm curious how. So it's clear that there's a huge value in looking at actions performed by hands. But I'm wondering, is there a way we can extend this? For example, movable is a really important action for an autonomous vehicle. So I'm wondering, is there a way we can extend this to think about object localization and finding objects of interest in that sort of scenario?
Yes, I think you're saying discovering which objects tend to move versus those that are stationary. Sounds very relevant for kind of learning from unlabeled video. Yeah, and again, maybe add to that the class agnostic ability. If you're looking at objects you don't know, but there's still supposing you have proposals to find that you could detect if they tend to move or not. Sure. Yeah. Okay. All right. Thank you.
Hey, Walter.
All right, I think we're okay now, right? In terms of the online.
Yeah. Thanks.
Okay. Move, I guess that's fine. Okay, so novelty on the road is still a significant impediment. New things appear all of the time. Humans are very creative. We invent new objects, right? Which are then seen on the roadside, et cetera. And even recording billions of miles of driving necessarily undersamples the visual world, which kind of seems surprising, right? Especially, right, if you're really deep into the big data strategy, you know, learning from data, all this stuff that we do in computer vision. But if you step back and think about it, it's like, yeah, you know what, that does make sense, right? Because the universe is so vast, even on a temporal basis in one day, right? There are so many new configurations of people and vehicles, different things, right, all over the world. You know, it's going to be an issue. So that means, clicker is not working. Oh, there we go. Novelty is a problem in any visual recognition domain once you move out of a data set. So I've been studying this problem for a long time, as Terry mentioned. In fact, Terry and I started this work about a decade ago. In the theme of some of the talks we've heard today, right, we started with classifiers, right? Because we thought, you know, this probably comes down to decision making. You know, what is going on? You know, we've got, you know, our training samples, right? We've got our known positives, our known negatives. We can learn a decision boundary from that known training data. But what is really happening when we have these unknown samples, right, from a different class? It's going to end up in space somewhere, right? So we can imagine having a really simple linear classifier. That unknown has to appear either on the positive or the negative side. Which side does it appear on? Well, that may be a function of the feature space. But the problem is, once it's far enough away from the support of the known samples, it's going to cause us, right, some trouble, right? Because we have no good basis to assign this as a positive or a negative sample, right, depending on what class we're interested in. And so we studied this. We started to articulate a notion of open space risk, right? The more we're away from, you know, the known data, the farther away we are from that data, the more of a problem we're going to have, right, as we put a sample out there. And that's good when we're engineering algorithms, right? It helps us reduce then the risk if we have this notion. And we can create different classifiers, which is where we started, these like variations on SVMs. Eventually the work took off, right? In the literature, you find variations on softmax, right? Trying to address this at a classifier level. We looked at incremental learning to try to not only detect novelties, but to identify coherent classes and then incorporate them back into our model. And then others, again, have picked up this work, going back to representation. What can you do in the representation space, especially reconstructing positive samples, right? What are the facets of that? So you see models like CROSR, multitask OSR. OSR here is open set recognition. There's a bunch of these that have hit the literature recently. And they all work to some extent, right? This is better than having no risk mitigation when it comes to unknown samples. But you know, the improvement has still been limited in practice, right? So maybe we need to go back and think a little bit more about this problem. So I want to pose this question, right? What does it mean to be novel? What does that really mean? If you look at the literature, this term is typically used rather informally, right? We sort of say, you know what, we know it when we see it, right? And that's about it in terms of thinking through this. Maybe we need a bit more. We can pose further questions. Is novelty a noticeable change in the world that does not impact an agent's task performance, right? We're simply assuming that novelty in many cases will be a problem, but in some cases it's really not, right? Do we have to account for that? What about a change though that does impact the performance, but is not directly perceptible, right? That could be a big problem, right? As we have especially interactive agents like we just heard about from Kristen's talk out there in the world. If the world has not changed, but the agent senses a random error that produces an input that leads to an unexpected state, is that novelty, right? Well, in some sense it is, right, when we think about the operation of an agent, but that is really not an issue with novelty as it exists in the world. Again, if you look at the literature, we're sort of assuming that novelty is inherent into some space, right, the physical world, and we're sampling it and then encountering it. But again, agents these days, right, especially when we think about AI at large, bit more complicated. So we got to factor all that stuff into something. So what I want to talk about next is something we're calling a unifying framework for formal theories of novelty. Yes, there are a few theories of novelty out there in the literature, but they tend to make different arguments, right? They're not unified. And they also tend to be domain specific, which is a confound. So what we wanted to do in this work was build not necessarily a new theory and a new explainable theory, but to create a framework which we could use then to spin up new theories as they apply to specific domains. This is work that's come out of the DARPA Sail-On program. And you can see the author list here, some of the folks involved in this workshop, either as organizers or speakers up here. So it's really a nice joint consortium thinking about this problem. Okay, so let's set some ground rules here for our unifying framework for novelty theories. So the problem, as I mentioned, right, no consistent definition of novelty in the literature. So what's our solution here? We want to formalize what it means for an input to be a novelty in the context of agents and artificial intelligence. So this means we can accommodate interactive agents, right, that are interfacing with the environment, getting new input, right, and making decisions based on that input to take further action. But it should also subsume the more traditional image classification style problems here within the computer vision community, right, which are kind of dealing with static images, right? Not really a complicated agent, but an agent nonetheless. This means that many theories of novelty are possible, and we can define them via this all-encompassing framework. Excuse me. So as I mentioned, right, there are some other theories out there. Again, some from my group, some from other groups. Open set recognition, right, is the one we're probably most familiar with, you know, in computer vision. But novelty detection is a classic problem, especially within signal processing. You can go back in the literature and see different articulations of that. Open world learning, this extended the idea of open set recognition to have an incremental learning component, right? So I identify novelty, I identify enough instances of novelty, and then I fold that back into my model. And then there's some more recent generative theories of novelty floating out there. Pat Langley had a paper at AAAI 2020 where he made an argument about sort of novelty in the world. Okay, so, sorry about that. This hybrid stuff is complicated. How's that? Is that better? Okay. Okay, so three spaces where novelty may occur, right, in our framework. The world space is the one we typically think about, right? That is the physical environment, right? We know unknown things exist there. We don't have a comprehensive idea of the universe, right? So that makes sense. But we're adding two additional things which are really consequential because they deal with the operation of the agent itself. So first, an observation space. In other words, what is sensed from the world space. That's going to be a sampling, a necessarily incomplete sampling. And that could be, again, as simple as I have a camera, right, that my agent interfaces with. And then the agent itself, right, which could be a perceptual agent, again, thinking about image classification, could be an activity-based agent, right, if I'm dealing with a mobile robot, or maybe an agent within a virtual environment. And that space, again, it can be decoupled from this observation space because there could be further processing, right? I got some information, right, and some feature representation. Now I'm doing further processing on those features. I may have some pre-programmed logic to make a decision, or again, I could be doing a lot of sort of additional learning from data within the agent, right? As we all know in AI, right, these agents are getting more and more complicated. And so we've separated that out. A couple more definitions which are really important here. Dissimilarity, right? How are we going to tell if something is novel or not? We're going to define that as the dissimilarity between the potentially novel world state and the experience of some non-novel world states. And we'll say that defines what novelty is. And then we can also define a notion of regret. This can be a function that assigns a penalty corresponding to a move to a new state. Right. And again, this is really consequential when we have activity-based agents, right, that have to move in the environment. Some of those moves may be advantageous. Some of them may affect performance negatively, right? And so we have to figure out, you know, once we're making this calculation and moving into a new state, was this a good move or a bad move? And then we can define these across the three spaces I mentioned, right? So assume we have some task tau that is tied to a particular domain, right? Something where we have an agent trying to achieve an objective, right? And again, this could be something basic like image classification, could be something complicated like I want to win a video game. We can define a world dissimilarity operator which exists only in the world space, so it'll be tied to some notion of ground truth. Again, this is information the agent probably does not have direct access to, unless, again, it's in a pre-programmed kind of virtual environment where you have an Oracle type setting. We'll have a representation of the world, and that could be, right, a subset of the entire world, which it most likely is, right, because we can't deal with infinities usually. We'll also have a regret function there, which again has the real labels, right, the ground truth. We can also have an observed dissimilarity operator. This is, again, the sensing piece interfacing with the core logic of the agent. That will have access to the world, but obviously some subset of the world, right, because the agent can probably not see everything. And then we can have a regret function associated with that. Again, thinking about actions, right, what actions are possible, what's that space? That's going to be coupled with whatever we were able to observe. And then we have the agent itself, right, which again, through the observation made, right, by the perceptual operator is going to have some notion of dissimilarity and then its own regret function as well. Okay, so here we have the main elements then of an implicit theory of novelty. And again, this is generic, right? This is a template. This can map to whatever your domain is. A key thing, which I haven't mentioned yet, see if my pointer works, right here. For each task, we're going to have this thing we call an experience tensor. This is going to record things like training data, if we have a learning-based agent, right? The stuff we have up front, which has been sampled from the world. It's also going to be what we've encountered in operation, right? We collect that information. So this is what we have direct experience with respect to what our agent is and what it's processing. So the agent is composed, right, of basically these two pieces interfacing, right? The perceptual operator, which gives us our observed space, which probably will be some feature space. We can do that processing there. And then the agent itself, which is operating on that sensed information. That all exists within the world space, right? Because the agent is in the environment. And again, the agent has incomplete information, but it's getting some of the information from the world through the perceptual operator. And then the agent makes decisions, right, takes an action, and then transitions to some new state, which could be good or could be bad, right? And of course, when we're thinking about novelty, the novelty may affect that in a bad way, but sometimes not at all, which is interesting, right? That's the key thing here, thinking about different types of novelty. So knowing that we have three spaces, what types of novelty exist there? Well, the one we really care about is the one that exists in all three spaces, right? This we call a unanimous novelty. So this is a novelty that truly exists in the world. It's able to be sensed, so it's an observation novelty. And the agent knows about it, right, through the observations. And so these are the things we typically care about. Now, if you look at this Venn diagram, it's kind of complicated. There's a bunch of other types of novelty there. What are they? Why do we care about them? Well, maybe not, right? The ones we really care about are the ones that are going to impact the operation of the agent, but we didn't sense them, or they were ignored for some reason in the processing. So we could imagine having, again, some observation that's made, and we've missed, right, a true novelty that exists in the world, and that may impact the agent's performance. That's an issue. But maybe there was a glitch, and we have a faux observation novelty, but the perceptual operator simply ignored it, right? So that information is not passed to the agent. That we probably don't worry about. There's really dangerous novelty in the world, perhaps, imperceptible novelty. This is something that we were not able to sense. But perhaps, right, it has some impact on the agent. That's a big issue. The agent itself may be glitchy, right? We could have some novelty that is flagged, but doesn't really exist, right, as an observation or in the world. Really fascinating. We may have this case of unverifiable novelty, where the agent has implicitly detected that something is novel, even though it was not sensed. Down here, right? It's not an observation novelty, right? So that sort of falls out of other variables, other things that have been sensed. And again, that could have an impact on the performance, but maybe not, right? All those things together are what we need to account for when we start to think about designing these agents. Now, there are two additional novelty subtypes. One is okay, and that is the managed novelty, which is a world novelty such that its implication on regret or performance is minimal, right? The agent is handling it, and this is not going to cause us a big problem in whatever our task is. The second one, I think, is one of the key things we need to think about in computer vision at large. That is this idea of nuisance novelty. This is a novelty for which the world regret and the observation regret significantly disagree. So this means in the world, it shouldn't really have a big impact once it's sensed and once it's processed. But for some reason, the agent is having a lot of trouble with it, right? It's flagging, this is a novelty. This is a novelty I probably need to care about. So you may be thinking, what exactly is an example of a nuisance novelty? Well, imagine you have a data set and imagine someone takes this data set and processes it globally to change the brightness in the images. And you trained on the old version, but now you're testing on some other partition, right, in operation, and it has that brightness shift. All of a sudden, right, you're signaling novelty, novelty, novelty. But if you're doing something like object classification, that shouldn't really impact the operation. Right? But again, if you're doing novelty detection with that, you may be getting this false sense that the world has changed drastically when it really didn't. That's an issue. Okay, so you may be thinking at this point, okay, it's a lot of good information, but is this really useful? You know, can I bake this into my design process when I'm creating, right, a new network, a new, more complex agent? The answer is yes. In fact, that's what my group and other groups have been doing. So here's an example task, handwritten document transcription. This is a really interesting computer vision task, which I think is highly underrated because this field declared optical character recognition solved around 2007 or so. But if you've ever had to like OCR a document, especially a handwritten document, you realize, ooh, we did not really solve this, right? There's still a lot to be done because you have to fix a lot of stuff by hand. So what is this task, if you're not familiar with this? Basically, I have an image of, say, handwritten text, and I want to convert it to plain text, right? Which is easier to search and edit, etc. And so why is this a novelty problem? Well, if somebody wrote stuff down, right, they can do whatever they want. So you typically find things like novel words, novel characters, glyphs, errors, right, things scratched out. There are other novelties you find here too, like the writing style, the overall document appearance, right? A bunch of these different things. And if there's a lot of novelty, right, that could significantly impact the plain text transcription, right, which is an issue. So in some recent work we published at ICDAR, we looked at creating an agent that can manage this, do novelty detection, et cetera. So going back to the framework, where would we start, right, if we wanted to try to solve this problem accounting for this novelty? Well, you start with a specification, right? A specification for spaces initially. So this is something that was pretty common in the AI literature, like the classic AI literature. You know, this is like chapter 3 of Russell and Norvig. We sort of updated this idea of creating, right, a specification using these elements of the framework, which I've described. So our task obviously is text transcription. The world is going to consist of some d-prime dimensional space of handwritten documents. An observation space is going to be a d-dimensional space that can encode all possible images of handwritten documents. In other words, right, the feature space. And we're going to have some perceptual operators, basically just optical sensors, right, the camera, that's going to capture a visible region of the world where a time step t results in a single image of a handwritten document. And then the perceptual operator may continue with feature extraction on the captured image to represent it as a feature vector of arbitrary dimensions to the agent in that observation space, right? So that's a pretty basic articulation, right? It's like take image, extract features, right? And now we're ready for further processing. So how about dissimilarity then, once we have that framework set up for the sensing? Well, the world dissimilarity functions and the novelty threshold, which we need to actually determine whether something is novel or not, are going to be determined by the ground truth labels, right? As I mentioned, right, that is the world, right? It's something the agent doesn't typically have direct access to. That means we can measure dissimilarity using a distance measure like Euclidean distance, say, with a threshold determined by the probability distribution of the data, which we can model because we have exhaustive knowledge of what that world is. And again, that's sort of an idealized conception of the world. Then we have dissimilarity functions and a novelty threshold for the observation space. That's going to be determined by the agent's knowledge and design for the task. So in a learning-based agent, which we typically deal with in 2022, this is done via generalizing from the ground truth and any available training or validation data. And these functions then can make use of Euclidean distance or whichever distance measure is suitable, right, for the task. Regret, again, something that's really important, especially if we have a little bit of interaction or temporal nature to our problem. The world regret function is based on the error as measured in the world space given ground truth labels. For transcription, there's a bunch of things that are typically used in the literature, right? This could be Levenshtein edit distance, character error rate, right? In other words, like how many characters do we get wrong? Or even the word error rate, right? If we're really interested in the application, right? How useful are these transcriptions for the user? And then we're gonna have an observational space regret function, which defines what the agent deems important to the task. And again, this maps to this machine learning setting, right? So this is embodied by the agent's internal model for the task, such as the loss function of the neural network or the likelihood calculation in some probabilistic model. Okay, so here's just a baseline agent, right, for this problem. Here we've got, the world, and we're going to sample from it, right, using our sensor, right? So now I'm in the observation space. Once I have my text line image, we'll assume this is, the document in the physical world here. And then we go on to process this via the agent. In the document transcription world, CRNN models, which are a basic recurrent network for this like temporal information, right, which you get out of a document, the sequence of characters. It's typically used to process that type of information. Whoops. That we're going to move then that feature space to different tasks. We can do the transcription piece, which is all I'm going to talk about, but you can also do writer identification and appearance recognition as well. For transcription, right, then we could apply a threshold over, say, the probabilities that come out of the CRNN, or we could choose a different open set specific classifier if we want to do incremental learning, like the EVM. And what we get out then is our predicted transcription, right, which should be some readable plain text, ideally correct. So thinking about predictions then made by the theory, right, if I was going to try to understand the nature of novelty with respect to this agent, what would I need to understand? So let's assume we've got a dissimilarity implementation, which is just 1 minus cosine similarity. Let's think about this experience tensor, right? I think this is a key piece to understanding this particular task. It serves as the history of experience of the agent and plays a key role when a change in the world state is considered novel at a time step, right? This is recording basically the information, all of the information that the agent has ever had access to, right? From training up through testing. The agent's training set and indirect information from the validation set are drawn from this experience tensor, which informs the agent about how it should set its internal threshold on the observation space to make this novelty determination. And then finally here, this observation, quite key, a world novelty may or may not affect the agent's performance on the task, and the novelty's effect may vary in impact to task performance. So let's try to formulate, right, some hypotheses tests that directly map back to this experience tensor to try to understand in practice, right, what are the novelties we really have to worry about? And again, this is a little bit different than just like straight up doing your data set based evaluation, right? Here, we're going to be concerned about, say, proportions of novelty, type of novelty, the distribution of the novelty, and the location of the novelty in the stream of information that this agent is processing. So a basic experiment here, we took the IAM offline handwriting data set, which is like the MNIST of the handwritten document processing world. And we modified it such that we injected different types of novelties, right? In some cases, this was adding things to these images. In other cases, it was these global transformations I was talking about earlier, some of which, right, you may consider to be nuisance novelties. And so we had 55,000 different novel writing samples used in this evaluation. And so we could ask then, some questions that are pretty relevant to the real world operation of an agent like this, like what affects the false positive rate? It turns out the proportion of novelty is pretty darn significant, right? The more novelty I have, right, the better chance I have, right, especially if I have an incremental learner, of collecting enough evidence, right, and then incorporating that back to the model, and then, right, reducing the false positive rate. So running some ANOVA analysis of the statistical influence, right, of all these different conditions, we learned some interesting things. We learned that the distribution of the novelty is key, the location of the novelty is key, the proportion of novelty is key, right? These were all statistically significant. But the hypothesized level of difficulty of the novelty was not a big factor, right? So it's kind of more about distribution, amounts, right, versus the type of novelty that was observed. And again, this style testing is a little bit different because it's like we're thinking about what we present to the agent, not just giving it the whole data set, wholesale and processing. Okay, so that was kind of what this framework is in a nutshell. I'm happy to answer any questions. Yes.
General question on this space definition. Maybe start with the goal of this
I would say it's more of the latter, right? Because the world in some sense is not understandable, at least completely understandable, because in some cases, right, it's so vast, right? So we're really interested in what is the agent sensing and what kind of mistakes can it make, right?
In that case, I think you touched this point in a very similar like the inconceivable novelty, and also the place where you ask me like the matter. I think, like for example, the working novelty that neither consumable or a fact agent is probably something that we don't even care about, and something that we probably don't even be having. In that case, even necessary to define three kinds of novelty. Is it enough to just define observable novelty and behavior novelty?
Yeah.
And just disregard the word.
Yeah, so that's an interesting question. I mean, maybe not. I mean, you can imagine different agents handling that situation differently, right? Like maybe in some cases, those world novelties that were imperceptible in one agent become perceptible in another, right? I mean, they're still there, right? We still have to account for them in a general framework. But I agree, like in your particular design, maybe not a big deal, right? It's again, like that's information you typically don't have access to in a complete sense from the agent side of things. But again, we were trying to be comprehensive, so we decided to define that as well. Good questions. Other questions from the Zoomers, anything? Silence. All right, then thank you. Stop. Oh, good, you stopped me sharing.
Does it look fine on Zoom? Okay. Okay. Hello, everyone. I'm Deepak Pathak, and thanks to the organizer for having me. And today I want to talk about some recent things our group has been working on. And more generally, the goal of our group has been to build robotic systems that can function in the wild, or in other words, in thousands of tasks in thousands of environments. Robots that can do chores in your house, but not just your house, but all other houses and all different scenarios. But this goal is very far from where things are today in robot learning. And in contrast, we have systems that can perform one task in one environment only. Okay, so like for instance, a system that can play Go cannot really grasp objects in a bin. Now, this generalization is not only the problem in robot learning. Even in deep learning, especially computer vision, or the simplest case of supervised learning, we suffer from generalization a great deal. Like if I take examples of vision transformers, only few months old, like 6 to 8 months old, and they work really well on ImageNet and other tasks. But if I show them this image of chair, they misclassify it to something as Band-Aid. Okay, and why is this the case? Well, it's not very hard to figure out that the reason behind this is that the data seen during training and test do not in general, sorry, it's not working for some reason. the data seen during training and test do not belong to the same distribution at test time, and whenever this is the case, things start to fail. Now, this is like, for instance, in case of chairs in image look like this, but if you see chairs in the real world, they look like this. And I showed an example of similar thing before. In robotics, the problem is much worse, where we can have all these robots that can perform all sorts of parkour tricks, but if I put them in the real world and ask them to perform a simple task of putting a block on the table, failures can be catastrophic. And for instance, in this case, the block fell, but then the robot hand got stuck, and now the robot fell. Now, every failure, unlike misclassifying a cat into dog, costs thousands of dollars, and which is very difficult to afford in academia at least. So how do we generalize beyond training? The solution that I'm going to propose in today's talk is very simple. The only way to generalize to unseen scenarios is to keep adapting online. Just keep updating your model to work in the real world. Okay? So in contrast to the current methods, which start from some training where we train the model, we freeze the weight, we want to, and then apply the test set, we want to shift to a setting where things are adapting continuously, or something is changing continuously in the real world. Okay? But the big question is, how do we go from this fixed frozen weight setting to this continually improving setting in the open world, in the wild? Okay? So in today's talk, I'll give a couple of examples in vision, robot learning, and different tasks as to how can we achieve this in different scenarios. So let's begin with the first task here. Let's say to reduce the complexity, let's fix the task. The task here is walking. Now your only goal is to walk in every possible scenario in different possible ways, okay? And the idea we want to employ is similar. Like these agents should continuously adapt online, and this adaptation will help them generalize beyond training environments, okay? So to make the task hard, or to make the training simple, we train these robots in simulation. So this is the only terrain where we train this robot. And in this terrain, you can see it's a bumpy terrain, and there are different kinds of bumps, but that's all this robot sees. But the main idea behind this robot is that it will adapt in the real world. So now I'll take this robot, I'll first show result and then go to the approach. So I'll now take this robot and I put this in the wild in lots of different scenarios, okay? And all these videos are real time, and same policy is being deployed everywhere. So for some reason, this is not working. Okay, so we deploy this robot from simulation to this terrain in the real world. Let's see, can you hear the sound? Okay, just a second. Sorry, should I enable on the Zoom?
Get out of screen sharing.
Okay.
Go back to Zoom.
Or should I stop sharing?
And stop sharing. Then share screen. Share screen. Share screen. Click. Oh, you got those two.
Okay.
You should be able to play some.
So this multi-modal system is very hard for human agents. I don't know if you can see this. Okay, so as we can see, this robot, while being deployed in the real world, can still function. So we can also deploy it in terrains which it has not seen before. For instance, stairs over here. As we saw earlier, the terrain had no stairs, just bumps that we can adapt to stairs at test time. One more example, putting this robot in this deformable terrain. Now, those of you who have worked with simulation know how hard it is to simulate deformable things in simulation. So it's almost next to impossible at high speed. Putting these robots on vegetation, it can walk forward. Indoor environments, it planks, etc. It can also walk in deformable surfaces like wet mud where the feet get stuck, or sand where there is a drag onto the feet. Now let's go into how is this system trained. And as I was saying earlier, the system is trained in simulation, but at training time, it sees this terrain. Okay. Now you want to randomize a bunch of things. Like you want to randomize some friction, some height, variance, but keep the same terrain. Now, instead of making a single policy walk across all the scenarios, we want to train an adaptive policy. So from simulation, we use the privileged data available in simulation, let's say mass, friction, center of mass, and we encode this into some latent vector, into some extrinsics, which condition onto this policy to output the action of the robot. Okay. Note that this policy is adaptive. It's not invariant. Now, this policy relies on what is the condition of the terrain to work in the scenario. Okay. But this extrinsics is not available at test time. So how do we deploy this robot? Okay. This extrinsics is not available because these parameters of which we obtain from simulation, mass, center of mass, friction, they are not available in the real world. Okay. So how do we deploy it? The key idea is we want the robot to adapt from its past data to adapt its extrinsics. So in phase 1, as I described earlier, you train this policy using reinforcement learning, conditional on the mass, friction, and height. But in phase 2, you take the history of the robot. So the history of robot's state and the actions you applied. And you use the disagreement between what you commanded to the robot, what it did to adapt this extrinsics at test time directly. Okay. So in phase 2, you basically regress this z vector from the history of the robot to find the z hat t. Okay. Now, why should history have any information about the terrain? So you can think about this very intuitively. Let's say if you move your hand in the mid-air, in air you apply some torque and your hand moves 1 meter. Now, if you apply same torque inside water, your hand will move less because you need more power to move your hand to the same amount. So the disagreement between what you command and what happens actually is a signal to break the environment. So at test time, what you basically do, you discard this whole encoder and just use the history along with the base policy to deploy the robot. So at test time, this module, which we call rapid modal adaptation, this module RMA, this takes the history of the robot and it outputs this latent vector to run the policy in the real world. And this is what results into generalization across all these terrains through this robot. Now let us really see, because in deep learning, we do not really know what is going on inside the system because everything is black box and there is some mumbo jumbo going on which allows the robot to walk. Can we really analyze that is it the adaptation that robot relies on to walk in new scenarios? So what we do here, we create a difficult scenario because we had tried all things outside. So we thought inside home, let's create something more complicated. So this was done during COVID. So you can see it's a home and here we create a terrain with plastic sheet and then we put some oil in it. Okay. Despite in academia, we can still use olive oil to throw on the ground. Okay. So to make the task even more harder, we put plastic sheets on the leg of the robot so that it can slip on this terrain. We ask it to walk. Now, as you can see, this can walk, but it's very difficult to appreciate how hard the task was. So let's see it in slow motion, like much slower. As you can see here, despite the slipping and almost about to fall, the robot can manage and walk forward. And in fact, when we visualize these extrinsics, we can see their behavior change as soon as the robot comes to this oily surface. Now we do more testing or more abuses to our robot. So when it is walking, we throw more weight on the robot. Note it was not trained for any of these ranges, but it can adapt at test time because of the training extrinsics being estimated from the history of the robot. So in one more scenario here, let's see it in slow motion. So here we can see the robot really bends down very like an agile animal to account for the impact or impulse from this falling weight. And it was not trained with such weights during training time. So again, a comparison of what happens if you adapt on the top. The robot itself is 12 kg, and we are adding 8 kg of weight. It's like carrying almost 70-80% on your back and walking with that weight. So it can walk with adaptation. But if we adapt only once and not continuously throughout the life of the agent, this happens. So it incurs a pretty bad fall, and this was pretty harsh if you heard the sound. And but yeah, but things we do in the sake of science. Okay, so the second thing here is how does it work compared to classical controller? And here is one more comparison. Now, classical controllers are not this bad, but in this scenario, if you notice on the ground, it's a mattress. Now, when you put a robot on the mattress, it cannot detect the force feedback. And because of lack of force feedback, classical controllers get completely thrown off and fall out of the scene. But with adaptation, you can still adapt and make the robot work in these scenarios. So we also ran this robot in and compared it to, can we connect this idea of walking in robots? Since this walking is happening from experience by learning through lots of experience, can we relate how does this robot compare to animals? So there is some analysis in biomechanics called Froude number analysis, by which we always thought before that this robot is a robot dog because it's a very small size, and we'll show you in a minute. But when we compared the Froude number, it turns out this robot is very similar in terms of Froude number to a horse. And in fact, there's a very similar work in classic work from Hoyt and Taylor in Nature 1980, where they measure how much energy do horses consume when they walk. And they show different gaits like walking, trotting, gallop by measuring how much oxygen they consume on this axis. And we did a similar analysis, not quite exact because our robot does not consume oxygen. But we found similar trend between the two scenarios where this robot horse, which looks like a dog, shows all these different gaits. So at low speed, it walks. At high speed, it gallops. At medium speed, it trots. So you can see the behavior changing from walking, trotting, walking at low speed. So as you change the speed, the robot changes the behavior. In fact, at very high speed, we found a flight phase to emerge. This is the phase which is displayed by cheetah when they run on the ground, where all four legs are in the air. This kind of behavior is very hard to hard code because it's like the whole robot is in the air at this time. Okay, so in more recent updates, we have applied this robot to biped as well. This is a much bigger robot. And similar walking on the oil or watery slippery surface. Despite not being trained for such a high payload, it can drag this 40 kg payload through wires or this rope, etc. But as I presented so far, all these robots were fully blind. Like all they were relying on the sensing of their body to walk. Now this begs the question, why do we need vision if a blind robot can do this well in lots of scenarios? Okay. Well, this question actually is very important because that all those terrains do not constitute most of our natural world. So for instance, perception enables precise locomotion. In a terrain like this, humans have no difficulty walking, like stairs, these stepping stones, and this is where perception comes to play. So here we want now what I'll show next is where we tie this proprioception based walking with vision and how we treat vision as a first class citizen. Okay, so this is about learning negative locomotion from egocentric vision. So, but how do we use vision? Now, the classic approach in robotics or in locomotion has been to use vision in a decoupled manner. So you take vision, you build a map using SLAM or some other approaches, and then you make your robot function in that mapping space. And these two phases are usually decoupled, sometimes learn end to end, but usually vision goes through this bottleneck of map in between. There are many problems with mapping, like you have noisy, there's multiple phases, you need extra compute, you need extra sensors to compute this map from all sides. But the bigger point is, this kind of mapping or this kind of explicit two-phase thing is not always present in biological world. In biological world, control and perception are tied together very, very coherently and very tightly. So these are what is so-called control perception loop. So for instance, this is a classic experiment and a very famous one from David Lee, I think 1974, where they demonstrate that when babies are learning how to walk, how tightly their walking is coupled to their vision. So they put child inside this room and they move the walls and the child falls without touching the wall. So that the child gets confused if the walls are moving and their vision causes their proprioception to fail and they fall in the scenario. Not just babies, like even in adults, it has been shown that control and perception are tightly coupled. Like for instance, when we hike, like how large will our step size be depends on where our gaze at. And people have done very thorough studies here as to how perception and control tied to each other. So our goal here is to basically make vision first-class citizen. Instead of going through this processing stage of vision and then doing control on top, you want to treat image as first-class citizen, and we follow similar approach as before. I'll not go into the approach, but rather go into the challenges. One of the main challenge with this robot is that this is a small robot. Okay. Now you may have seen robots from ETH lab on the left, Animal C, Spot in the middle from Boston Dynamics, and this is a small robot called A1 robot. So we have this robot here. So we'll show more demos in the break, but it is so small that you cannot see it from the back probably. So you'll have to get up to see the robot. We'll bring it closer to you, so the talk is still going on, but we'll show more demos towards the end of the talk. But the problem with this small robot is that it is very difficult to climb on stairs or difficult terrains because your legs and your body do not have enough gap between them. Okay, let me stop for a second. So this is running our controller from vision. Don't go too close because it will try to climb on you. It does not know yet about people, so it just tries to climb everything it sees in the real world. Okay. So we'll show a detailed demo in 15 minutes. Maybe we can stop here. Okay, let's continue the talk and then we'll show the demo in just 10 more minutes. Okay. Now, the difficulty with a small robot is that, as you can see in the figure, if you are trying to climb a stair, your legs may hit the stair. If you are coming down, you may topple because there is not enough clearance between your body and the ground. So you cannot adjust your leg. So no matter how good your vision is, your hardware is incapable of doing it. So what we found that if you treat vision as first-class citizen and learn with control, robot learns interesting behaviors to climb difficult scenarios. Since it's very small, it does not extend its leg in the way humans do, like in a cyclical manner. It rather extends it out, so abduction and adduction. So it extends the arm out to climb the stair like this because of size of the robot. And this is only possible because the vision was first-class citizen here. Okay, so here is an example of robot walking. You can see on the very top the depth image that the robot is seeing online. It's first-person view. And it can, it's very difficult terrain and again made in the whole setup. So even though blind walking can do very well, it will never work in scenarios like this. It can come downstairs but not go upstairs because to go upstairs you need to see where, how to move your legs, etc. Those who have been to Pittsburgh, this is Highland Park in Pittsburgh. You can see how high the stairs are compared to the height of the robot. The stairs are almost reaching this level of the robot. And this is vegetation where it gets stuck. That's why it's This is a pretty high slope, takes a while. So if you notice closely, the robot takes its leg out and brings it inside. Because the height is very small, it performs this adduction behavior to climb the stairs in this way. It turns out that it's not very easy to find difficult terrains in the real world. Like in this convention center, we had to spend 1 hour to find these scrapes here to make some terrain, and we'll make it after the talk. But we have been running around both Pittsburgh and Berkeley to find difficult terrains to shoot these videos. But just in the interest of time, there is more stuff here. So far, this was one task only. Okay, this was just walking. But the original goal I promised here is to go to lots of environments and lots of tasks, right? But how do we do such a thing for robots, like what we have done for deep learning in computer vision? How do we get data from lots of environment for lots of tasks? Well, it turns out it creates a chicken and egg problem for robotics. Like, to build robots that can work in lots of scenarios and lots of tasks, we need diverse data. But data will only be there when the robots can actually work in the scenarios and people can put them in their homes, right? But nobody wants a robot which does not work. So what do we do here? The solution is to use diverse data on the internet. So use data of humans doing things, which are lots and lots of things, and learn from them to perform robotics. So this is not imitation learning I'm talking about, where human helps control the robot to do things. It is learning by watching, like watching humans do things on YouTube, or even watching humans when they are not teaching you, doing some task of their own and learn from them and perform some task. So we want things on the right, not on the left, okay? But this creates many challenges. If you're watching others to do tasks, how do you sense the environment in 3D? How do you understand what the intent of the human was? And how do you manage embodiment transfer from this passive videos to robot's own body? Okay, like typically, how do we transfer knowledge from humans to robots is as follows. We use some sort of VR mechanism at the bottom, or we use these gloves, like this Jeff Bezos here is controlling these robots, I think at Mars conference or maybe somewhere else to bring this. But we want to use vision to go from YouTube, any person doing things, any camera, any task, any subject, and anywhere. And we want to transfer this knowledge to the robot in real time. Okay. So this is a system we call robotic telekinesis, where we go from all sorts of YouTube videos, we detect humans and how do they behave, their hands specifically, and we convert a mapping between human hand to robot hand and train this on the data. So here you see a training curve going through lots of human videos on the YouTube. I think these examples are from 100 Days of Hands and Epic Kitchen mixed together. And once you train this system fully on YouTube, you do not need a robot to train the system. Just for CVPR audience who do not want to work with robots, this is fully trained on passive data, and you can control these robots in the wild. But here, if you notice, you're copying the robot, and just copying is not enough. You want the robot to also function on its own and solve tasks. So this is where we want to bridge the gap between passive data and robot functioning autonomously. So this is called human to robot in the wild. So what we do here, we start from passive data on the internet. We use passive data to collect priors. There are a lot of works in CVPR, this CVPR specifically, where we are seeing results on hands, human movement, where you can extract priors from just a single RGB video as to how humans are moving in 3D space. We use that priors, and then we perform some exploration in the real world, because of course, YouTube video is human doing something, then the robot may fail in doing so. And then we transfer it to the policy of the robot. So here's an example. Here we collect, first we learned how to get priors from YouTube, then we see a person doing something here, and then we transfer, and the robot here is practicing on its own. It takes 4 or 5 hours of practice, and after some time, it can learn to open the drawer by using these priors from this data. Now, this method is basically learns in the real world in 4 to 5 hours. It does not require reinforcement learning, does not require imitation learning. And it is very easy to scale to lots of tasks in the wild in the scenario. So here there are 20 tasks or so we are doing across lots of environment. This was done during the time when there was snow in Pittsburgh, so we could not go outside CMU. So it's every CMU building we could take the robot to and shot this thing. You can do the same thing with Dexter's hand as well. So here there is robotic hand doing tasks autonomously without having the human there copy there. This is the end of the talk. Now what we'll do, we'll set up the terrain for doing some demo for the robot. And before I end, this is the work done by all these students, Ashish, Ananya, Zipeng, Shikhar, and Kenny, and advised by myself and Jitendra in the Legged Robot part. So with that, thank you. And I can take questions while we set up the environment. Any questions? Okay.
In one of the slides, you showed a comparison between a traditional controller and your vision. Do you mind telling me what's the controller that we use?
So this is the default controller that the robot came with. It is, I mean, they don't reveal it, but it is largely based on convex MPC controller from MIT Sang-Baekim's lab. But it relies on foot contact feedback. So there was feedback loss in the mattress, so it was failing.
Okay, so if it's a PID controller, then my understanding is that it's a simple feedback controller. What you are presenting to your algorithm is very much like adaptive control framework. Basically, you are giving the time series and construct a time series-based estimator, and on top of that, you have the controller adapting as well. And then you are giving different time horizon when you are updating your estimator and your controller. And I think this is very similar to some established techniques inside the adaptive control series. So do you mind explaining to me from the theory level, what's the difference between the existing technique and what you are doing in your theory that's making the difference between what's working and what's not working?
Yes. So I will just correct that it's not a simple PID controller, it's convex MPC. So it's like a culmination of lot series of papers over several decades. So it does take time series, etc. into account to compute the trajectory of the robot. So it is more sophisticated than just a PID controller. So that's one. But in some sense, I would not distinguish it too much from adaptive control. This is in some ways a learned version of adaptive control. So what happens in adaptive control is like you look at the history compared to robust control. You use the history to estimate some variable. Usually in robotics, it is the actual system parameters like physics, like mass, friction, etc. They are very hard to compute in the real world. Here, we do not compute those parameters. We compute the effect of those parameters because that latent vector is learned together with the policy. So it is only capturing what does the friction will affect, how it will affect the robot body while moving. You are not capturing the exact friction because that's impossible to predict from the history, the actual value of the system. So it works in like aeroplane case scenario where your system is in the mid-air with not much of contacts. But in case of contact, it's very hard to estimate the exact system parameters.
Okay, so my understanding is that the problem setup is different.
No.
I think that we have a much more general approach. So we know the adaptive control literature and we have applied this technique in other settings. And the setting where people have done things like L1 adaptive control and so forth, okay, for quadcopters. This is just like, I mean, why linear techniques get beaten by nonlinear techniques. It's like that. We are able to prove fewer theorems, but we have a much more adaptive system, much more powerful system.
I think that's a really fair point. I think that's why machine learning is an important technique, or not even new technique, important technique as well for the control community, where you can actually improve the amount of model, the capacity of the model that we are using. But on the other hand, I think it's also similar to what adaptive control has.
But it doesn't work as well. You have to have your choice. Do you want to prove theorems or do you want a system which works better?
Although we can prove theorems. In one of our recent work, we do have some theorem, if that helps.
I think one of the problems with adaptive control, or in general, this kind of nonlinear system where your estimation or perception and the actuation is coupled, where it's very likely that you are always hoping that your perception and your actuation is convergent, but it's also very likely because of this coupling, you are sometimes trapped or like misled.
I think it's a valid concern in most cases, but here the two-phase separation between the 1 and 2 phase, which I showed earlier, and I showed the examples, we do find that convergence always happen, and this variable is actually changing behavior to adapt the robot in different terrains. In the video I showed is kind of example of that. But two-phase training is basically to amount for this deep learning hardness of the problem.
Let's take this discussion offline so that we can have more questions. Thanks.
I just want to say the results are very cool.
Thank you.
It's very impressive. You don't show up at conferences with proofs. One question I have is, some of the problems you're claiming to solve seem to be self-created. So the height issue is because you're using this robot, which is a particularly profile. Are you thinking indoor scenarios where you cannot have a big robot, in which case people make an argument that Lego robots aren't safe around people when the power goes off, they'll fall, so lead systems will prefer. So what are you thinking about that?
So here the example. So there are two parts to the answer. One is that small robots are more preferable to be around human. I mean, that's because they are better and less. They cannot hurt you as much. But the other bigger reason is that the example I showed is all relative. Like for this robot, some terrains are harder. Like normal stairs are harder because it's a very small. But for a bigger robot, climbing a bigger stair is also hard. Like for a Boston Dynamics robot, for instance, climbing a very high step, it's a very difficult problem. In fact, if you look at their controller, you have to explicitly switch from walking to stair climbing mode, and it's a different policy because in that policy, robot does like this. So if you put a bigger stair which does not fit this clearance height, so that will fail there. So I think this is a relative argument I was making through this robot, but it's a more generic thing that whatever bigger robot you will have, at some point there will be a next thing which is harder for it. By treating vision as first-class citizen, these things do get handled very well compared to separating the vision out of the equation. Thank you.
Just one quick point. Since we're already in the break time and the next talk starts in 6 minutes, can we do the demo while he answers the question?
Yeah, sounds good.
Okay. So some people can take the demo and questions.
What would the baseline or catastrophic failure look like without your method for this robot if you were to, let's say, do too much work?
Correct. So I did not have time to put in the baseline as well because this paper was submitted just a few days back. But the baselines here are, for instance, you create a map or you don't have a vision policy, just a blind controller and go forward. I think the failures over there are kind of self-evident, like when that gap is very high between the stairs, the robot fails to put the step on the ground and just completely gets flipped all on its face. So blind policy can do very well in all these scenarios which have flat terrain or difficult terrain, but in like stairs or gaps or stepping stones, you need vision to account for it.
I was more so referring to the domains that you saw at the beginning. So, for example, like you had the robot learn simulation.
Correct. So we have many baselines. One is domain randomization, where you compare it to it. Second is explicit height estimation of the terrain in front of you. So there are many comparisons, very thorough comparisons in the paper, which.
I have one question. So, if you're learning a new task or if you're moving from one task, how does the robot remember?
Yeah. So currently there is no learning. It's adaptation only. So when we come to learning, where you actually change the weights of the policy, that would require handling, forgetting, and all those issues. So we are working on that. That's not part of the solution yet. It's adaptation only. Okay.
Hi, Nico.
Hello. Is it okay if we take questions offline? I can happy to answer them in person after the talk, and we can all enjoy the demo. Okay. I think we can make it more harder, like higher. Should we put more?
I think they're showing the
People also, they come in front of you. I think we'll do it all stairs outside. We just like walk it. There is also a poster on Friday. We have paper on how to combine locomotion with adaptation. We also have robotics. I don't have to control the yeah.
We're going to be mostly on the same laptop, so.
Yeah, we also have power. I thought I was introducing Derek. Hello.
Hi. You don't have to introduce me too much because I'm introducing the
Yeah,
session.
exactly.
Introduction.
I'm just going to say, like, professor from UIUC, like, going to talk about GPV, and I won't spill all the beans about the challenge, and then I'll hand it off to you.
All right. So next we have Derek Hoem, who is a professor at UIUC. And he's going to introduce a series of talks on general purpose vision and the grid challenge. So I'm not going to spill all the beans, and I'm going to hand it off to Derek to introduce next round of speakers.
All right, thank you. Just have to figure out, okay. So where does this, let me see if I can move this bar so that it's not like right in the middle of the title. Is that all right? That's fine. Okay, so computer vision has made a lot of progress in specialized models. And by that, I mean models that are trained to perform certain skills and concepts in certain domains. For example, something that can detect and segment the 80 categories on the COCO data set. And so now we want to build on that success to create more general purpose vision systems. So what do I mean by that? One aspect is generality of architecture, where we want task agnostic architectures that can perform a broad range of tasks, including ones that are not necessarily anticipated by the designers. So humans are an example of this, where we can learn to perform lots of new tasks without changing our bodies. Second is generality of concepts across skills and domains. If a system learns to classify something and it can detect and caption other things, then it should also be able to detect and caption this new thing that it learned to classify and apply that knowledge to related image domains. And then third is generality of learning. We want the system to be able to learn new tasks from non-experts who don't have any understanding of the underlying architecture or necessarily deep learning. And when it learns new things, it should do so without losing its existing abilities. So why do we want this? Well, history shows that when we generalize technologies, it exponentially increases the impact. For example, when we went from special purpose computers like tabulating machines to general purpose computers, it made it so that application engineers could create new applications without understanding all the details of the underlying hardware. That created an explosion of new applications, which led to the information age. We've seen this to a very small scale in natural language processing, where you can create sequence-to-sequence models that can perform many different tasks. Then came benchmarks like the GLUE benchmark and SuperGLUE to evaluate the broad capabilities of natural language processing systems. And that created some of the research framework that was necessary to further develop models, leading, for example, to GPT-3, which demonstrated effective few-shot task generalization. And then there's many startups in the last couple of years and many applications that have been built around GPT-3, doing applications that the original developers of GPT-3 had not envisioned. And so this leads us to GRIT. We created GRIT in part to be able to advance general purpose vision, to create a test framework that would be able to answer the kinds of questions that we're interested in looking at these kinds of generalization. And so Tame Gupta and Ryan Martin are going to present the GRIT benchmark. And then we're going to see presentations by 3 general purpose vision systems that evaluate on the GRIT benchmark. GPV1, that's presented by Amita Kamath, GPV2, presented by Christopher Clark, and Unified IO, presented by Jia-Sin Liu. And this last one is the first system anywhere that's able to perform all the tasks on the GRIT benchmark. Tommy. I'm not sure if you're sharing.
Yeah, let me do that. All right, you see it? All right, let's get started. My name is Tanmay Gupta. I'm a research scientist in the prior team. And today with Ryan, we'll be talking about the GRIT benchmark, or the General Robust Image Task Benchmark. So the goal of this benchmark is to evaluate general capabilities of a vision system. Now, as simple as that question sounds, it's not an easy problem. How do you evaluate a general purpose vision system? There are a bunch of tasks
that we study in the vision field: image captioning, visual question answering, visual semantic role labeling, depth prediction, image text retrieval. So which of these do you choose to include in a benchmark that is meant to evaluate a general vision system? So first of all, there's no single task that's good enough to evaluate the capabilities of a general vision system. So you need to include a set of them. And it's important to include a set that evaluates diverse set of visual capabilities. Now here, by diversity, I mean diversity of outputs. So you want to have tasks that involve class labels, free-form text, bounding boxes, segmentation masks, surface normals. You want to have diversity of concepts. So for now, think of concepts as nouns or objects in your images and input and output text. And we want to have diversity of data sources. Data sources are data sets, the image sources, and the annotations that come on top of it. And lastly, we want to only include tasks that have a clear and unambiguous task definition. So things like image captioning, which has a lot of feasible captions possible for one image and are difficult to evaluate, are not included in this benchmark. So here are seven of the tasks that are included in the grid benchmark. And these are categorization, localization, referring expression grounding, visual question answering, segmentation, pose key points, and surface normals. So as you can see, these span a wide variety of outputs. So bounding boxes, segmentation masks, key points, surface normals. And to participate in this benchmark, we have a set of training sources that you're allowed to train on. And these include multiple data sets and their various splits and annotations. So note that you're not only training on, for example, COCO segmentation and evaluating on COCO segmentation, but you're training on a bunch of different kinds of annotations from a bunch of different data sets, and you're doing multitask training, and then you're evaluating on COCO segmentation, for instance. So today, how do we do this evaluation of general purpose vision systems? We choose a data set for each task. For example, for segmentation, we choose the COCO benchmark. We train on that data set's training set, so in this case, COCO train, and then we evaluate on that same data set's test set, so COCO test. And this means a couple of things. First, we're assuming that the image distribution that we're going to see in test is the same or similar to the image distribution that we have seen in training. For example, in the training set, you might have horses that appear in a certain way, and in the test set, you have horses that appear in the same sort of way. The concept distributions are also similar and often identical in the training and test sets. So the nouns, adjectives, and verbs that appear in your class labels, question answers, or captions that you evaluate on test have all been seen in train. So what's missing in this kind of an evaluation? Well, in short, there are three things that are missing: generality, robustness, and calibration. So let us look at what these mean. So by generality, first of all, we mean generalization to new image distributions. So for example, you're training for key point prediction on certain style of images, but then you're evaluating on the same task, key point prediction for construction images, which are very different from what you've trained on. Similarly, we want generality across concept distributions. So you're training for concepts like giraffe, birds, and banana, and then you're evaluating on concepts like bagel, oyster, and golf ball, which haven't been shown to the model, or at least the segmentation data for those concepts haven't been shown to the model. Now you might ask, why do we even expect concept generalization? When you have never seen bagel, how do you expect it to segment out bagel? Well, so the subtlety here is that you're not allowed to see segmentation examples of bagels, but bagel might appear in training data for other tasks, and it might appear in pre-training data, for example, conceptual captions or visual genome. And that is what we refer to as transfer of concepts across skills. So you learn concepts from one skill and then apply them in context of another. We also want to evaluate robustness to image distortions, which is missing from current data sets. So you train on clean images, and then you test on images which have some kind of a noise or weather phenomena happening in them, for example, snow, frost, or fog. And finally, what's missing is evaluation of calibration and knowledge assessment. So in this relatively innocent example, a system has misclassified this image as a dog with 95% confidence, but you can imagine situations where systems are used to decide who gets incarcerated or who gets to have a particular job. And there, this confidence scores plays a huge role in decision-making and significantly impacts a person's life. So it's important to know when your model does not know, and it's also important to know when your model makes high confidence incorrect predictions. So to summarize, GRID is a benchmark of 7 vision tasks, but it also measures generality, robustness, and calibration on all of these tasks. So let us look at how GRID implements generality. So we want to evaluate generalization to novel data sources and concepts. So obviously we want to train and test on the same data source. So for example, we're training on COCO images for segmentation and testing on the same distribution, but we also test on new distributions, for example, open images V6. So note that you're not allowed to train on open images train set, but you're still evaluating on it. Similarly, for evaluating generalization to novel concepts, you're training and testing on the same concepts that you've seen in training, for example, COCO, but you're also evaluating on open images V6, which has a new set of concepts. And again, you want to learn these concepts from training data of other tasks or from auxiliary data sources like conceptual caption, visual genome, or Web10K. To evaluate robustness, we select a subset of images for each task, and then we add various perturbations to it. Now, these perturbations are sometimes noise, like Gaussian noise, short noise, etc. Sometimes they are weather phenomena, for example, simulated snow, frost, and fog. Sometimes these are things like JPEG compression. And we also have universal adversarial perturbation by which we modify your images. So on this subset of images, we have 20 distortion types that are applied, and there are 5 intensities for each distortion type that we provide to you. And then the performance is reported with and without distortions on these samples. Finally, to measure calibration, we require models to produce a confidence score along with the predictions. So confidence score is supposed to be the model's belief of how accurate it believes the prediction to be. And AI here, for example, is the accuracy for the ith sample, and CI is the confidence score that goes between 0 and 1. And we have various measures that are defined that assess knowledge and calibration. So for example, misinformation is high if your model produces highly confident, inaccurate predictions. So it's CI times 1 minus AI, and then you average that across all samples. Similarly, for calibration, we report self-awareness and RMSE. So self-awareness score is high if your model produces higher confidence scores for more accurate predictions and vice versa. And RMSE is better when it's lower. So RMSE is defined as your model produces confidence scores that are reflective of its accuracy. Now, Ryan will tell you more about the tasks, input, outputs, and accuracy measures.
So as Tommy mentioned, we selected 7 diverse and representative vision tasks spanning recognition, vision and language, and 3D vision. So I'm going to run through here our definitions of these tasks. Some of them you may be familiar with, some of them may be new to you. The first task is object categorization, which involves an input image and an input bounding box. The output is expected to be a text label for which the bounding box describes the region in the image. So our metric here is 1 if this label here, drill, is the correct ground truth label, or 0 otherwise. The next task is object localization. We define this as taking an input image and an input text, which is the objects that you want to localize. The expected output is a list of bounding boxes, 1 for each instance. As you can see here, we have a different bounding box for each kitchen and dining room table found in the image. The accuracy metric is computed by first matching boxes in the predicted output and the ground truth output. We do this by maximizing the overall intersection over union using a Hungarian matching algorithm. And then the final metric is the sum of these intersection over unions divided by the number of predicted boxes plus the number of boxes that are missed in the ground truth. The segmentation task involves an input image and an input text, which describes the objects in which you are trying to segment. The output are a list of masks, which we are representing in this compressed format called run length encoding. And the accuracy metric is very similar to the last task. Instead, here we use boundary intersection over union, which takes the boundaries of each of those predicted in ground truth masks for the matching process, and then also for this final sum. The referring expressions grounding tasks involve an input image and input text. And the goal is to output a single bounding box, which describes the region of the image that relates to that input text. So here, man on the end, black suit, and as you can see, the boxes around that man. The accuracy metric for this task is 1 if the intersection over union is greater than 0.5 and 0 otherwise. The visual question answering task involves an input image and an input text describing a question. The output text is the answer to that question, and the accuracy metric involves first matching that output text answer to the reference ground truth annotated answers. And if there are more than 3 matched answers, then the score of 1 is awarded. Otherwise, it is the number of answers matched divided by 3. The key point estimation task involves an input image, and the expected output is a list of key points for each person instance found in that image. And there are 17 key points per person. There is the ear, nose, right shoulder, left knee, all those. The accuracy metric is based off of the object key point similarity. So for each one of those 17 key points, this score is calculated with the following equation here. And then that is averaged over all 17 key points in an instance. And then once again, to get the score for the task, you average that over all instances in the image. The surface normal estimation task involves an input image and expects output normals, which we are representing as an RGB image. So for each pixel location in the input image, we want a 3D vector output. This 3D vector is converted to RGB by normalizing and shifting and scaling. To compute the score for this task, we first conduct a global rotation to find the best match between the predicted normals and the ground truth normals. We do this so it is agnostic to the coordinate frame of which is predicted. It can be in the camera or the world coordinates. The final metric is the percentage of normals with error less than 11.25 degrees. So after describing all that, it would be good to know when and how to use the GRIT benchmark. So GRIT is really good because you are able to answer a bunch of valuable research questions that would be pretty difficult to do on your own. So if you've ever wondered, how accurate is my model on novel image sources? Or how well does my model perform on novel objects? What concept groups are most difficult for my model? How robust is my model to image distortions? Each one of these in itself is very valuable. The great thing about GRIT is that you get to answer all these questions at once. And how do you do that? Well, first you generate predictions on a test or ablation set, and then you upload these predictions to our leaderboard. The evaluation server will evaluate all these predictions and produce over 500 metrics, which you can view on the leaderboard. You submit once and you can answer many of these research questions all at the same time. So to actually answer those research questions, we have devised this flexible query format. So here we have an example, how robust is my segmentation model to image distortion? And you're able to use this expression, which we've created. So first you pick the measure, which is accuracy here, then the concepts you want to evaluate across, we're just allowing any, and then the partition. So we're interested in image distortion, so we're looking at the distortion partitions. And lastly, we specify the task as segmentation. We input this into the leaderboard, and we're able to filter out just those 3 metrics, which answer our question out of the large amount of metrics produced in the GRIT benchmark. And you can see here, we actually have some data we can answer this question for mask RCNN, which on an undistorted set achieves a GRIT score of 40.6, and on a distorted set achieves a score of 18.7. You can see the delta is 21.8. So we were able to answer that question. Additionally, GRIT has 2 competition tracks. There is a restricted track and an unrestricted track. The restricted track involves only training on a specified number of data sets. So these data sets are listed here below. And this track is good if you are interested in data efficiency or comparing between models which have seen a similar amount of data, or if you are interested in leveling the playing field when it comes to computational resources. The unrestricted track allows you to train on any data except for the data that is used to evaluate the GRIT tasks. And you might want to use this track if you want to work on very large scale foundation models, if you really want to work on scaling compute and data sets. And lastly, if your model has a component in it which has been pre-trained on data that is not allowed by the restricted track. So for example, if you use a clip image encoder, you would want to submit to the unrestricted track. Lastly, I want to point out that we have a submission frequency for the leaderboard. So the grit ablation leaderboard lets you submit as many times as you want, so you can try out all the variations of your model, and these can be private or public. Now, the grit test leaderboard only allows you to submit once per week, and these submissions must be made public. So Tame now is going to talk to you about the results of the grit benchmark so far and what it says about our current state of computer vision.
All right, so far, we have had quite a few submissions on the ablation unrestricted set. And many of these have actually been created by us as baselines to serve for future submissions. So we have, for example, for classification, clip-based methods. We have surface normal prediction model to serve as a baseline for you. We have mask arsenal for localization, segmentation, and key points. We have a few GPV models, which you're going to hear about next, GPV1 and GPV2. And we have an external GPV model or GPV-like model called OFA, which we validated on grid ourselves. And finally, we have unified IO, which is so far the only task that can do, only model that can do all of these 7 tasks. And it has been trained with 3 billion parameters and it's trained on 80 data sets. So it's a pretty powerful model, and we'll hear more about it from Jiasun pretty soon. So overall, the trends have been as follows. As the amount of trained data and model sizes increase from GP1 to 2 to unified IO, generality and robustness have improved across tasks. However, it is interesting to note that unified IO, even though it's more general and robust, its calibration is the worst. So here we are reporting root mean square error, and lower is better. And unified IO has the worst calibration out of all of the other models. So this is just something to highlight that there's still a lot of room for improvement on this benchmark. On the restricted set, we have had relatively fewer submissions. And the gains on the unrestricted set seem to come largely from bigger models and more trained data. So our request is that if you're looking for more control of the trained data set size, use the restricted set because it's a better benchmark to evaluate better architectures or learning methods. Here are some of the kinds of insights that you can draw from the restricted evaluation. So here, for example, we're reporting numbers on the same source on top and new sources on the bottom for each task. And we find that across all tasks, except for key points, there's a drop in performance when you go from same source to new source. Similarly, for same concepts, we find that generally the performance goes down when your model hasn't seen a concept in training. And we also see drop in performance and significant drop in performance due to distortions. So with that, here's the link to the grid benchmark. You can go to grid-benchmark.org, and there's more details, including leaderboards and things like that. Now, Amita will tell us more about GPV1. Which one was it? Okay, let's start. Yeah.
Thanks. Okay, hi everyone. My name is Amita. I'm a pre-doctoral young investigator at AI2. And today I'll be presenting GPV1, which was joint work led by Tanmay Gupta in collaboration with myself, Ani Kambhavi, and Derek Hoyam from AI2 and UIUC. So we heard about general purpose vision and what we're trying to aim for, but to make it more concrete, I'm going to talk about the different tenets that we put down. And as I talk about each tenet, I'll talk about how we made progress towards it with our first installment of GPV, which was GPV1. So the first tenet is generality of architecture. Now, what does that mean? We propose that a general purpose architecture supports learning a wide range of tasks within a broad domain without requiring any change to the architecture or learning algorithm. So we put down GPV1, which is a task agnostic vision language architecture. Now, this means that it can be trained on any task that takes in an image and a natural language prompt as inputs and outputs a text and bounding boxes. text and or bounding boxes. So for example, if I have an image of a cat and a dog, and I say locate dog, it's able to return a bounding box around the dog. If I say generate a description for the image, it gives back a caption. So to kind of demonstrate the generality of the architecture, we train on 4 different tasks: localization, classification, visual question answering, and captioning. We use Dieter's Hungarian matching loss to supervise the bounding box and relevance heads, and the negative log likelihood with teacher forcing to supervise the text decoder. So a little bit more about the architecture. Our image and text encoders are based on Dieter and BERT. For cross-modal fusion, we have Wilbert's co-attention module. And we have modality-specific decoders for the bounding box, region relevance, and freeform text. Now, what's very important is that these modality-specific decoders are reused for any task that uses that modality. So for example, VQA, captioning, classification, all reuse the freeform text decoder. The second tenet is generality of concepts across skills. So we say that a general purpose architecture can perform tasks in skill concept combinations not seen during training. So very briefly, what skill concepts mean. For now, we'll take skills to mean different tasks like VQA, localization, and concepts to be nouns, verbs, adjectives. So what we're saying is that if you can do VQA for dogs and localization for cats, you should be able to do VQA for cats and localization for dogs, even if you didn't see the latter two in your training explicitly. So we hope that your model is able to pick up concepts in the context of one skill and apply it to other skills without needing training data for them. So to kind of evaluate this, we created a new split of COCO called COCO Ski for skill concept evaluation. And what that is holding out some skill concept pairs from the training data and then explicitly evaluating on those at test time. So we retrain some specialized models on just the seen skill concept pairs and then evaluate them on both seen and unseen, above and below. And you can see that these models perform very poorly on skill concept pairs they have not seen before. With our model, GPV1, we train it again only on the seen skill concept pairs, and we evaluate them for now trained on each individual task. And we perform quite similarly to the specialized models. However, when we do joint training across all 4 tasks with GPV1, we see very significant gains, especially on the unseen skill concept pairs, which means that we're able to do the skill concept factorization to combine knowledge and use them across different skills. The third tenet of GPV is generality of learning. What we mean by this is that a general purpose architecture can learn new tasks with minimal loss of performance on previously learned tasks. So to evaluate this, we look at referring expression grounding, and specifically the zero-shot task performance on this. So GPV1 that is trained only on localization gets about 34% on Ref COCO+, and GPV1 trained on all 4 tasks gets 43%. And this gain comes from learning about adjectives, learning about different concepts from the different tasks that are seen. And these numbers are pretty good. So for example, we're able to draw a box around the right dog when asked for visible dog, or for red across the nose, along with some interesting text outputs. In the paper, we also show that multitask training leads to better learning efficiency and robustness to forgetting. So what are the limitations of GPV1? The first is that training is limited to only 80 COCO categories. So for example, if you give it a picture of a monkey and ask it to describe the image, you get an output, a bear sitting on a tree branch, which is like the nearest neighbor COCO category to monkey. So you can't really blame the model because it's never seen the concept of a monkey, but ideally you would like a larger training set. So we've expanded this to over 10,000 concepts using web data in GPV2, which you'll hear about from Chris. Evaluation is also currently limited to 80 COCO categories, and this is expanded to over 500 in the DCE benchmark, and of course, further expanded in GRID, which is what you've been hearing about today. So results on GRID for GPV1. GPV1 is able to compete on 4 out of the 7 tasks, which are categorization, localization, VQA, and referring expression, which, to stay true to the paper, is still zero shot here. We're currently #1 on the restricted leaderboard, and number 3 on the unrestricted leaderboard. And here are numbers, but it's clear that there's still room for improvement on restricted. So with that, if there are there any questions? Okay, I'll hand it over to Chris to talk about GPV2.
Oh, yeah. I thought it was just.
You said it was flat, right?
Yeah, but I should. Yeah. Okay. Hello, I am Chris Clark. I'm a research scientist with Prior, and I'm going to present GPV2, which is our successor to GPV1. So the main difference from GPV1 is we've scaled this model up, and in particular, trained it on many more concepts. So we used web unsupervised data to teach it about 10,000 concepts. We've also done some other improvements like improving the model, and we have a different evaluation framework so we can evaluate across these 10,000 concepts. So as before, the main goal here is to learn about tasks from data like COCO, so that can teach us how to answer questions or localize things or write captions. And then learn a large number of visual concepts from unsupervised web data. And then in theory, if our model can put these two parts together, it can solve a lot of different tasks with a lot of different concepts, and we'll end up with a very general model. So the web data we use is going to be web search data. So this will be from typing search queries into Bing search engine, and that'll give us a large number of examples of the thing we queried for. So why are we using web search data? There's a few advantages compared to, say, using a corpus like conceptual captions. One is we can get really good coverage of tail concepts, since big image search will give us quite a few images, even for relatively rare or not talked about much things. The web search images we get are also usually good quality. They're centered and cropped and give us a very clear picture of the concept we're looking for. And an interesting one that relates to some of the continual learning that's been talked about here is that if we can train these models on images from Bing web search, then as new concepts change or new concepts appear in the world, we can use search to retrieve them and then update our model of these new things. So we can keep our model updated with new trends. And we did do a study in the paper showing that the data we can get from this has better coverage of tail concepts than conceptual captions, but I'll leave the details out. So using this, we build Web 10K. This is a data set of concepts and images. We built a list of 10,000 nouns from various sources of plain text. And then we can search those nouns to get images from Bing search. Our notion of concepts also extends to verbs and adjectives. So to get information for these, we pair our nouns with verbs or pair them with adjectives and issue web searches for these compound queries. And that gives us images for things like buffalo plowing or modern armchair. That gives us information about adjectives and verbs as well as these nouns. And the great thing about this is it's very cheap. So this was only $150 to get nearly 1 million images to train on. So when we have these images, we're going to multitask. We're going to train our model to do VQA questions based on these images. So generally, the simplest thing to do is to just ask the model, what is in this image? We have some slightly more interesting templates where we ask our model kind of what is the verb or what is the adjective that the image is showing as well. So with these templates, we get a total of 3 million question answer pairs. So now we have a source of web data. We also have a new model. I'll go through this quickly, but we're going to use the VinVL object detector to get features for different regions in the image. We'll use the T5 word piece tokenizer and T5 embeddings to get features for any text input, like the question from VQA. These features get put together as one sequence, and then we'll encode it with the T5 encoder, and then decode with the T5 decoder to generate free-form text. So this ability to generate text is what we use to do things like generate the answer to a question, or generate a caption, or generate a class name for image classification. We do 2 additional modifications. So we also allow the user to input a bounding box to tell the model what to focus on in the image. And for this bounding box, we just extract features with the same pipeline and then add a learned embedding to it to distinguish it from the other features. And then we also want the model to be able to select bounding boxes to return as output. So to do this, we have a trick where we use the bounding box features as input to the T5 decoder separately. And then we can decode there to get some kind of text output for that specific box. So we can do that for like object selection, where we decode from the box, and if it decodes a class name, we can then return that box as being relevant to the query. So to evaluate this data set, it would have been nice to use GRIT, but this came out a bit before GRIT. So we evaluated it on DCE, which is kind of a GRIT 0.1. This contains 5 different tasks. And in particular, these 5 tasks are all drawn from data sources that are not from COCO. So they're all built to have concepts like tricycle or gondola that rarely appear in COCO. So to do well on these tasks, the model needs to learn what these concepts looks like from the web data, and then combine that with knowledge of how to do these different tasks that it learned from any COCO training data we have. So I'll show ablation results on this set. Here I'm showing training GPV2 either just with the COCO training data or multitasking with the COCO training data we have for these tasks, plus the Web 10K question answer pairs. So here we see a pretty significant gain in performance with the web data, especially with captioning and classification, showing the model was indeed able to learn from the web data and apply the knowledge it learned from that to these other tasks. We did some experiments with other models. So BLT5 is a model from prior work. And we went back and tried this with GPV1 as well. We generally see the same trends here. So using web helps the model generalize on this outer domain test set that contains new concepts. And then we did submit this to the GRIT leaderboard once the GRIT was ready. And for a little moment, we were the first entry, but now Unify has passed us. We can do 4 tasks here, but we can't do some of the like pixel classification tasks like segmentation and surface normals. And I'll finish just by showing some qualitative examples. So here I'm showing in green what the model predicts when it's trained with the web data. And in red, I'm showing what it predicts when it's trained without the web data. So we see, for example, in VQA, the model with web can correctly understand the woman is wearing a sari, but the without web model just guesses scarves, because that's kind of the most similar thing it's seen in the COCO data. For captioning, we've often seen the model trained on web data able to give a more specific kind of caption. So here it's able to name a blueberry muffin, where the without web model ends up just producing a very generic caption. And then I'll share one more qualitative experiment we did So we were interested in testing GPV2 if we trained it on some kind of new concepts that are so new they might not appear in static corpora like conceptual captions. So we gathered a bunch of data from COVID-19 concepts like masks or vaccination cards that only became prominent in the last 3 or 4 years. And then we did web searches for these queries and trained our model with this new data, the web search queries. And we were able to find that the model is able to learn about some of these new concepts. So for VQA, the model understands that this is a vaccination card. And for captioning, the model can identify this as a KND5 mask. And that's what I was saying for GPV2. There's a paper, a demo, and code available here. Thank you. Yes.
First question is, if you want to extend your method into UDS, not easy to create that web search web and transfer to what's the plan to like generalize.
So a new data set, like a new task.
You want to make it more scalable, not only the API side of code. Yeah, new modality of data set, new kind of tasks, how to make it more general.
Yeah, I mean, really that requires a fundamental change to the model. So the model here can produce text output. So if the new task just requires generating text, we could just train the model on the new task. If the model requires some other kind of output, we need a different design. I think Unified IO, which is going next, has exactly such a design that can train on more tasks.
Yeah. The second question is, if the cross task they have no class for that. For example, you mentioned if I can answer the question of the log, I can directly I can look that, right? But what if I can answer? I know there's a few of them. I use this knowledge to look like other objects, or there's no overlap with the class.
Sounds very difficult. Although our assumption is you use web search data like this, you should be able to get some kind of image for pretty much any concept. So you should always have at least some signal to learn what these different concepts are.
Yeah, another question is how to distinguish this method with continual. I think GPU1, you show the table from the task-specific model, show better. So I can also do one thing like I use a pre-train clip and backbone repetition, and only change the headers. Right? I think this is also not that hard cost because I only need to change the header. Right? What the main difference of your general structure and this continual transfer level?
Yeah, I think there's two big differences. So one here is we share all the parameters between the model. So there's no task-specific heads. For some tasks, that might not seem like a big deal. So for like classification, you just need a small linear header. For other tasks like object detection, you probably need a pretty substantial head on top of whatever backbone you're using to actually do the task. So that means you might need quite a lot of parameters there that aren't getting shared well. Yeah.
So have you tried to compare with other baselines? So I was trying to figure out the main contribution from if you have a new version of data set, you have a bunch of new labels to do this one-task learning, or your model itself is. I would try to also do multi-task learning, but use different structure, like general C and test like that.
Yeah, I mean, we picked this model mostly just as like a strong kind of example of what these multi-task models typically look like. It does have some novel components like these box selection methods. And I mean, as I showed here, we did try several other different models. And again, our kind of main interest was just trying to show that when you do this multitasking scenario, the model can learn these new concepts from the web.
Cool. This is Justin. So I'm currently our work on VPLOW. This is a joint work with Chris, Joan, with Chris and I. So grid has benchmark. Grid benchmark is very challenging. Right? So as you heard from the prior talk, it requires 7 diverse skills for a single model. So most of the existing models can handle the 4 tasks, which usually involve sequential task objects. And the last 3 tasks are more challenging, which require the models to produce prefixal labels or complex structure objects. So what we want to build is modern growth. So we want to support massive tasks, such as like image generation, editing, text estimation, relation detection. Sorry, there's syntax slide.
The green one.
There's a green button.
Sorry for that. So what we want to build is modern growth. So first, we want to support massive tasks, such as image generation, editing, text estimation, and image captioning, and also like those penalty tasks. And second,
Share the whole screen. Yeah.
and okay, no, yeah. So and the second is we'll get rid of the task-specific tags. So we'll
Okay, yeah, it's really hard to see the screen from here. So, and yeah, so the last one I want to do is too easy to scale up. So the models are driven by natural, so that it can be benefit from the large amount of labeled and unlabeled data. Such a model performance can scale with the parameter size. So we have two main motivations for this model. So first, if a model can learn to generate images such as STAR-D, it should be able to solve any semantic vision task. And second is we want to converting vision inputs and outputs into sequences such that we can train them jointly. So let's look at the image output quantization first. For tasks with image output, such as image generation, segmentation, and depth estimation, so we use a pre-trained VQVE encoder to encode the target with a sequence of tokens. Then we can decode the VQVE decoder to decode them into a target output. Note that the VQVE is shared across all tasks. So what if we have multiple targets? For instance, we want to segment the image. Given this image, we want to segment the giraffe out. So given a bunch of binary masks, we map them into a 3-bit color space. And then we can map the multiple target back with post-processing. So for tasks with 1D structure outputs, we can compilate them with coordinates locations, such as pixel to sequence, and converting them to a sequence of tokens. For example, for the object detection and post-estimation, we can representing them with 2 tokens, such as the X and Y, and the bounding box represented by that. Then we can post-processing to map it back. So for post-estimation, there are 51 points per person. So, and the sequence length will be too long if there are multiple people. So we take a bounding box as input and detecting 1 person each time. Then we can casting this human post-estimation problem to detection plus single human estimation. So note that this 2-stage is also done by the same model. So we use a prompt-driven task specification, such as the characterization is what the characterize of this region and given the bounding box location, and the answer is a hot. So you can see that the left and right is the ground truth and the prediction outputs. So here are the prompt for 7 tasks of the grid. So the same model can also do image generation and semantic-based image generation, and also the image imprinting, depth prediction, and a lot of NLP tasks. So let's look at the model with a little bit more details. Given a target mask, we use VQGAN to convert them into sequence. Given the image and text input, we convert them, use the input embedding, and use a simple thing like cache embedding. And then we use an encoder-decoder framework to produce a discrete output sequence. And we further decoding the image and text target from these discrete tokens back into the original space. So during training, we use a discrete sequence as a target. And the VQGAN encoder and decoder are frozen and shared across the diverse different tasks from the dense vision output. So here are some more details of the model. So we follow the T5 implementation with a minimum modification. So we use a pre-trained VQGAN from ImageNet, and we use patch encoding for image input. So there's no INT involved in this architecture. So we're adding this absolute position encoding, which is important for vision. Basically, we are injecting the position embedding at the input. We're also extending the relative position encoding from text to image. So basically, is that given the 1D thing, we are extending to 2D. And we have a fixed bucket of learned parameters here. So our training has 2 stages. During pre-training, following T5, and we are doing this text span denoising task. So, for example, given this image of something is lying on some tokens, and the target is to reconstructing these tokens. And for the mask image, we're using this mask image denoising task for image output. So basically, given the image, we randomly masking 75% of image, and the target is to reconstruct it. So note that it can be either a single test or single image, or from a multimodal data. So we have the second stage is multitask training. So we joint train with around 80 vision language data set, and during this phase. So our task consists of a diverse set of these different tasks. So for vision tasks, we have a list of tasks like image classification, detection, segmentation, depth, surface normal, pose. And for vision language tasks, we are adding basically this captioning and also VQA, like all of these available. And language tasks, we're also picking a bunch of them. So basically the goal is to gather all of the possible public open source data set to test the limited of this unified model. So here are some details of the data sets and implementations. The first data set is critical to train these foundation models such as DARDI and CLIP, and those data are not public. So we construct our own data set to ensemble existing open source vision language, and language data set, such as open image and ready captions. And our data amount is about 60 million, and they are around 7 TB kind of size. So in terms of implementations, our total vocabulary size is around like 50K, and there's 1,000 location tokens plus like 16,000 like vision tokens. So we have trained 4 models: small, based, large, and extra large. So extra large is around 3 billion parameters. So we're using indexing mixing, which is basically kind of like depending on the output has. So basically, like we are dividing the task in the which head is using, and then like for a batch, we are mixing them with this kind of ratio. So each data set is sampled by its data size, and we are using the temperature scale mixing with T equals 2, basically to making the lower frequency data more visible during training. And our image resolution is this. So basically, during pre-training, we are random sample 128 patches and 256 for multitasking. So let's see some results. So, okay, this is a result for Unify IO on the grid leaderboard. So we can see that we're increasing the grid result from 32% to 64%. And our unified model achieves a state-of-the-art performance on 5 out of 7 tasks. So I think it's mainly due to our large-scale pre-training. And on the key point and surface normal task, we are around 2 points behind the mass RCN benchmark. And so there are mainly 2 reasons. First, we are a cascade system that we are doing detection first, and then we are doing this key point estimation, right? And second, our model predicts 0 when the point is masked, which can cause a large error during evaluation. So we are around 6 points behind of the surface normal state-of-the-art model. And the main reason is that VQ GAN is only trained on ImageNet. So there are kind of decoding errors here, and the resolution is fixed of 256 by 256. So our model scale well with parameter size, right? So they are around 20-point improvement from a small model to XL model. Here are some more summaries. So first, we propose Unify IO, which is the first framework that can handle massive vision language and language tasks. And second, we treat 2D images task as a conditional image generation task. Third, we use a pre-trained VQ GAN to convert image into sequence tokens and join train with language tokens. And we will release a code plus pre-trained model maybe in the coming months. So here are some acknowledgements. So this research was made possible by this cloud TPU from the Google TPU Research Cloud. And also, we would like to thank to the Google and Jack's T5X system. They have building amazing libraries, and also these grading demos from the AI tool release team. So here are the demo page, and you are welcome to see the kind of the demo here. Thanks.
All right, or go on Zoom. Okay. All right, I'll introduce myself. I'm Abhinav Srivastav. I'm a restart sharing. Move this guy. Yeah. Okay. No. Stop sharing. Stop sharing. All right. Good. All right. So I'm Abhinav Srivastav. I'm a professor at assistant professor at University of Maryland, College Park. So we are going to move into the session of object class discovery. We had a teaser challenge at this workshop, which is basically an in the wild object discovery benchmark, which was primarily led by Pulkit, Anubhav, and Saket. But before we go into detail of what the challenge was, I wanted to go into a bit of a history of why we are drilling down into this one topic and why we designed it the way we designed it. So first I'll talk about why we are reviving this object discovery in terms of its definition, how did we come here, and where are we going next in terms of where should we go next. So if it was not clear so far, the talk is about object discovery, and it's a fairly generic setup. Given a bunch of images, the goal is you want to extract objects and associate with all these different boxes with each other, and such that you're able to group them together and say that box 1 is object 1, box 2 is object 2, and so on and so forth. Now, generally, there is no way to actually say that we have found a cat or a dog without any text annotation or using caption data or something like that. So the best you can do is call this, we found category 1, category 2, category 3, so on and so forth. And then you can do some post processing Hungarian matching using test set to finally evaluate your models or train detection systems. Okay, so this problem is generally called object class or object category discovery, that you have to discover the object class or a category of objects. Now, the general framework for this, we'll first cover classic works of where we are, like how did we come here, what are different approaches to solve this. Then I'll go into a little bit of a segue or a rant about why is it not fashionable anymore, right? Like why did people stop working on it, or what are different things that people started working on that side sort of muddled the definition, and people can disagree with me on this part. All right. And the next, I want to talk about some benchmarks. So we propose a benchmark, and this teaser challenge was a simplified version of that benchmark. So I'll go over some detail of that, why that was interesting, what are the characteristics of that benchmark. I'll briefly mention some very simple baseline frameworks and point you to some papers that you can look at in this space. Okay. All right. So in recent memory, this started with, again, recent memory includes pre-deep learning works. This started with this series of work on unsupervised object discovery, one by Brian Russell and the other by Henry Kong. So the goal was, given a set of images, they segment out different regions, they associate or cluster those regions together, and then they say that this one group corresponds to one object. So for example, on the left image there, you see you have a bunch of trees segmented together, a bunch of bikes segmented together. On the right, you have a graph across all segments, and you're finding connected components in the graph to discover laptops and mouse and mug and so on and so forth. So this is how unsupervised object category discovery started, right? Then a bunch of work led by Christian Grauman and Yongjae Lee's team sort of moved into knowledge-driven object discovery, which assumes some sort of prior knowledge. And what they mean by prior knowledge is you know about some objects a priori. So suppose you know about, you have detectors for sky, house, grass, driveway, and so on. You look at a region and you look at a structure around that region in terms of these known classes, and then you say, I'll make a feature descriptor out of that. And you discover those individual things as objects. So in this case, you discover these mailboxes as new objects based on the context of knowledge around, known knowledge around those objects. So this was what I categorize as these knowledge-driven object discovery works. Then we made a big shift, and there are two main directions that moved here. One of them was from our lab at CMU, led by Xin-Le Chen, and the other one was by Mickey Rubenstein and co-authors, which was doing this object discovery tasks, but in internet images. Now, whenever we move to these internet images, the problem was a lot of these models were dealing with canonical images, and a lot of these methods ended up being co-localization, co-segmentation methods, and so on and so forth. And what I mean by that is, you'll pick a term, say car, you'll search Google for that term, and you can search Google right now for that term, right? And you'll see the images, and you get a lot of these canonical style images, where you have nice fancy sports cars, nicely rendered cars, and you have some noise images in there, some indoor cars, some wheels, and so on and so forth. And the goal is to take all those images together and discover the common object category in them. And that's the car segmentations that you see there, right? So this is sort of a co-segmentation, co-localization problem, that given these set of images, tell me what is common in these set of images, and that's my output. So this co-localization, eventually we started using other data sets for it, and then we started calling this the object discovery task. So this discovery word was kind of co-opted by this co-localization task, where we had a bunch of works where we took Pascal images and did co-localization between two pair of images, found out what is common, and then discovered them, and so on and so forth. Okay, so I call this multiple personalities of object discovery. So we started with an unsupervised object discovery set, which was basically a clustering problem or segmentation problem in image space. Then we moved into adding more external knowledge to that object discovery task. And then suddenly, with the access of so many internet images, we started adding internet images, which were very different from the distribution of images from our data sets. We had canonical images. We started doing weakly supervised stuff, because you have Googled the term car to find those images, so you know there are cars present in those images, right? And we moved algorithms from the segmentation style algorithms or clustering style algorithms to more co-localization and co-segmentation style algorithms. And I'll show you an example of where these kind of things fail. Then we again started calling these methods object discovery. We did some unsupervised things in there, but primarily everything still remained co-localization. And currently, before some of the recent works that we did and some other groups did, object discovery was this internet image or Pascal VOC style object discovery, but still deep features, but still the flavor of co-localization. So my personal opinion is that this is where we sort of lost our track, right? Before this, we had this bunch of images. We wanted to discover these object clusters and so on and so forth. And after the start of using these internet images, we sort of converted into a co-localization, co-segmentation problem. And where that comes to bite us is if you look at these images on the bottom right, you have the same image from Pascal VOC, right? And if I give you another image with a person in it and ask you to discover object, you'll discover these people, these two person in these two images. And if I give you another image with a bottle, you'll discover these two bottles, right? So the goal of all these co-localization or a high level bird's eye view of all these methods is consider all pairwise combinations of images in your data set, and you can potentially discover whatever is common between them. Now, things don't scale as well, because if you have two images with people on bike, sitting on bike, then that whole thing becomes one object. In general, doing these pairwise comparisons is not scalable, and so on and so forth, right? So that's one issue. The other is the sort of metrics that these sort of algorithms and these sort of benchmarks afford us. So when we are on the left, our metrics used to be the quantitative metrics were this precision recall curves or purity recall, purity versus number of clusters, purity recall curves, and so on and so forth. And then we had qualitative results. So one of the problems on the left side was they didn't give you one number that you can compete on, which our field loves, right? On the right, people kept coming up with new metrics, which are more suited for this co-localization task, like correct localization or call lock, correct detection or call debt, detection rate, and then there is precision checkout for the segmentation one, and then they have qualitative results, right? And these metrics that became so popular that your reviewer too is going to come back and hound you about deserves a slide of its own, that these are all broken when it comes to the task of object discovery. And I'm glad with for the grid talk, like the kind of metrics that you guys are talking about is sort of the metrics that we were getting into when we were trying to decide what should metrics for object discovery be. So we will come to some of the metrics later. So, okay, so the current set of metrics. So correct localization basically says percentage of images where any single object is correctly localized, right? So given an image of this room, if you recognize one person correctly in this image, we'll call this image as being correctly localized. So usually you'll see numbers in between 94 and 95%. no matter how good your discovery task is on some very challenging benchmarks. Correct retrieval, just mean number of k nearest neighbor that come from the same class, right? Detection rate is just a fancy word for standard recall measure. I don't know why people need to invent new terms for this, but anyways. So, okay, so we have core lock and detection rate. Again, they test co-localization capabilities. And I don't blame them for using it because they're using co-localization methods. They test co-localization capabilities, but they are not really object discovery metrics. Then you have correct localization or correct retrieval, which basically assumes that you have only one instance of object per image, right? Or one object per image. And then you have detection rate, which is essentially recall of underlying region proposal systems. So what ends up happening is a paper will come out and say, oh, this is our detection rate, and see this detection rate is so awesome compared to all the previous methods. But it'll turn out that they're using RPN as opposed to selective search, and all the difference that is coming from that RPN. Right? The number or detection rate is exactly the same as RPN detection rate. So, so those are the issues with these sort of metrics, right? Next pet peeve with these multiple personalities is data sets. So back in the day when we were doing those kind of things, we were doing Caltech, ADL or activities of daily living, MSRC, label me, and so on and so forth. When we started doing these internet images co-localization tasks, we started with the internet images dataset, which was the Mickey Rubinstein dataset, which was a co-segmentation dataset to begin with, and then it became a discovery dataset. And then because that was not satisfying enough, we took Pascal, and then we say, oh, we'll take car and only left-right flips, and then we'll do co-localization, or we'll take 6 objects, 2 variations, and then do co-localization, and so on and so forth, right? And then we tried to scale them with 2,000, 5,000 images, and if you read most of the papers that use that, none of those methods can actually scale up to large data sets. So the problem that happens is if you are a PhD student and you want to work in this space, you are very confused on where should we go next. Should we focus on those first family of approaches, right, which according to me are like the true sense of sort of what discovery wanted to do, or should we focus on these later set of approaches? And the problem is you have this reviewer too sitting who will always want to do the other thing, right? So if people have submitted papers in object discovery, if you do the right, they'll say, why didn't you do the left? And if you do the left, they'll say, why didn't you do the right? And so on and so forth. So this sort of vicious cycle continues. And that's my argument that that's why this field of object discovery was sort of held back. So where are we? So we lack consistent task definition. Right, and that I think is a big issue was a big issue. We have scalability issues. So we need to be able to scale up to large number of images, large number of categories, complexity, like number of images and number of objects per image and so on and so forth. And we sort of, all these approaches assume that you can do global reasoning, like pairwise comparison between all images in the data set. So joint optimization overall, as opposed to you keep seeing images, you keep discovering objects, you keep associating with them, but don't assume that you have access to the whole thing at once. Anyway, so all these current benchmarks that we talked about have all these combination of these issues. Either they are not realistic, they're toyish, they have unrealistic assumptions, they are designed more for classification, they are suited more for co-localization or co-segmentation. They only support qualitative evaluation, like there's no labels available to actually evaluate how to do discovery, and so on and so forth. So we presented a new benchmark or a new way of looking at this problem in this paper, Pursuit of Knowledge, led by Saket, which was the ICCV last year. And why I have an asterisk there is, this is not the challenge, final challenge benchmark that we're talking about. So I'll present the benchmark that we had. It had a lot more things going on. We simplified it for this teaser challenge, but we hope to make this teaser challenge more complex and probably borrow ideas from the great people on their metrics and incorporate it in the benchmark itself. So the goal was assume that your last object detection data set that was ever labeled was Pascal VOC. And that's where our labeling stopped, right? And then COCO sort of becomes your in the wild discovery set that, okay, you have given this COCO data set and you want to discover objects from it. If you want to have a detector train it on Pascal. If you want to have region proposal train it on Pascal. If you want to have knowledge of some objects, you train it on those 20 Pascal object categories, right? And again, this is not the challenge task exactly, but what we discovered was almost all teams that participated in the challenge, even if we didn't say this is the setup we want, everyone ended up using Pascal VOC as sort of hint for their detection system. So what is the challenge? So right now, if you had a detection training set, say VOC, you trained object detection system on these, right? And you tested on a standard image that comes from that data set, you get a good detection, you detect cat, right? But if you get an image which is from a different distribution, which have other objects that look similar, then you detect this bear as cat as well. So there's sort of semantic drift happening in your detection system. And the goal of this benchmark is you detect your 20 objects correctly, right? You know that when are these other objects not related to your 20 objects, you cluster those unknown objects together, and then you tell me that all these pink or magenta boxes are bears and all these green boxes are ties and so on and so forth. So you sort of discover this category from a large set of images. So before I go into more detail or salient characteristics and evaluation and all those things, the first question that comes up in people's mind is, doesn't it sound like X, Y, or Z? Because like people have tried to approach this from a variety of different angles, but there are subtleties in how they're different. So I'll mention some examples that come to mind. So the first one is these webly supervised never-ending learning frameworks like Neil and Levan and so on and so forth. The key difference, according to me, is they were sort of language driven in the sense that they had a priori list of concepts, right? They start with the term bear, go Google images, learn classifiers using whatever algorithm you want to use. There is some sort of reliance, at least this is true for the Neil system we had at CMU, there's some sort of reliance on canonical images. So if you have a canonical image, you can use that as detector, fire across, build a giant graph, and so on and so forth. The non-public data sets crawled from images, right? People keep asking, like people used to ask us, like, how do we compare against Neil? And you just can't. It's a proof of concept system, but the next day you Google those words, Google's algorithm would have changed. The images that you see for car back then on the top are very, very different from the ones that you see now. So it's very difficult to actually do fair comparisons when you have these kinds of webly supervised systems, unless someone has license to release, like Open Images was a good example of them releasing a bunch of images. The second area which is related to is sort of open world recognition. So which is basically you reject unknown classes. So you detect your 20 classes and reject all the unknown classes. And then you have a human in the loop or an oracle sitting that gives you labels for those, and then you train a classifier using that. So the benchmark that we have, there's some hint of doing this, that we use an oracle label to do Hungarian matching to actually train detectors and so on and so forth. But it goes beyond just doing open world recognition. And then there's online learning, which is learning new classes, new data of known classes, incremental learning, and so on and so forth. So the list goes on, and in the paper we discuss how they are related and different, and I'm happy to take those things offline. Otherwise, this whole talk is going to be just about how those things are related. All right, back to the benchmark. So the benchmark says you last label data sets, ImageNet if you want to do pre-training, Pascal VOC if you want to train detectors, and you have in the wild COCO labeled data set, unlabeled data set. So your known classes are these 20 object classes that you get from VOC. For testing, you can test these 20 classes as well, right? And you can test the detection performance, the open set performance, which is just throwing out the unknown stuff, semi-supervised learning performance, detect, add them back to the labeled set, see if there is semantic drift, if you improve performance, and so on and so forth for those 20 classes. Then you have unknown classes for quantitative evaluation. And this we can do on the 60 COCO classes that we have labels for. So for those 60 classes, we can say that, okay, we can train detectors for them using your clusters or whatever you provide us as the discovered classes, and then we can show performance. And that's what we call object discovery. And then you have object discovery and downstream detection task. And then you have 60 plus other objects that are not labeled in COCO. So we can do qualitative evaluation of those. And again, that's object discovery, but we can't really put numerical numbers on that. Okay. So now coming to the challenge benchmark, right? So challenge benchmark, we wanted to simplify all this paradigm. We didn't want to control a lot of things. So we said, you know what, forget about the last labeled data set, unlabeled data set, and so on and so forth. Okay. You can use self-supervised features, supervised features, just tell us what you used in order to solve this task. You just cannot touch COCO. That's the goal. And for testing, even though this no evaluation of known classes is very, very important, and it actually plays an important role in how discovery happens with prior knowledge and those kind of things, we sort of didn't want to get into that in the beginning. So we removed that component, and instead of 60 COCO classes, we said we'll evaluate on 80 COCO classes. So for pre-training, they can use supervised features, self-supervised features, They can use some sort of detection pre-training on VOC, not use them, whatever the algorithms want. And interestingly, almost all teams that submitted, they had a self-supervised Dino feature or VIT features, right? They had Pascal VOC boxes, either to train their out of distribution detection system or RPN system and so on and so forth. So they did follow the paradigm that we want in the benchmark, but we didn't have any restrictions this time around. Okay, so what are the salient features of this benchmark and the teaser challenge that we ran? So one benefit is these data sets are widely used and understood, right? And we have like new benchmarks coming up that also show generalization performance on these benchmarks. So you know the known performance, you know sort of the upper bound, you know what happens if you bring in more data from other data sets and so on. There is a rich discovery set with all known and unknown and related, unrelated classes. So it gives you a good way to evaluate algorithms across different setups of discovery. The images are complex, it's large scale, it is localization focused, so it's not just classification discovery, it's localization discovery, right? And any future progress in terms of labeling on these data set, for example, Elvis labeling set, which is the federated labeling set, we can actually use that and use it in our evaluation framework, because now every pixel is labeled. So whenever you discover other objects beyond these 80 classes, we can actually do some sort of evaluation using those. In terms of difficulty, even with these just 60 or 80 unknown classes, depending on whether it's teaser or the benchmark, it's still extremely challenging. It's still current setups, and this was before grid, current setups in terms of scale and difficulty just for the task of object discovery. And it deals with realistic images, which is, I don't know why we have to convince people to use that for this task. If now this I'm talking about more for the benchmark, not for the teaser challenge, there is a distribution shift from VOC to COCO in terms of the complexity, the number of objects, the number of images of known and unknown classes, and so on. And there is this notion of semantic drift, that if your dog classifier starts detecting pair and adds it to your labeled set to do some supervised learning, you have semantic drift, which we can actually evaluate when it's happening. So, so these are the salient features that sort of the benchmark offers. Now, in terms of metrics, this is the most tricky part. So we still have co-localization recall metrics just for completeness, because reviewers won't accept your paper if you don't report those numbers. We gray out those numbers when we report these, but we want to push, and we hope that some papers get accepted from reviewers where they don't use these metrics. Okay, but we recommend discontinuing using these metrics for this task. You have this discovery and pattern mining metrics like AUC of cumulative purity and coverage plots. The number of, you can also have number of discovered objects after you do the Hungarian matching at test time. The problem with cumulative purity versus coverage is it does not penalize over clustering. So you can give me as many clusters as the number of objects in your data set, and your performance is going to be perfect. So, so we have, for this challenge, we came up with this normalized AUC, which sort of penalizes the number of clusters that you have and the number of down-to-the boxes that you have and so on and so forth. We like the metrics that grid people have proposed for their discovery and how they do the matching and those normalizations. So this is the part that we're working on right now, in what metrics are suited for this task, which can give you one number that our field loves in order to compare on this benchmark. And then we have the Oracle detection metric, where you do majority voting for every cluster. If you're doing a clustering-based approach, you can do Hungarian matching if it's per image boxes, trainer detector, and then evaluate them on COCO minival, and you get some detection score. And that tells you how well, if you ask a mechanical Turker to give you one label for these 500 images in this cluster and train a detector, how well is that detector going to perform? And the good thing about this Oracle detection metric is it avoids humans in the loop annotations, because you have these 60 or 80 annotations on COCO. We can use them as Oracle annotations and train detectors. So it becomes an end-to-end pipeline, which was an issue with some of the past open world recognition systems. All right, so for the challenge, we had a discovery metric, which was the normalized AUC. We had an Oracle detection metric, which was MEP at 0.5. And we had reported some other metrics in terms of number of discovered objects and co-log, just so that teams know what their performance is. So the simplest approach you can imagine in solving this task, and this is at UMD, we did this approach with some bells and whistles to provide a baseline and to show that where that baseline will rank on the leaderboard. So you take some pre-trained features, supervised or self-supervised. You train some region proposal network, ideally class agnostic. It can be selective search, or it can be a trained RPN style system. Given all the COCO images, extract all the boxes, do some fancy clustering on some fancy features, get the clusters and done. Those are the clusters that you return. And that's the simplest thing you can potentially do. There are issues, like scalability is a big problem when you do any of these clustering approaches. How many clusters, how to choose when to cluster, is person a cluster or tie a cluster or clothes a cluster, and so on and so forth. What about background patches when they start clustering and dominating your discovery set? So for one tentative solution, like I'll refer you again to the paper where we proposed the benchmark, where we had a discriminative clustering approach, which was sort of inspired by discriminative mid-level patch mining papers. So I won't go into detail of that. I'll just jump to the challenge results. So for challenge, we had an option for teams to submit just to object discovery and evaluate on normalized AUC, or submit to both object discovery and then do the final downstream detection task doing the algorithm that we provided. So we had these many teams that participated in the challenge, and UMD team is the simple framework that I talked about. And we had a reasonable improvement. We did allow them to submit multiple times just so that we can see like how much are they able to push within 1 month of us releasing the data and the final challenge deadline. So we eventually, MIG was the team that ended up winning the normalized AUC at 0.14, and then Amadeus and then UMD. And there are a bunch of other teams which didn't discover as many objects, but on the top, like teams consistently discover 55 to 60 objects. But there was sort of a trick there. You do more clustering and then you do some fancy OOD stuff and you are able to do reasonable at that task. But it was very interesting to see this one-on-one mapping when you do the same team when they're doing the detection side of things. And since UMD, we focused on training a fast RCNA detector, we were able to get 8.6 AP on the mini COCO mini val. But all the other teams were sort of, it's still not random. It's still better on like 0.03 is still something on COCO. It's better than chance performance, but still it's a random, I would say it's a random detector. So all the teams that focused on clustering, just focused on clustering and improving their own clustering and how they can win this normalized AUC. But none of those could actually work in a downstream detection task. And as a side note, we did have the core log metric for all the entries. We had like 20, 30 entries. For all the entries, we had the core log metric, and the metric ranged from 95 to 96%, no matter how good the detection score, how bad the normalized AUC or anything like that. So another reason people should stop using those metrics for this task. All right, sorry for the small font size. We did that late last night. So for discovery, this is sort of the cumulative purity versus coverage plots for the top 3 winning teams that look like. So we had the winning team, Amadeus, in this, as you can see, had around 3,000 clusters, 58 objects, and the MIG team focused on sort of recall. So they were able to get a lot more boxes covered as opposed to Amadeus, and UMD was sort of in between those two. And there was interesting trend. So we did allow them to submit multiple entries. So you could see like, so on the left is MIG, on the right is Amadeus team. And you could see that across different submissions, they were actually able to push their performance up just within one month of them knowing what the task is, what the metric is to the final result. We only do analysis on UMD's detection system. The left one is not the true PR curve, it's just a precision at some specific recalls. So you can see that it's not as good as the PR curve we are used to seeing now on Pascal or COCO and so on and so forth. But it reminds you of when, like, before deep learning era, where detection systems were and how they were building up. So this should give you hope that yes, this task can be solved if this is the first stab at doing that task. And on the right, I show you the top 5 performing object detectors that were trained using this discovery method. And you can see that for classes like elephant and bear, you are close to 40–50% performance. All right, so that's the end of my talk. We'll have 3 different talks. We'll have MIG do a virtual recorded video. We'll have Amadeus who sent us the slides, so the organizer will present that. And then we'll have the UMD baseline team that will just briefly present what they did for training the baseline. So thank you, and I'll take any questions if you have questions.
Super quick question.
Yes.
So since like all the methods had like that did well had 60 classes roughly, which I think is the number of remaining classes in COCO, is that used like, is that basically because people know that there's 60 classes?
So in this one, no, because this one was not known versus unknown. This one was just 80 COCO. So there are like, you can read that as 60, they could discover 60 classes easily. but those 20 classes are the notorious ones that they were not able to discover. Second was, I think, and then that's what normalized AUC sort of hides it, and that's why I don't want that to be the final metric, and we are still debating. If you just over cluster to 3,000 clusters, you will be able to cover, like, because it's just majority voting. So if you have small clusters and you get 2 images of one box, two images one, you do oracle matching, you can merge all these clusters to be the same object. So that's what all the teams started doing, because our baseline code had 80 clusters, because we had 80 objects. We said do 80 clusters. They looked at the numbers and then they started pushing the over clustering thing, and that's where they ended up. So it's still difficult to beat the over clustering trick, but I think that is, if whatever metric we finally come up with has to deal with the over clustering. Like normalized AUC sort of deals with it compared to what we had before, but I don't think it solves the problem yet. Yeah, does that answer it? Any other questions? All right, thank you. We'll have the next team set up.
Good enough.
Good afternoon. This is Team MIG. Glad to have the chance to give the presentation. I'm presenter Yu Hongyang. This is our presentation content. First, we will go through our pipeline. Then we will elaborate 3 parts of model design, and finally give our experiment setting and results. First, let's overview the pipeline. As we illustrated in the figure, we take an image from COCO train, feed it into 2 independent networks, one for proposal generation and one for feature extraction. We use a class-agnostic RPN as the former, and the VIT fine-tuned using contrastive learning method as the latter. After extracting the feature, we perform over-clustering method on it to get a clustering model for discovery. Then here we introduce the class-agnostic RPN part. The overall RPN is similar to faster RCN, but classification head is replaced by a new localization quality head in here and here. We use IOU or centerness to measure the localization quality of one proposal. We found that class-agnostic RPN shows more robustness on those novel categories on COCO. After process, we get 3,000 proposals and we perform a class-agnostic NS on these to filter these exhausted proposals. Now we have region proposals. Utilizing these proposals, we designed a contrastive method to fine-tune our feature extractor from dyno initialization. First step, we crop the images into instance patches. VOC images are cropped using ground truth boxes, and COCO images are cropped using generated proposals. Then we form the label set and unlabeled set. We are able to use supervised contrastive loss on the label set and unsupervised contrastive loss on the whole set. The way these two laws calculated are shown here. Zi denotes the feature of instance patch. Zi and Zi prime are different views created by a random augmentation. In supervised contrastive loss, Ni denotes those indices of patches with the same label as Zi. After extracting features, we use mini-batch over clustering method to produce a clustering model for discovery. During we discover baseline methods, we found that enlarging the sample size from feature pool can increase the discovery performance. But due to the complexity of k-means, it also brings inefficiency. So we use the mini-batch k-means instead to utilize our feature pool. Secondly, we found overclustering can boost the purity AUC. This is because when cluster increases, model can produce fine-grained clusters, which are expected to be pure. And last, we'd like to share our experiment setting and results. In class agnostic RPN part, we use Dino initialized ResNet 50 as backbone and train it on VOC before producing proposals on COCO. In contrastive fine-tuning part, we use a VIT-based model as backbone and take the cropping strategy as we mentioned before. In clustering part, we sampled 500 kilo features from feature pool and perform mini-batch overclassing method with 124 batch size and 3 of 4,000 cluster norm. And here are our discovery results and detection results. We placed first in discovery challenge and second in detection challenge. This is all of our presentation. Thank you for listening.
Now we'll have team Amadeus, and for that, Anubhav will be presenting the presentation. Yeah, is it fine? How do I exit this? Perfect. Oh, yeah.
Hello, everyone. I'm Anubhav, and I'll be presenting on behalf of Team Amadeus. So I'll skip the part where they explain what the challenge is. I'll directly get to their solution. So they have a straightforward approach. First of all, they use the pre-trained detector, and they run an RPN, and through that RPN they get the unknown boxes. And for getting these unknown class boxes, they use an approach. I think that was introduced in the paper called Open World Object Detector, and they follow the exact same approach. And once they get those boxes, they get the features of those boxes through a pre-trained VIT on the dyno task, and then they cluster those boxes, and they figure out the open world classes. So in detail, what they have done is they train a faster RCNN architecture using a ResNet 50 backbone. They follow the approach that came in our paper, and it basically initializes some unknown clusters based on the RPN confidence of the objectness, and then it changes the loss in the ROI pooling head, basically adds a contrastive loss on the prototype for each of the classes. In this case, they have the Pascal VOC, so they have the 20 classes from Pascal VOC plus one unknown class, and then they train this detector. Then they run this detector on the COCO train set, through which they'll get the bounding boxes from this detector, and then they apply k-means on these on the features of these boxes, which they get from the VIT model trained using dyno, and that's how they get their clusters. Once they have these clusters, they run the same model, the detector model, on the COCO minival set, on which we are computing the performance, and they assign those boxes to the clusters that were discovered through the k-means, and that's how they get their results. So they have some ablation experiments where they show that as they increase the number of clusters, they are able to discover more objects, and their AUC has improved. Yeah, that's all that we have from in their presentation. Thanks.
All right. Now we have team from UMD. Archana Swaminathan will be presenting. So Archana, can you?
Yeah, on it.
Thank you. One second. What do you have to do?
Can you see my screen?
Yes.
Okay, thank you. So, good evening, everyone. I am Archana Swaminathan, and I am here on behalf of Team UMD.
Archana?
Yeah?
Can you just wait for a second, please?
Yeah.
Archana, can you start sharing?
Can you see my screen?
Yep, go ahead.
Okay, so good evening, everyone. I'm Archana Swaminathan, and I'm going to talk about what we submitted to the Object Class Discovery Challenge. So to begin with, you guys are familiar with the problem at hand. What we had to do was we had to discover novel objects in an unlabeled data set. Over here, we were tasked with using COCO 2014 trained data set. And we could use knowledge from known objects, where Pascal VOC was our known data set. And then we also had to check the real world application of whatever discovery approach that we come up with. to see if that we can detect these objects again. So we had some options while choosing the baseline, and we went with the self-supervised approach. So the self-supervised approach is very simple because there are no labels involved when we choose the Dino supervision approach. Whereas in ImageNet, all the classes that are there in our unlabeled data set, which is COCO, are also present in ImageNet. So this makes the problem unfair. So we go ahead and use Dino initialization. So what we do is we train a faster RCNN detector with the ResNet 50 backbone with the Pascal VOC data set. And after doing that, we take our discovery test data set, which is COCO 2014 train. And we run the 2014 train, we have a detector run over it and extract boxes. And then from after extracting the boxes, we extract the Dino features from these boxes. So now after extracting the Dino features, we had the choice of choosing the number of clusters that we wanted to cluster these features into. So we ran a number of experiments from starting with 100 clusters and then going up to 1,000 clusters, and we just increased it every time by 100 clusters. So we realized that by choosing 900 clusters, we evaluate all these experiments for the normalized AUC, and we see that 900 clusters gives the highest normalized AUC. So we choose that as our baseline model, and then we perform the rest of the challenge. But then after looking at the leaderboard, and we realized that the more number of clusters that we train, train the GT with, the better the normalized AUC will be. So then we ended up having experiments with 2,000, 3,000, and 4,000 clusters as well. So now we ran our experiments with this. So we had 900, 2,000, 3,000, and 4,000 clusters. And then we took these cluster IDs as the new category IDs. And then we trained our models all over again to check the detection performance. But we see that the detection performance after having so many new classes is quite poor. So we decide to use a clustering approach to reduce the number of these new classes to make it easier for the model to detect them again. So we go ahead and we choose Finch clustering because Finch is fully parameter free and it's very easily scalable to a large data set. So it worked very well with COCO, and we were able to compute these cluster partitions very quickly. And it also does the clustering automatically compared to k-means. So using the Finch clustering for our baseline experiment where we had 900 clusters, we were able to bring down the number of clusters to 207 and 131, which was by using the cosine and Euclidean distance functions for the Finch algorithm. So after getting these clusters, we retrain our models and check the detection performance. And we see that the detection performance has considerably improved as compared to using 900 or 2,000 or 3,000 clusters. So we also had another experiment where we decided to look at the COCO samples that were not in the distribution and cluster only them. So what we did here was we trained a support vector machine to overfit the VOC dataset, and then we run the COCO dataset through this. So through this SVM, we find out which classes are known and unknown in VOC, and we use the original labels for the known classes, and we apply the Finch clustering only to the unknown classes. And then once we have these known class labels and the Finch clustering labels, we use these as the new category IDs and retrain another faster RCNN with these labels. So this way, again, using the cosine and Euclidean distance functions, we had like 1,000 clusters and 651 clusters. And then finally, these are our results from the leaderboard. From this, you can clearly see that for the discovery challenge, the more number of clusters gives you the more number of newly discovered objects. And you also have really high normalized AUCs with that. But then in turn, this leads to poor detection performance. So we noticed that the experiments that we ran with the Finch clustering by bringing down the dimensions, we were able to have a much better detection performance. And so this is, a step ahead in improving the real world applicability of such a system. Thank you very much.
Thank you, Archana. Now we'll have Shu to give the closing remarks.
All right, thank you so much. Let me wrap up. First, I think this workshop is quite successful, and thank you for attending the workshop. So please enjoy the conference and happy holidays. And we have recorded all the talks, so we will release them after the conference. Anyway, I'll see you next year, and enjoy. All right, bye.
All right.
Thank
you,
you
Shu.
all. Yeah.
Yep. Thanks a lot to all the volunteers.
Yeah, thank you, Tom, Yushu, Shannon, everyone.
Thank you so much.
Yeah, hi. Yeah, bye. Okay.
Bye.